Final check. Mic. Mic check. Last time.
Am I audible clear? Yeah, sure. Thank you. A very good morning to all the respected invitees, delegates, participants who are joining us online and present here at Multipurpose Hall. It is a moment of great honor and delight to welcome you all at the inaugural function of 2 days theme meeting on nuclear probes for materials, medicine, and industry, NPMMI 2022, organized by Radiochemistry Division BRC and co-organized by Society for Positron Annihilation and Nuclear Probes. Today we are delighted to have Dr. S.M. Yusuf, Director, Physics Group BRC, as our guest of honor. Now I welcome our guest of honor, Dr. S.M. Yusuf, Dr. P.K. Pujari, Director, Radiochemistry and Isotope Group, Dr. P.K. Mohapatra, Head, Radiochemistry Division, Dr. Y.K. Bhardwaj, Chairman, Organizing Committee, NPMMI 2022, and Head, Radiation Technology Development Division, and Dr. Priya Maheshwari, Convener, NPMMI 2022, to please come to the dais. Thank you all for the honors. May I now request Dr. P.K. Mohapatra to head Radiochemistry Division to welcome this gathering. Please.
Dr. P.K. Pujari, Director, Radiochemistry and Isotope Group. Dr. S.M. Yusuf, our guest of honor, Director, Physics Group. Dr. Y.K. Bhardwaj, Organizing Committee Chairman of this theme meeting. Dr. Priya Maheshwari, the convener. Dr. Tomar, Dr. Ghanti, Dr. Parida, Dr. Pant, other delegates present here and also those who are attending online. Now I welcome all of you to this 2-day theme meeting, which is organized here at BARC. Now, as the name suggests, this is the nuclear probes for materials, medicine and industry. So now, this nuclear probes, this research started in Radiochemistry Division long ago, I think maybe around 1985. It was initiated by Dr. Satyaprakash. And the two fields which we started that time is positron annihilation spectroscopy and time differential perturb-angular correlation. One was, I think, Dr. Tarun Datta and Dr. Pujari. The positron annihilation spectroscopy part, they have started working from 1985 onwards. And Dr. Tomar and Dr. S.K. Das, they started working on the TDPSC around same time. Now this positron annihilation spectroscopy, it is, as you know, you may be knowing, it is very important for this defect structural analysis in materials, like the voids, dislocations in the maybe the metals and alloys, and even soft matter also, the holes can be found out, about information about the holes can be found out by positron annihilation spectroscopy, depending on the lifetime of the positron. So if the longer lifetime, you have a defect compared to the perfect structure. Again, this medicine, of course, it is well known, everybody knows this PET technology is being used where this fluorine 18 DFC compound is used routinely. FDC compound is used routinely, and it's a very sophisticated technique which are not available previously at many centers. Now we are slowly getting this. Now, this coming to this TDPSC, of course, this is work which I'm starting radio chemistry division, and Dr. S.K. Das, who has shifted to our VCC laboratory in radio chemistry. There also a lot of work is being carried out in TDPSC. Whereas you may be knowing, this is some radionuclides and special radionuclides are available where you have two consecutive gamma rays are emitted, and by correlating them, the anisotropy in that, so they can find out information about the host lattice. So you basically have, I think, this 181 hafnium and 111 silver or indium and 199 metastable mercury, which is, I think, very short half-life. People are planning to do it, but I think we have not carried out any study here. So now this also gives a lot of information from this angular correlation coefficients about the structure of the host. Now, this work, which has been started long ago, I think, in the radio chemistry division, is still going on very strongly in our with the leadership of Dr. Pujari and his dedicated team. They started with the positron annihilation spectroscopy initially, then they got, I think, a slow positron beam, and now they are developing a pulse positron beam, and also this pulse, the positron annihilation lifetime spectroscopy, that also they are carrying out studies. I think this is a very good thing they have started, and it is motivating a lot of young people to carry out studies in material science. So I expect that this work will be carried forward by our motivated colleagues, and also we invite collaborations from other centers from India to coordinate, collaborate with radiochemistry division colleagues, carry out this study further. So with this, one more thing I wanted to say that this, I think this positron discovery was in 1932. So this is the 90th year of positron discovery, and angular correlation time, it was discovered in 1947. This is the 75th anniversary of TDPSC. So this is a very special occasion also to commemorate these discoveries. So with this, I welcome you all for a very fruitful deliberation and discussion on this two-day theme meeting. I hope it will be very interesting for all of you, and also our foreign delegates, those who will be speaking on this occasion. This will be quite a learning experience for most of the delegates. Thank you.
Thank you very much, sir, for giving us such wonderful glimpses of the journey of Positron Lab at Radiochemistry Division. May I now request Dr. Y.K. Bhardwaj, Chairman, NPMMI 2022 and Head, Radiation Technology Development Division, to brief the audience about this meeting. Please.
Thank you, Ms. Debrati. A very good morning to you all. This theme meeting on nuclear probes for materials, medicine and industry, NPMMI 2022, organized by BRC in collaboration with Society for Positron Annihilation and Nuclear Probes, is fourth in the series of Bombay positron meetings. Earlier meetings were held in 2012, 13, and 18. So this series of meetings is still in infancy, as it is just 3 meetings young. But I like to share here that the response to our earlier meetings have been overwhelming. The main objective of these meetings has been to bring together scientists and researchers around the world working in the area to share their experiences, results, observations, and discuss new advancements in the field. Earlier meetings primarily focused on positron as a probe for different materials like metals, alloys, semiconductors, polymers, porous materials, and advancement in positron annihilation techniques and instrumentation, and also for healthcare applications like positron annihilation-based diagnosis therapy and imaging like PET-CT or PET-MRI. These meetings would provide a common platform to researchers, scientists, physicians, and industrialists to form a close-knit network for cross-breeding of ideas and to get into further collaborations. With the realization that a single technique or probe may sometimes not be sufficient to resolve a fundamental scientific problem, and it would be better to use other complementary techniques to have a deep insight into the problem. The scope of earlier meetings has been extended through this meeting. This meeting integrates other nuclear probes for their applications in material research, medicine, and industry. Here, I would like to add that to comprehensively integrate the fraternity of researchers in the nuclear probes and to provide them a common platform to take ahead related activities. Recently, the Society for Positron Annihilation and Nuclear Probes has been registered, and this body is co-organizers for this meeting. The present meeting would be spread over 6 technical sessions, where 16 invited talks will be delivered by national and overseas experts, including eminent medical doctors. Talks will cover not only the application of different nuclear probes for material, healthcare, and industry research, but also the challenges involved therein and other recent advances in this field. There are 25 posters from young researchers which will be displayed online during the meeting, in addition to the physical poster presentation by local participants. The technical session will be followed by a panel discussion on radiation isotopes for social application tomorrow evening. With this, I wish you all a fruitful, scientifically enriching meeting ahead. Thank you so much.
Thank you very much, sir, for giving this comprehensive overview of our meeting in PMMI 2022. May I now request Dr. P.K. Pujari, Director, Radiochemistry and Isotope Group, BRC, to give his valuable remarks.
Good morning, Dr. Yusuf, Dr. Mahapatra, Dr. Bhardwaj and Priya in the audience. Very nice to see Sarwalji after many, many years. Dr. Ghanti, Dr. Tomar, Dr. Acharya, Dr. Parida, my colleagues and delegates. So, as it has already been mentioned, we started Trombay Positron meeting in 2012, and the title was the same. It was Positrons in Materials, Medicine, and Industry. And that was a very much successful meeting, and primarily it was aimed to consolidate the positron activities in the country. And we had many participations those days from universities. Also, we followed it up with in subsequent years. And in addition to Indian participants, primarily from DA organizations and few universities, we had our friends from overseas who used to participate, who have participated in the past. And today this meeting also, we have 5 or 6 speakers from abroad who will be participating. And we had a big meeting, that is PPC 11 in Goa. That was that because of that it was kind of going on biennial, but we couldn't, we did not hold this positron meeting during that 2014 or so. So coming to, like it has already been mentioned by somebody that positron, though, has been the focus, and we are having very active collaboration, and the use of neutrons and other nuclear techniques to, do good science. And you will see that it is broad based under the auspices of this organization, and we have a lot of participation from the neutrons people, and aptly Dr. Yusuf is here, and would like to hear from him about his impression. And having said this, the positron, we have a session, the final session, a group discussion about applications of both neutron in industry, medicine, and material science. Of course, it is very well known. You will see we have somebody talking on neutron boron capture therapy to neutron radiography. Of course, is becoming very popular, and you will be happy to know that BRC is now actively going to collaborate with industry for offering its neutron beamline for that purpose. So I would not like to take more time on my talk. I would like to hear from Dr. Yusuf his impressions, and I look forward to a very interesting session this meeting. And I welcome my friends from overseas who would be participating in this meeting. And I thank my colleagues who have really organized this meeting, and this is a all-women team actually. Priya Mashpuri, the convener, and Devarati Das is the secretary. So happily, the Women's Day is coming. Maybe we could have held it. It's a joint effort, but of course there are others who are supporting in the background, but they have taken the lead, and that's very heartening to see. And with this, I thank you very much for participating in this meeting. Thank you.
It was off. Yeah. Dr. P.K. Pujari, Director, Radiochemistry and Isotope Group of Bhabha Atomic Research Center, and President of Society for Positron Annihilation and Nuclear Probes. Dr. P.K. Mahapatra, who is the Head of Radiochemistry Division of BRC. Dr. Bharadwaj, Head RTDD and the Chairman of this theme meeting. Dr. Priya Maheshwari, who is the convener of this theme meeting. Other delegates, I see my very respected senior colleagues, Professor Tomor and others, my TC colleagues, my friends, all participants, dignitaries, ladies and gentlemen, and particularly who are joining online and from overseas. So I am really indeed very happy to be part of this inaugural function of this theme meeting on nuclear probes for materials, medicines, and industry 2022. And it is being organized by the Radiochemistry Division of BRC, and of course, in association with the Society of SPAN. And as it has been already pointed out, that this is probably the in a series of meetings, and it is started way back in 2012, and it is really a good initiative from RCD to have this kind of theme meeting, because it can consolidate all the ideas and the new concepts and developments which are taking place not only in BRC, not only in India, but across the globe, and that you will be witnessing in the next 2 days of this theme meeting program. This positron annihilation spectroscopy is very fascinating in the sense, as you know, the positron is the antiparticle of electron, fundamental particle. And positron, when it is, you can get from isotopes like sodium-22. And when it is implanted in a material, if there are, let us say, voids where there lacks of positively charged particle, so it gets captured over there. It can also, for example, insulating material, positron can also form positronium by taking electron. So both this positron and positronium has a special property because it is the lightest atom, as you can see, and as you can imagine, and it is the smallest in size, so it can easily go to these voids, defects. But both positron and positronium, they can decay. In fact, lifetime is from typically 0.1 nanosecond to few nanoseconds. And when it decays, it gives the information about the voids, because the decay time is correlated with the void size and so on. So this kind of, by doing experiment and by doing detailed analysis, one can talk about the defects and voids in materials, and that has been fruitfully utilized by my colleagues, and that is led by Dr. P.K. Pujari. And I congratulate them for this great success in this area. And you will be hearing many talks in this area, not only from his group, but from other groups, including overseas speakers. Now, another area, sub-area,
what is called the development of slow positron beams, because depending upon the, if you can tune the energy, what happens, you can essentially talk about this penetration depth. And as a matter of fact, then you can study thin films or polymers, this kind of material, where it doesn't have to penetrate that high. So this is another area which has been fruitfully developed and utilized. Positron emission tomography, what is known as PET, and for that, as you know, F18 isotope is very, very effective, and the PET diagnosis is routinely being carried out with the help of the medical cyclotron, which where the both RMC and VCC is playing role. And here I like to call that, recall that, there will be another RMC center at Kolkata, and that is again Dr. P.K. Pujari and his group. They have taken strong initiative, and it is coming up. It is almost at the final stage. Now coming to another nuclear particle, nuclear probe, which is neutron, and which is very close to my expertise, because the neutron is a another fundamental particle like proton, but neutron does not have any charge, but it has got magnetic moment. And neutrons, as you know, it was discovered by Chadwick in 1932. And after the discovery of neutron, there were first, test reactor was developed, as you know, the Chicago Pile 1 and Pile 2 test. But the first reactor was developed at ORNL, and that was related to the Manhattan project, graphite reactor, as you know all. And after that, many reactors are built over the globe. Also, this Palestine neutron source, you get lots of neutron flags. So neutron has this amazing property. Without having charge, a nuclear particle, it can penetrate deep into the matter, and it gives all the ingredients to study bulk materials. Bulk means I am talking about centimeter kind of length scale, where it can penetrate. And my expertise is on the magnetism side, because neutron carrying magnetic moment of minus 1.913 nuclear magneton, so it can interact with the magnetic moments of electrons. In fact, it can interact with also the magnetic moments of the nucleus, if nucleus is having non-zero moment, and one can study that. So neutron has several advantages over X-rays in terms of the contrast factor, because neutron, being a nuclear particle, it interacts with the matter. It does not go by this atomic number. Rather, it decides it goes by the nuclear interaction. So the nuclear interaction, it is such a way that it will depend upon the isotopes. It can vary the scattering strength, depending upon which isotope, even for a given element you are talking about, because nuclei is different. Okay, so as a result of that, the contrast, for example, one can detect very light elements, for example, hydrogen, okay, deuterium or deuterium, in presence of very heavy Z elements. It can give the sensitivity of detection of two neighboring elements from the periodic table with almost nearing Z elements. For example, you take any tensor metals, you can do. So this kind of advantage it has. As a result, this area has developed, and its benefit is being utilized all over the globe. So neutron also, so as a result of that, if you go to our Dhuva research reactor, you will see there are various beamlines for different purposes. You will be hearing some of the benefits of that. My colleague will be speaking about some of these aspects. Neutron is also used for neutron activation analysis. For that, Dr. Acharya is there. He has used one of the beamlines in Dhuva guide tube lab, and he has been very passionate about it. He has been doing this. So this neutron activation analysis, or prompt gamma neutron activation analysis, it is very another important area in this department. So I'm sure that in next 2 days you will be discussing about that. Neutron capture radiography, which was mentioned by Dr. Pujari, this is yet another important area. But what is most important that apart from this neutron scattering or neutron activation analysis, what is also this reactor can give the isotopes for healthcare purpose. And that both in Indian context, in DA context, both this Dhuba research reactor as well as Apsara U, both are producing isotopes for healthcare. So they are the role of course, this radiochemistry and isotope group of BRC, as well as RMC, as well as BRIT, you know their contributions, and it is really helping for mankind. In fact, this neutron activation analysis is very fruitful in other areas, including environment, forensic science, material science, food, and so on. But of course, I like to mention here that the inductively coupled plasma mass spectroscopy, so that is very competitive because their sensitivity is better than this the neutron activation analysis method. But of course, the NAA has its own advantage in terms of dealing with the solid materials. So that advantage is there because solid samples can be investigated by this. So when we talk about these nuclear probes, we must also talk about other nuclear methods, which is again close to my expertise. For example, MOSFET spectroscopy, the nuclear magnetic resonance, MRI, and so on. So these are very powerful techniques for studying magnetic related phenomena, particularly MOSFET spectroscopy, which is again basically utilization of gamma. And this gamma ray, this MOSFET spectroscopy has become much more now versatile after the availability of the synchrotron radiation, because it is not limited to only iron 57 or specific 5F element. So it has opened up the almost entire periodic table because of the availability of this tunability of synchrotron radiation wavelength. I must also mention the benefit of the charged particles, whether it is proton or other charged particles. They are also very much exploited in BRC and other places to study materials. For example, we have Photia accelerator, we have Platon. So from there, various kinds of charged particles are produced and being used as nuclear probes. So I can see the very good program is lined up from today and tomorrow, and you will be witnessing this. And I must congratulate all these organizing committee members led by Dr. Pujari and of course chairperson and convener. They are very much here. So it will be a great benefit, beneficial. It will be great beneficial for the community who are practitioner of this subject area of all nuclear probes, because putting together in this vast subject area together is a commendable job, and I'm happy that this activity is being taken forward by the RCD of BRC, and we look forward for a great theme meeting over these next 2 days. Thank you so much.
Thank you very much, sir, for enlightening us with your insightful and motivational words. May I now request Dr. Priya Maheshwari, convener NPMMI 2022, to give the vote of thanks.
A very good morning to today's guest of honor, Dr. S.M. Yusuf, Director Physics Group, Dr. P.K. Pujari, Director, Radiochemistry and Isotope Group, Dr. Y.K. Bharadwaj, Head, Radiation Technology Development Division and Chair, NPMMI, Dr. P.K. Mahapatra, Head, Radiochemistry Division. It's a privilege to have been asked to propose vote of thanks in this gathering. At the outset, on behalf of Organizing Committee of NPMMI, I express my profound gratitude to Dr. S.M. Yusuf, Director Physics Group, for sparing his valuable time to address this gathering. Thank you, sir, for your encouraging words. I'm deeply thankful to Dr. P.K. Pujari, Director, Radiochemistry and Isotope Group, who has been a constant support and source of encouragement and guidance behind this meeting. Under his guidance and mentorship, we could initiate the series of positron meetings, which are Trombe positron meeting, and this is the fourth in this series where we have widened our scope. On behalf of the whole organizing team, I sincerely express my gratitude to Dr. P.K. Pujari for being a solid support for us and mentoring us throughout these years. I extend my thanks to Dr. P.K. Mahapatra, Head Radiochemistry Division, for his invaluable guidance and constant support to organize this meeting. I wish to place my sincere thanks to Dr. Y.K. Bharadwaj, Chairman Organizing Committee NPMMI, for his constant encouragement and guidance throughout this meeting. On behalf of Organizing Committee NPMMI, I convey my deep regards and thanks to Dr. S. Kannan, Associate Director at CNI Group, for his guidance and support in all possible manner to organize this conference. On behalf of NPMMI, I express my hearty gratitude to the distinguished speakers from India and overseas, distinguished participants and delegates for their significant presence and participation in this deliberation. I extend my gratitude to the members of panel discussion for gracing their expert views and opinion on the subject. I thank all the TC members for their kind support for organizing this conference. On behalf of organizing team, we extend our gratitude to all the members of advisory committee and organizing committee for their invaluable suggestions and guidance. I place my sincere thanks to SPAN for supporting this meeting financially. NPMMI 2022 is thankful to all the BARC and TSH administrative staff and security personnel for their cooperation, which enabled us to host this meeting smoothly. I express my gratitude to Dr. R. Acharya for his constant guidance, which helped us in planning and organizing this event meticulously. Last but not the least, I express immensely my heartfelt thanks and appreciation to my team, the members of Nuclear Probe Section, who have been a rock-solid support system at each and every step of planning this meeting. I have been fortunate enough to have such a wonderful team to work with. Our team leader, Dr. K. Sudarshan, who has been a round-the-clock guidance and navigation system. Thank you, sir. It is hard to pinpoint the contribution made by each individual member of the group, but the synergistic effect made by each of them has been commendable. And I sincerely express my profound gratitude to them for putting their zeal and zest to make all the preparations. Thank you all. I especially thank Ms. Debarati Das, Secretary NPMMI, who has always been on toes all the time. Thank you. I like to place my hearty thanks to all the people who worked in the background and whose name I might have forgotten to mention. So with this, on behalf of the whole organizing team NPMMI, I wish you all a pleasant and fruitful deliberation at the meeting. Thank you all. So now I request you all for a group photograph. So I think we may have to come towards the dais side. And after that, I invite you all for a tea downstairs. I announced. Yeah. And we will be reassembling in the hall for the next section, sharp 11. Thank you. The talk is the online talk, so I request you all to be here on time. Thank you. I request all of you to please come forward to this side so that
चलो
हम लोग आगे Welcome to the first session of Day 1 NPMMI 2022. I request Dr. P.K. Mohapatra, Head, Radiochemistry Division, to kindly chair this session.
Thank you, Devarati. So the first scientific session will start with the presentation by Dr. Reinhard Rehberg, the Martin Luther University, Halle, Germany, and the lecture title is Introduction into Positron Annihilation Spectroscopy for Defect Analysis in Solids. So Dr. Rehberg, please.
Yeah, hello. I guess you can hear me. Can you hear me? Hello?
Yeah, you're audible. Yes.
Okay. Thank you very much. So first of all, it's 6:30 in the morning. So good morning to everybody. And thank you for asking me to give an introduction into positron annihilation as a tool for defect studies in solids. So I will start with some historical remarks. And after that, I will introduce you briefly the two main important techniques for defect studies, which is positron lifetime spectroscopy and Doppler protoning spectroscopy. Thereafter, I will introduce you in this positron trapping model, which gives us the possibility to calculate concentrations of defects. Then finally, I will speak a little bit shortly about semiconductors. There are special properties of positron annihilation there, and then I will give you two more examples. Yeah, so positron was discovered by, actually was predicted by Paul Dirac at 1928, and it was discovered in 1932 by Anderson. You can see here this trace of a positron penetrating through a lead plate. Then thereafter, shortly after this time, positronium was predicted and discovered later in 1951. And then the positron researchers started to study annihilation in matter in the beginning of the 40s. I will show you in the next slide one of the first papers. Positrons can be obtained, of course, not only from cosmic rays, but at large facilities, at reactors and accelerators, we can use pair production. So we have to use gamma radiation larger than 1.02 MeV to get positrons. And in laboratory setups, as most of us have, we can use beta decay sources like mainly 22 sodium. Yeah, so in the very beginning, it was already clear that the conservation laws must be fulfilled during annihilation. So this is energy and momentum of the electron-positron pair. And because the positron there's only one positron available, so there is, it will be in the ground state with very low energy and momentum. That means that this pair has energy and momentum of the electron. So we can really study electron momentum distribution. And this can be directly measured. And this was shown for the first time here in this paper. So if you have a momentum of the electron in direction of the penetration of the gammas, then you have in perpendicular to the direction of the gammas, you will have some kind of angle deviation, and you can measure it. And this was first time measured here. Nowadays we do it in two directions. So we have two-dimensional detectors, so we can measure in X, Y direction sharply, and we make an average in Z direction, in the direction of the gammas. And if we take here single crystal and we just move it and 2-3 times, and then you can reconstruct the complete energy momentum distribution of the electron. This is a famous example, and this is the famous Fermi surface of copper with its necks, and this has been measured by positrons, and theory is very much the same. And this was a nice application for this in this direction. In the 50s, 60s, we got more experimental techniques, so positron lifetime and Doppler broadening technique. And then people found that the positrons are very sensitive for crystal lattice effects. So Brandt, for instance, found that vacancies in ionic crystals are positron traps and changed the annihilation parameters, which you can measure. And Dechia found in plastically deformed semiconductors that there is trapping by defects. And nowadays we know that these are dislocations and vacancy clusters actually. And McKenzie found that vacancies in thermal equilibrium in metals can be found. So that means that close to the melting point, there's a large number of thermal vacancies in equilibrium, and we can measure them. And I will show you later an example with what we did. So what we can mainly study is then open volume defects in at least in metals and semiconductors. So vacancies, vacancy clusters, also dislocations, grain boundaries when they are not too far away from each other, and sometimes precipitations in metals and also in semiconductors. But the positron lifetime spectroscopy is the main tool for studying defects in solids. So in laboratory setup, as I said, we can use 22 sodium sources. This has the advantage that together with the positron, a gamma is released. So it's 1.27 MeV gamma. And so you can measure from outside the start. When the positron is born, you can see it, and you detect this by scintillator and photomultiplier, as you will see in the next slide. And then the positron penetrates deep into the sample when it comes from the source with an energy up to 540 kilo electron volt. And so it goes in about 100 micrometer. Then during this pass, it will lose its high energy and reach thermal energy, KT. So this is called thermalization. And then the positron starts to diffuse for about 100 nanometers and annihilates somewhere in this sample with an electron. If there is a positron trap, like here, a vacancy, it is a trap because this positive core is missing, and so therefore you have some binding energy. It's about 1 electron volt, so it's deep enough, and it's much larger than thermal energy. So positron being there once, it will annihilate in this position and change its annihilation parameters. So especially the lifetime. The lifetime becomes larger because the electron density here is smaller, and when the electron density is smaller, lifetime becomes larger. And you can measure it because during annihilation, we have this 511 MeV annihilation radiation, and the time between these two gammas gives a lifetime. So we can identify defects, and we can also quantify them. Positron lifetime spectrometer nowadays is digital and very simple. So you have these scintillators, photomultipliers, and the anode pulses are then digitized in a digitizer and connected to a PC. So we have this start gamma 1.27, stop gamma 511 kV, and then we get a positron lifetime spectrum. A single event is measured like this, but we have to measure about 5 to 10 million counts to have a good spectrum. This is an example of these anode pulses. This is a start pulse, and you can see here we have the time mark for start, and stop is later, and the time difference can be easily calculated here and can be stored. And then if we have 5 to 10 million counts, we have the spectrum. And to quantify the defects and to measure the defect concentration, we can use this trapping model. This is the most simple one with just one defect type. So what happens when the positron comes from the source? It is first in the bulk, and from this state, it can disappear by annihilation from the bulk with a bulk annihilation rate, or it can be trapped actually into the defect. Yeah, this gives this first equation here, and then in the defect, it can be in this state. This is called defect. Oh, Priya told me there's some problem. I don't know what is the problem. Can you hear me still? It's good Could be somebody confirm me that you can hear me? Akira? So Andreas said everything is okay. Priya asked me to stop my talk for a moment. I'm sorry. So I will wait for a message of Priya that everything is okay. Andreas, can you hear me, Andreas? Yeah. And so everything okay with you at your side with the talk and everything? Okay. Yeah, okay, alles okay. So I don't know. I wait for Priya's message that everything is fine. So I can see Akira's cat as always. Okay. Yeah. So Priya, please tell me when I have to continue, when I can continue my talk, yeah? Yeah, I don't know. So Andreas told me that everything is okay with my talk and also with the video. So I don't know. So I think I can simply continue. Andreas, what do you mean? Everything okay with you? Shall I continue? Okay, so maybe it's better to wait for Priya's message. Es ist small. I'm sorry, Andreas. Es ist ein bisschen zu klein. Ich kann es nicht lesen. Sorry. Ich bleibe mal in meinem Talk drin. Ich will hier nicht rausgehen. Aber du kannst mir gerne eine WhatsApp schicken. Das lese ich. Yeah, I don't know. So whether I can continue. I still have the requests of Priya that I have to wait and have to stop my talk for a moment. In case I can continue, please tell me. Ja? Okay. Gut, dann wird es gleich weitergehen. Danke. So I can see the conference desk once again. So I hope I can continue, right? So may I continue? Okay. So yeah, okay. Thank you very much. So Priya told me that you are there. I mean, Andreas told me that he was all the time connected to me. And okay, yeah. And so, but now it works again. So I was just explaining the strapping model for determination of defect concentration. So as I would like to say that I start again with the foil, I think. The positrons from the positron source are first in the defect-free bulk. And from here, they can disappear by annihilation, but they can also be trapped, this pass and this pass. So then they disappear here. This is the first equation. Second equation is this defect state can be liberated by trapping, kappa d, this is trapping rate. And it can be then can be left there by annihilation here, this lambda d. This is a different annihilation rate. This, if you solve this equation system, it's very simple. You get two exponential decay components, and here you have the abbreviations for this. And from your if you and if this is one defect type, and then we have two k plus one means two lifetime components, and this holds for more defects. If you have two defects, you will have three lifetime components. And okay, yeah, this is an example for lifetime spectra. The red curve is for silicon, for pure silicon without any defects, one component, bulk component. And if you have a plastically deformed silicon sample, then you get actually two defect components, two defects and three components in the spectra. This one is for die vacancies, 320 picoseconds, and 520 was for vacancy clusters. These are many vacancies clustered together. I will not go into detail about this experiment, but you just to show the spectrum. And if you have just one component, you get this very simple equation here. You can fit the data, that means the lifetimes and the intensities by nonlinear fitting method. And you will get these numbers and you put them in here. And your experimental result then is the trapping rate, kappa d. And this is proportional to the defect concentration. To calculate it, you need to know the trapping coefficient, mu, but this is known for very many examples. And so we can really calculate defect concentrations this way. Okay, so there was a theoretical calculation of Thorsten Stab when he was with us in Halle to calculate vacancy clusters in silicon. There are some magic numbers with especially low formation energy at 6, 10, and 14 vacancies, and he calculated also the lifetime, and you can see the lifetime is increasing, but get a saturation for a large number of vacancies, and so we can calculate, we can discriminate between mono vacancies, die vacancies, and small vacancy clusters here. Okay, the second technique, which is very useful for defect studies, is Doppler broadening. I talked about angular correlation already and positron lifetime, and this is the third technique. If the electron-positron pair has a momentum in the direction of the annihilation ray, in the propagation ray of the gammas, then this leads to an increase of the energy. You will not get 511 for the annihilation line, but maybe 517 or 520 keV. And then at the same time here, the other ray has smaller energy, maybe 507 or something like this. And you can easily measure it by a very simple setup. This is just germanium detector in a standard setup. And you can just measure this 511 line with a high resolution. And you can see a difference if you have a reference samples without defects. Here it's gallium arsenide. Or when you have plastically deformed gallium arsenide, again, you have open volume defects. And then this inner part is higher. And the reason for this is when you have more annihilation at valence electrons, that means in defects, in open volume defects, where the core atoms are missing, you have only valence electrons for annihilation, then this inner part is higher because the momentum of this valence electrons is small. And if you make a normalized plot, you can see that there is some increase. And you can define some line shape parameters like S, which is this fraction, this red fraction divided by the whole curve, with the whole area, or in the wing parameter, you have this W parameter. And with these parameters, you can also tell something about defect concentrations. And actually, the background is rather high. So was the idea, I think, of Kelvin Lin in US to take two detectors and measure energy of both. And this really reduces the background quite a lot. So here you have an example. This is the normal spectrum. This is the other one. But if you measure one detector as a function of the others, you get this spectrum. And you can see here in the end, the background is very low. So it's orders of magnitude smaller here. And this gives you very beautiful spectra. And if you look sharply, you can really see here that the resolution is also better. So it's a much better spectrum. And and this has a chemical sensitivity. As you can see here, we measured different elements and plotted it as a ratio to defect-free gallium arsenide. And you can see there's a clear difference for all the elements. And if you have a vacancy, say tellurium vacancy, and you have in gallium arsenide, you have a, say, gallium vacancy. And if you have a tellurium atom directly at the site, you can see it. I do not have the time to show everything about this, but you can look to this paper. There's a good example for this study. You can really discriminate whether you have a silicon or tellurium atom at the site, in direct vicinity of the vacancy. Okay, so 2 examples. Once again, the thermally stabilized vacancies in thermal equilibrium in aluminum here, for instance. You can see for the average lifetime, the red curve here. It has a small increase first, and this is thermal expansion of the lattice only. But then it increases further. And this means that you have positron trapping into thermal vacancies. And yeah, you can see the lifetime. So it's 242 picoseconds. So this is just a mono vacancy. Yeah. And so you can then make a plot, a Arrhenius plot. You calculate the trapping rate, which is the measure for the amount of trapping, and you plot it versus 1 over temperature, and then you can get this EF, which is not Fermi energy. This is formation energy of vacancies. You can calculate formation energy of vacancies. And an old result was here from 1972, this one. And nowadays, the techniques are more sophisticated, and we can get it with much higher accuracy now. You may ask why this is interesting. It is interesting for metal physics. All the simulations which are nowadays done for alloys, for precipitations, and so on, they need this formation energy of vacancies and also migration energy. So how to measure migration energy? So we have to quench in vacancies, and from this, and then we have to anneal them. So here in that case, the samples were heated 2 hours at high temperatures, and where the concentration of thermal energies is high, then we quench it to minus 110 degree. To quench it to room temperature water will not help, because then the vacancies are already movable, so it's no chance to measure them. So we have to find a liquid which is colder. And we tried a lot of things, so salt solutions and whatever, but finally it was very simple. We just take ethanol. Melting point is low enough that it's minus 117, I think, degrees centigrade. So we can cool it down easily by liquid nitrogen. Just give some nitrogen through that that bottle here, and then you can quench in samples just from the furnace. You put them in here, and then you quench in the vacancies. So the problem is not the quenching. The problem is to put them into the cryostat without intermediate warming up. This is not so easy. Here you can see the positron source, 2 samples. They were then put together and form a sandwich with a source in the middle, that all positrons coming out here really hit the sample. Put it in the cryostat, which is already cold. Liquid nitrogen is already going through, and then you can put it to the sample holder and measure it. And you can see it here, it's here inside. And then this is a lifetime spectrometer. And you can put it in without intermediate warming up, which is very important. Then you can really see that the vacancies are still there. And then you can start to anneal them. And when you make here some isochronal annealing, you can easily get then the migration energy which we did. But I do not have the time to show it in detail. This is just to show that the lifetime spectrum, again, we got 242 picoseconds, so a very good result, because we really know that this is just a mono vacancy, not a vacancy cluster or double vacancy or whatever. No, it's just a mono vacancy, and this anneals out then when you make the annealing experiment up to 350 K. And you see that, I'm sorry, you see it's not really the bulk value that was seen here also. there is some remaining trapping, but this is probably, or is surely, it's by dislocations, because if you put the vacancy, the sample here in liquid nitrogen, so in this very soft material, this pure aluminum, then you get the formation of dislocations, which are seen here, and they anneal out, but at higher temperatures. So last thing is vacancies in semiconductors. So in the metal, the charge of a vacancy is effectively screened by free electrons. So like, though they are neutral. In semiconductors, it's not true, because we do not have enough free electrons for this. So they can have a negative charge, and that means they are, of course, better trapped. So the trapping is increased. Sorry. Or they can have a positive charge. And then we have here some potential ball which has to be overcome for trapping. But it's so high that at thermal energies, they cannot go inside. So that means we will not see positive positrons, vacancies by positrons. We can just see neutral or negative charged vacancies. And so this is sensitivity range here. I'm sorry. As a function of vacancy concentration, and you can see positive vacancies are probably not seen, but neutral are of course well visible, and we have higher sensitivity for negative or double negative vacancies. So it starts at about 10 to minus 7 per atom, which is very sensitive, and it ends up here at about 10 to minus 3. So this is close to the concentration of vacancies in metals at the melting point. So you can still see the vacancies, but you cannot calculate the calculations, because all positrons are trapped. We call this saturation trapping. So in that case, you can just see the positrons, but you cannot see them, but you cannot calculate the concentration anymore. There's another possibility using a positron beam where you can still measure the concentration here, but they do not have the time to explain this. This is an example, and this was defects in electron irradiated germanium. So we made electron irradiation at 2 MeV and energy at 4 Kelvin in Jülich actually, and this it uses just mono vacancies, no di vacancies, just mono vacancies very clearly, and to have vacancy in the interstitial pairs, and you see this very steep annealing stage. So when you anneal the sample, you can really see the vacancies disappear. And up to 10 to 18 irradiation dose, this is the same for all doses. But if you have enough vacancies, 10 to 19 irradiation dose, and actually this is introduction rate of about 1. So we have 10 to 19 vacancies. Then they are enough to find each other, and they start moving, and they form di vacancies, and they are more stable. Up to 400 Kelvin. This is the same in silicon. Silicon, they are stable up to 500 Kelvin. So you can see the day anneal later. By the way, you will see many more examples for semiconductors in the next talk of my friend Akira Uedono. So this is my last slide. Positron annihilation spectroscopy. So we have many applications, not only what I said, bulk defects in semiconductors and metals, alloys, and so on. We can also study near surface defects in thin layers, and this will be a topic of Andreas Wagner in a talk which comes still today. So we can look for defect depth profiles near the surface after ion implantation and so on. And we can measure epitaxial layers, growth defects and bismuth defects and so on. This is a very important field of positron annihilation nowadays. And we can also study soft matter physics, open volume polymers in the diffusion and so things. And we can measure small pores between 1 and 100 nanometer by positrons. And this uses positronium, actually, positronium spectroscopy. And this is subject of the talk of Radek still today. Nowadays, we have very intense positron sources using pair production. So Andreas Wagner will give today examples for this. We can now measure fast kinetics, so precipitation processes, for instance, or defect annealing, diffusion, and so on. So we can measure spectra in a couple of seconds nowadays, and there are even more applications for positrons. So thank you for your attention, and maybe there are questions.
The presentation is now open for questions from the audience and also online participants.
So obviously everything is clear. I'm happy about this. Okay. So thank you very much.
Morning, Reinhard. This is Pradeep here.
Yeah, Radek.
One question, I've forgotten maybe. So what is the signature and of this positively charged vacancy? And
Yeah.
any way to identify, we know that positron is not getting trapped, but is there any way to get a sense of it, in the sense it is
Actually, yeah, I understand your question. If you have positively charged vacancies and their concentration is not very high, then you have this. Okay, let me check whether I can find it again. Then you have this repelling potential here. And this is really much higher than the thermal energy. Positrons will not go in. You have no chance to see it. It may be different if your concentration of the vacancies is high. So that the next vacancy is here, say here. So that means you will not, it will not, the positrons will start from that level, and then they go into the positively charged vacancies. But then the concentration must be close to saturation level. So, but for normal concentrations, say up to 10 to 18 per cubic centimeter, there's no chance to see that. But what you can do is you can change the charge by light. And you can not only change the, you can only not only see the vacancies there, then you can also find their their position in the band gap. And that is, of course, an interesting thing, and that has been done by several authors. The Finnish group is famous for that, and that you can and the same you can do for neutral and negatively charged vacancies. You can simply change the charge by illuminating the sample by monoenergetic light, and you can change this energy to see where this change happens. Then you have the position in the band gap.
Thank you. Thank you.
If there are no more questions, let us thank Dr. Krause-Reber for an extremely nice presentation.
Thank you very much.
Now move on to the next presentation by Dr. Uedono from University of Tsukuba, Japan, and the lecture title is Open Spaces and Vacancy Type Defects in Solid State Materials Probed by Means of Positron Annihilation. Dr. Uedono, please.
I started the mic. Can you hear me?
You have 30 minutes, so we'll have maybe a few minutes for the discussion at the end, maybe 2 to 3 minutes. You can complete in 27 minutes, please.
Yeah, thank you very much. Can you hear me? Good. Now let me share my screen. The sharing screen was prohibited, I suppose. So only the chairperson can give me the right. Nope, not yet. Okay. It seems to be okay. Wait a moment. Where is it? This one?
At the bottom of your screen. Yeah.
And here. Maybe I made mistake. Sorry. Let me. Where is the screen? Okay, okay. I think I made a mistake. Wait a moment.
We are able to see your screen, sir. You show the slides.
Yeah, wait a moment. I think I made a mistake. Let me try again. Oops. Sharing the screen again. Where's my screen? Actually, though, that's not my screen. Maybe no. There is some difficulty here, so wait a moment. I changed my mind. Yep. And this one. And this one. Yep. How about this?
We are able to see your screen,
Yes,
sir.
yes.
Kindly continue with the presentation.
Good. Thank you very much. So, thank you very much for introduction, and I would like to thank organizing committee for giving me a chance to present our recent data here. So, my talk. Let me start from the motivation of my talk, why we are interested in open space and vacancies in gallium nitride device-related materials. Then I'll talk about a study of vacancies in ion-implanted gallium nitride, and also I will talk about open spaces in thin L2O3 alumina films deposited on gallium nitride substrate. Then I'll make brief summary. But first, let me start from what is power semiconductor device. Why we are so much interested in the semiconductor device, especially power semiconductor device. The power semiconductor device is a switch, just a switch to control the current flow. It's just a switch. So let me show you the one example of how switch can convert the DC to AC. So this is a switch, and this is a DC battery. And with switch, you can change the DC to AC. And this is a waveform. And the same thing can be done by two transistors, like this. Well, if you are not so happy about this shape, this looks like digital 1 and 0, not looks like sine curve, then I could introduce pulse width modulation. In this case, you can see that the pulse width is modulated. Then if you take an average of the voltage, now the wave started to look like sine wave. So this is DC-AC conversion by switch. So what is the ideal power switch? Obviously, no voltage drop in the on state and no current passing in the off state, of course. But there's another demand that can be operated at any temperature, any atmosphere, and high frequency. Obviously, frequency recently required is 100 gigahertz. So 100 gigahertz, you cannot use this kind of switch. So that is why we need power semiconductor devices. Now, let's look at the material for power device. So in this case, please look at figure of merit. If the silicon used as a power device, the figure of merit is 1. Now, in the case of SiC, the figure of merit is 700 and gallium nitride 3000. Obviously, gallium nitride is very much good, very good material as power semiconductor. So, gallium nitride device can be used for high frequency and high power device. And its applications are, for example, DC-AC or DC-DC conversion for solar system, or electric vehicle and airplane. These are the motors can be controlled by gallium nitride power device, and wireless charging system. Yes, that is almost already available, and 5G or 6G architectures. And also that can be used for LiDAR, laser imaging detection and ranging technology for cars or airplanes. And of course, there's a lot of medical technology application. So recently, we observed a strong increase in the gallium nitride device market. Up to 2026, it's expected to be increased plus 70%. Major driver are the consumer products and also automotive and telecom and datacom. So it seems that the future of gallium nitride is bright, but there is one big problem. That is ion implantation. Well, you probably know that the success of silicon-based devices depend on the availability of ion implantation. Using ion implantation, you can implant impurities to a limited area with desired density. But unfortunately, fabrication of especially P-type gallium nitride using ion implantation is very, very difficult. Very difficult. Nobody successfully fabricate P-type gallium nitride by using ion implantation, say several years ago. But also techniques for achieving acceptors, that is actually magnesium, Mg, is not mature. Successful fabrication of the P-type device has started to appear from 2015. So a study of annealing behavior point defects in ion implanted gallium nitride is definitely important to utilize the ion implantation technique for gallium nitride device. That is why we study the ion implantation to gallium nitride by using Positron Annihilation. Now let me start from the first example, the vacancies in ion implanted gallium nitride. So in this case, magnesium ions are implanted into gallium nitride substrate at the 10 kiloelectron volt, relatively low energy and relatively low doses. Then samples were annealed at up to 1300 degrees C in Nth atmosphere. And here you can see the Mg magnesium concentration as a function of the depth. And obviously, this region is due to the channeling effect of magnesium. But the major implantation depths are around here. And however, after 1300 degrees C annealing, we observed a strong increase of magnesium here. So this is a distortion of magnesium profile. So that is a big problem. And also, even at 1300 degrees C, we observed no activation of magnesium in this case, no activation. So that is useless. However, if we implant nitrogen ions after the implantation of magnesium, looks like this, then we observe the large, strong difference of the magnesium profile. Obviously, the magnesium diffusion to the bulk was suppressed. But here you can see the very strange flat region of magnesium. And in this case, we observed the activation of magnesium in this case. So here is you can see the number of acceptor as a function of the depth. And in the case of the nitrogen sequential implantation, we observed the activation of magnesium. However, without the sequential nitrogen implantation, we observed no activation of magnesium. So that is a big problem. And in order to understand why this kind of things happen, we use the Positron Annihilation. Now, here you can see the S parameter that was explained by Professor Claude-Riebel as a function of positron energy. And the corresponding mean implantation depth of positron is shown here. The S parameter for defect-free gallium nitride is here. So increase of S parameter around here is due to the trapping of positron by vacancies introduced by nitrogen implantation. Again, in this case, there's no implantation of magnesium. This is only nitrogen implantation. Then after getting the S parameter energy curve, we can analyze the S parameter energy curve to get the depth distribution of S parameter like this. From this data, we see that the defects introduced up to, say, 600 nanometer, and this is defect profile. Now, after 1300 degrees C, we observe the increased S parameter. With annealing, annealing is supposed to decrease the defects, but unfortunately, in this case, S parameter increased, suggesting the introduction of vacancy cluster. And the S parameter depth profile looks like this. Well, S parameter going up after 1300 degrees C. Now let's compare between the magnesium profile and defect profile after 1300 degrees C annealing. Here you can see the large S parameter gap observed at 200 nanometer. And you can see the strange flat region of magnesium ends 200 nanometer. So naturally, we can conclude that the diffusion of magnesium was suppressed by the trapping of magnesium by residual vacancies, even after 1300 degrees C annealing. So that is one of the conclusion. Now let's check out the defect species introduced by nitrogen implantation. In this case, we use the so-called SW plot. So this is a very simple technique to identify the species of vacancy type defects. Let me explain. If positron is trapped by, 100% positron is trapped by vacancy type defects, we can get characteristic S and W parameters. If positron annihilated from defect-free, then we can get defect-free S parameter and W parameter. In the SW plot, defect-free S parameter and W parameter here, and if concentration defects high enough, then we can get characteristic S and W parameter here. And if defect concentration increases like this, then SW value goes like this. And after the experiment, if I get the SW value here, I can estimate or identify the species of vacancy type defects, and also I can estimate the concentration of the defects. And if I am not so lucky, SW value is here, I have to assume another type of defect. That is the SW plot. Now, here you can see the simulated SW value for gallium nitride. This is the simulation results. This is defect-free SW value, and this is a gallium vacancy SW value. If I put one nitrogen vacancy here, SW value is here, and if I put two nitrogen vacancy, two gallium vacancy, then SW value here, three nitrogen vacancy, and four nitrogen vacancy here. Please remember that the SW value goes to the right-hand side if I increase the number of nitrogen vacancy coupled with gallium vacancy. Now, let me show you the SW value obtained by experiments. Here you can see the defect-free gallium nitride here, and this is as implanted SW value. So this difference is due to the difference between the simulation and experiments, where I could say error. And considering the difference between simulation and experiments, because as implanted SW value is here, so I can conclude that for as implanted sample, the major defect species was divacancy. Well, it could be gallium vacancy only, or it could be gallium vacancy coupled with two nitrogen vacancy, comparing to the thinking about the error between theory and experiment, but definitely not gallium vacancy coupled with for nitrogen vacancy. That's what I want to say. Now, this is SW value for after the annealing experiments. This is as implanted sample and 1000 degrees C and 1100 degrees C annealing. So if I make a straight line that connecting defect-free 110, 110 and 1100 degrees C annealing SW value, then the line can hit the vacancy cluster, like gallium vacancy 3 and nitrogen vacancy 3. This is a model used in the computer simulation for gallium vacancy 3 and nitrogen vacancy 3. This gray ball represents nitrogen, and this green one is gallium, and this yellow cloud is a positron density. So this is relatively large vacancy cluster. Now, after 1200 degrees C annealing, SW value here, and 1300 degrees C, SW value here. Very interestingly, SW value tend to go back to the as implanted sample. This behavior is very much different from the behavior of SW value for Mg only implanted gallium nitride. In the case of magnesium implanted gallium nitride, the as implanted sample here, the vacancy, then go to the SW value here after 10,000 degrees annealing, and the straight line hit the vacancy cluster. The same situation. However, after 1100 degrees annealing, SW value straight go to the defect-free value, and those values are found on the line here. So this means that no change of defect species occurred after 10,100 degrees C annealing. Now, let me explain why this kind of difference occurred. Here you can see the gallium nitride matrix, and if I could put the magnesium at the gallium site, that is a successful activation of magnesium. However, unfortunately, after 1100 degrees C annealing, what we observed is a vacancy cluster, a lot of vacancy clusters. Then, after higher temperature annealing, for example, 1300 degrees C annealing, I might be able to use 2 gallium atoms and 2 nitrogen atoms intershell site, and also magnesium ions. So these intershells could be trapped by vacancy cluster, and in this case, magnesium would go to the gallium site, but unfortunately, what I get is a magnesium-nitrogen pairs. It does not act an acceptor, however. Therefore, in the case of nitrogen implanted sample, because that is a nitrogen implantation, I can use additional nitrogen atom. So in this case, of course, we can get the magnesium located at the gallium site without nitrogen vacancy. So that is what I observed. So the difference between magnesium only implanted sample and the nitrogen implanted sample can be attributed to the recombination between nitrogen vacancy and excess nitrogen atoms in the damaged region. So actually, that can be observed for the S parameter depth curve for Mg plus nitrogen implanted gallium nitride. After annealing, 1300 degrees C annealing, the S parameter goes like this. The surface S parameter goes down. Well, this is not due to the annealing out of vacancy type defects in the subsurface region. This is due to the partial activation of magnesium and the resultant downward shift of the Fermi level position. The decrease in the Fermi level position causes the transfer of the charge state of vacancies from neutral to positive. So as I as Professor Klaus-Lieberg mentioned, in this case, vacancy type defects going to positive, and the positively charged defect cannot be trapped by positron annihilation. But in order to answer the question, well, positively charged defect can be activated by helium-cadmium laser illumination. Well, this is another experiment, but if we implant the magnesium, for example, 10 to the power 17th, S parameter relatively low, but after the illumination above the light energy, say 2.5 electron volt, S parameter goes up. So this is due to the trapping of excess electron produced by illumination by positively charged defect. Then we can get the information of positively charged defect. Now, nitrogen sequential implantation. Are we happy now? Well, unfortunately, no, because we found several side effects. Nitrogen implantation, additional nitrogen implantation naturally introduce additional defects, and they react under the imbalance condition between gallium vacancy and nitrogen vacancy. And also we found that the acceleration of magnesium precipitation by nitrogen sequential implantation. And the other issue we need to consider is hydrogen. Hydrogen is always in the gallium nitride, so we have to think about MGH or MGH-VN complexes. So we are now working on them using not only Positron annihilation, photoluminescence, cathode luminescence, scanning TEM, 3D atom probe tomography, and computer simulation of magnesium in gallium nitride. I'm collaborating with AIST, NIMS, Nagoya University, Tokyo University, etc., etc. Well, that is another story. So today I would try to change my topic to the open space in L03 film. This is, you can, typical gallium nitride device structure. For example, let me explain gallium nitride MOSFET. Here you can see the P-type gallium nitride. It should be created by ion implantation. Then yellow part is the insulator. Well, actually, the old device has an insulator. So insulator is very important for gallium nitride device. But the problem is that what kind of the insulator is suitable for gallium nitride? We need a certain barrier for electron that prevent to go to the insulator from gallium nitride here, or a certain barrier for holes. So in the case of SiN or gallium 203, those barriers too small. And helium hafnium, the barrier is around 1.1 electron volt. Well, that is enough for room temperature operation, but the power device seems to operate high temperature, so this is no good. So only possibility is L03 and SL2. So in this case, I'm going to talk about L03. So in this case, L03 deposited on gallium nitride, and then sample annealed at 900 degrees C. Then we measured S parameter energy curve. For L03, thickness 25 nanometer and gallium nitride. This is S parameter, and after getting S parameter, we can get the depth distribution S parameter, and this region here or here is a Positron annihilation in L03, and this is a gallium nitride. After 800 degrees C, we observed the increase of S parameter in the gallium nitride, suggesting the introduction of vacancy type defects. And also, we observed the decrease of S parameter or decrease of S parameter for L03. Today, I'd like to talk about here. This is a positron lifetime corresponding to the positron annihilation in L03. This is as deposited sample. So these are the annealed sample, 800 degrees C, 900 degrees C. The lifetime spectra were decomposed into 3 components, tau 1, tau 2, tau 3. And each corresponding intensity is shown here, I1, I2, I3. I3 is very small, so 2% around, so we are not so interested in here. But the problem is that I1 and I2. So after annealing, tau1 value decreased from 0.26 to 0.24. And this lifetime corresponding to change of this lifetime, the relative intensity increased. So this suggests that the size of open spaces was decreased and its concentration was increased by annealing treatments. Then the question is, what kind of open space we are detecting? In this case, we use the computer simulation. We all know that the atomic layer deposited L2O3 structure is close to the gamma L2O3. So gamma L2O3 is a strange pair that is a spinel-like structure. So 8 aluminum vacancy must exist in 3 spinel unit cells to satisfy stoichiometry. So, but we do not know the position of aluminum vacancy in the unit cell, so we randomly distribute in the aluminum vacancy distribution by using inside the computer. So in this case, aluminum vacancy accidentally made a cluster. Of course, in this case, Poisson lifetime is long, 0.25 nanosecond. And in this case, aluminum vacancy distributed. So in this case, Poisson lifetime is short. So gamma L2O3, there is a certain distribution of Poisson lifetime. Now, as I said, using the Poisson experiments, the lifetime decreased from 0.26, 0.24. So in the simulation, 0.26 is here, and it can go to the 0.24. That is a very probable situation. So after the annealing, we observe the dissociation of aluminum vacancy. So such kind of information, the change in the open space size relate to the electric properties of insulator and diffusion property of impurities L2O3. So such kind of information is very important for gallium nitride devices. So let me summarize my talk. But let me talk about what positron annihilation can do. So these are the related paper, recent my related paper. We checked the dose dependence, multi-stage annealing, electro effect of capping film on defect during annealing, hot implantation, co-implantation, magnesium, hydrogen, gallium, nitrogen. And also we checked the implantation from nitrogen phase and ultra high pressure annealing and the open spaces in insulator. So 1 year ago, 2 years ago, my collaborator, Professor Amano, Nobel Prize winner, proudly announced that the highly effective activation of MEMG implanted P-type gallium nitride by ultra high pressure annealing. And the related work is here. And you can see that the author in the red letter is a Positron annihilation researcher. And the author in the blue letter is a non-Positron annihilation researchers. So I would try to say that the Positron annihilation somewhat contribute for the development of gallium nitride devices. Well, that's all. Thank you very much.
Thank you, Professor Vedono. Now the lecture is open for questions from the audience.
Dr. Wagner seems to have.
Andreas would like to ask one question.
It took some time to the thing. Yeah, thank you very much for the contribution. I have one question regarding the ion implantation. So the ion implantation had been done on site where you measured the annealing effects, or did you have to transport over some time?
Well, ion implantation was done by ion implantation company. Then the sample was transferred to the Tsukuba University.
And for the lifetime measurements also, or did this was happen in Munich?
Well, today I didn't talk about lifetime measurements for ion implanted sample, but the lifetime measurement for L2O3 was done by Munich.
Okay. Thank you.
Any further questions?
Yeah, Ijikar, there is one question. Please go ahead with your question from Ijikar. I think if it is not there, then we thank Professor Vedono for his very informative presentation.
Thank you very much.
Thank you, Professor. Now we go to the next lecture by Professor B.S. Tomar. He's a professor at Homi Bhabha National Institute, Nagar, India. And his title of his presentation is TDPSC, a nuclear probe for microstructure studies in material science. Professor Tomar.
Very good morning, all. At the outset, I would like to thank the organizers for giving me this opportunity to speak on a topic of nuclear probes, in particular the technique of time differential perturbed angular correlation, which, as Professor Mahapatra pointed out during the inaugural function, we, under the guidance of Professor Satyaprakash, we developed techniques like TDPSC and positron annihilation spectroscopy in the mid-80s. And it is I feel very happy to share my experience of those developments and also some of the literature later on. So the plan of my talk will be, since this audience may not be familiar with the technique of perturbed angular correlation, I will give an introduction to this technique for the benefit of the audience. Then I will just touch about the instrumentation for the TDPSC technique, and then also give the list of nuclear probes which are used in TDPSC technique, and then touch upon some of the applications of TDPSC in material science. So the subject of angular correlation is at the interface between the nuclear chemistry and the solid state chemistry, I would say. So in nuclear chemistry section, the majority of the people were working on nuclear fission, nuclear reactions in 70s and 80s. And at that time in 80s, Professor Satyaprakash encouraged us to pan out, to take up new problems. And one of the very interesting aspects was the chemical effects of nuclear transformations. So how the nuclear phenomena can be influenced by the chemical processes that is happening in the sample, and how we can obtain the information about the chemical phenomena using the nuclear techniques. So that was how the nuclear probes came into being. And so the subject of perturbed angular correlation essentially starts from the basic nuclear physics of angular correlation. The angular correlation essentially means that if there are two gamma rays or any two radiations, alpha beta or beta gamma, any two radiations which are in cascade, emitted one after the other, they are in cascade. So the nuclear decay follow certain conservation laws, conservation of angular momentum being one of them. So let us focus on the case of a gamma-gamma cascade. So after the alpha decay or beta decay, we populate the nucleus in its excited state, II. II is the spin, and which emits a gamma ray of multipolarity L1 to an intermediate state having spin I, which in turn emits another gamma ray having multipolarity L2. L1, L2 are essentially the electric or magnetic characters of the nucleus. And then, so I'll talk about Q and tau later on. So this conservation of angular momentum between the two radiations in cascade essentially gives an angular correlation between the two radiations. So if we do an angular correlation measurement between these two gamma ray, essentially what we are doing, we are measuring the coincidence between these two gamma rays as a function of the angle between the two detectors. That is what we call as the W theta. So if you measure the coincidence counts, then this follows a distribution like this, AKK, PK cos theta, where AKK, K actually is the sort of a coefficient, like, we have this 0, 2, 4, like that, subscript, the order of the correlation, and PK cos theta is the legendary polynomial. So this AKK are essentially the directional correlation, correlation coefficients, and they can be calculated if we know the spins and multipolarity of gamma ray. Then from the Clefts-Gordon coefficient or 3G symbols of the gamma rays and the levels, we can calculate exactly the AKK coefficients. In other words, you can actually, this AKK essentially represents the anisotropy of the angular correlation. So what I have shown here, that if you vary the detector angle between two detectors from 90 to 180 degree, then the coincidence counts at 90 and 180 are different. So it changes. And so we can say that W180 minus W90 is called the anisotropy of the angular correlation. Now, what happens from the PSE, angular correlation, how we go to TDPSE? So if the gamma-gamma cascade has got certain characteristics like, the intermediate state has got a finite quadrupole moment. And those nuclei which have got a spin, one or more than one, will have a measurable quadrupole moment. So this is the electric quadrupole moment of the nucleus. Then this is one condition, that nucleus should have a finite quadrupole moment. And secondly is that the intermediate level should have a lifetime of a few nanoseconds. With these two conditions, what happens? After the first gamma ray is emitted, the intermediate state is populated in certain magnetic substates of that level. For example, if it is 5/2, intermediate level 5/2, then all the sublevels of that 5/2 are not equally populated. But then, and that is why this angular correlation arises. The second gamma emitted from nucleus oriented in space in different directions. If there is a interaction between the quadrupole moment and the surrounding electric field gradient, then this population of magnetic sublevels get altered, and so we say angular correlation has been perturbed. So the perturbation of the angular correlation arises because of the interaction of the nuclear quadrupole moment with the surrounding electric field gradient. It can also arise from the interaction between the magnetic dipole moment of the nucleus in that state with the surrounding magnetic field. It could be applied magnetic field, or it could be a hyperfine field generated by the structure like ferromagnetics or antiferromagnetic substance. So that this perturbation leads to a factor called GK that we call as the perturbation factor. Now, if you can expand this series, so you will find that because of this electric quadrupole interaction, the odd terms will vanish, and you have the 0th order term, A22, G22, second order, and 4th order terms. And later on, for the sake of convenience, you can also neglect the 4th order term. Though the 4th order term does have a significant magnitude. So that is the basic principle of the perturbed angular correlation. Now, why this perturbed angular correlation technique did not become very, very popular either to the solid state chemistry people or the nuclear chemistry people because of certain limitations. One of the limitations is that we do not have a standard equipment available in the market. Like, for like MOSPOWER or NMR, you have standard equipments where here you have to set up a fast slow coincidence setup to do the experiments. And so, in fact, this is the flow sheet for that TDP setup, where we have this 1.5 inch by 1.5 inch sodium iodide crystals, 2 crystals, couple them optically to the PMT. So you cannot even have standard sodium iodide thallium detector from market. You have to buy the crystal, couple optically with the PMT, make the bridge circuit, and then use it for the TDP experiment. Then you take the signals from anode and the dinode. Anode actually is DC coupled. So you apply a negative voltage to the cathode, and so anode is grounded. And you take the timing signal from the anode, because if you make AC coupled, the signal becomes very slow. So after this anode goes to timing, so the constant fraction discriminator gets the timing signal from both these sides, and then you between there is a start signal and stop signal. The time to amplitude converter converts the time gap between this start and stop into a voltage signal. That's called the TSC. And the energy getting gamma 1, gamma 2 you are getting through the slow part. So you have an amplifier, then you get the gamma rays in this, and then fast coincidence, and then this will strobe the TSC. So essentially the output of this is the TSC spectrum, which is the exponential decay, delayed gamma coincidence spectrum. And that essentially gives you the lifetime of that intermediate level, which may be of few nanoseconds. Now, this exponential decay of the intermediate level will see oscillations because of the interaction of electric field gradient with the quadrupole moment. That is why if you see the exponential decay, because of the perturbation of angular correlation function, you will see oscillations, and by two angle data, you can determine this G22 attenuation factor as a function of time, and that G22 function versus time is essentially giving you the oscillatory behavior of the angular correlation function. And if you take a Fourier transform of this G22 part, then you get the frequency of the quadrupole interaction. This is called the Haber-Fine interaction frequencies. So this in nutshell is a brief introduction to the TDPAC setup. So essential idea is to obtain the quadrupole interaction frequency, which I will give you a little more details in subsequently. So this G22 essentially, the attenuation factor is arising because of the quadrupole interaction between quadrupole moment and the electric field gradient, and it can be written in terms of this Sk S2n cos omega nt, where omegas are the frequencies of the transitions in the magnetic states, which I will explain subsequently. Yeah. So when we come to TDPAC, I try to give you explain using this particular decay scheme. One of the most widely used nuclear probes for TDPAC is the hafnium-181, which is having a half-life of 42 days and emits beta minus to the excited states of tantalum-181. This excited state half plus spin and parity emits a gamma ray of 133 keV to an intermediate state which has got the half-life of 10.8 nanoseconds and has got a quadrupole moment because spin is more than 1, so it's 5/2, and then emits a gamma ray 482 keV to ground state. Now, because of the interaction between the electric quadrupole moment of this nucleus and the surrounding electric field gradient, this intermediate level splits into its sublevels, plus minus half, 3/2, 5/2, and the transitions between among these will give you the frequencies omega 1, omega 2, omega 3. So for now, this electric field gradient could be symmetric axially or asymmetric. So for axially symmetric electric field gradient, we get this omega, the quadrupole interaction frequency as 6 EQ VZZ. Q is the quadrupole moment, EZZ is the electrical gradient, and I the spin. And the electrical gradient is nothing but the second derivative of the potential gradient at that time around the nucleus. And the asymmetry of field gradient is Vxx minus Vy by Vzz. So gradient along the x, y, and z direction, instead of 3 parameters, we define 2 parameters, Vzz and eta. So now, essentially, how to get these coefficients, Skn coefficients? If you set up the Schrodinger equation for the interaction between Q and Vzz and solve this equation, you will get the eigenvalues as omegas and the amplitudes. This one will be the matrix which will diagonalize that matrix. They will give you the amplitude Skn coefficient. So that is how the data of the coefficients of this TDPSC can be obtained. So this in nutshell gives you the principle of the TDPSC technique. So nowadays, the standard programs are available like DPAC to analyze the TDPSC data. But in the beginning, you have to, it's better that you learn the basics of the technique. Now the most important part becomes, when you analyze, when you get the data, how reliable is your data? So that nuclear instrumentation becomes very important. And I was mentioning, I showed you a schematic which was in the 80s. And now we have colleagues have very sophisticated equipment where you have this now better resolution than sodium iodide thallium, lanthanum bromide, cerium dope detectors. And instead of 2 detectors, you can have 3. So at a time, you get both W90 and W180. And now you have this, the signal processing also become different. Instead of getting the gamma ray in each channel, you can have all the signals going to the logic signal. So you have that fast timing, energy signals. So you have, and this timing will generate tag will give you a timing signal, and you can have the OR gate between 2 channels. So you get either 1, 2 or 1, 3, and 3 energy signals you can put in a list mode. So all data goes to list mode, and which you can select separately later on. So this fast slow coincidence setup is used to generate the TDPSC spectra. Essentially, what we are getting out of this time spectra because of the coincidence between the 2 gamma rays, 133 in 1 detector and 482 in the 2 detectors. So you get W theta, W90 and W180, and then you can analyze to get the TDPSC spectrum. In fact, I'm told that now, in fact, even the amplifiers have been done away with. So you have the signal processing so fast. From the preamplifier directly, you can feed the data signals to the data acquisition system by digital signal processing. Okay. So how do I pick up a nucleus? Whether I can, suppose I'm interested in particular ML element, can we have a suitable probe? Because I may be interested in chemistry of a particular element. So if we know the characteristics of a nucleus to be used as a PSC probe, then it will be easy to select the nucleus. So it should have a half-life relatively long, maybe few hours to few days. The intermediate level spin, that I1, I2, I3, the intermediate level spin should be more than half, so that it has got a measurable quadrupole moment. The nucleus can have a quadrupole moment in its ground even if its spin is 0, but we can't measure it. So to measure the quadrupole moment, it has to have spin more than half. Then the intermediate level lifetime tau should be more than about 1 nanosecond, because the instrument resolving time itself will be about 500 picosecond. So it should be more than that. The energy of the gamma radiations in cascade, the ones which you are, because the detector window may attenuate the gamma ray. So roughly 100, more than 100 keV. And of course, if you are interested in chemistry of a particular element, then the chemical compatibility with the host matrix is also important. So these are the criteria. And if you look at the nuclear chart and find out certain radioisotopes meeting these criteria, then you have a nuclear probe, and you can study the chemistry of that element. In fact, many a times, you can just dope this probe, which you will substitute the lattice of the other material, and then you can study the particular matrix. So these are the probes, nuclear probes for TDPSC. certain part is not visible here. So you can see here you have the probes, the half-life, the decay mode, the lifetime of the isomeric, the ground, this is the daughter product, the lifetime of the intermediate state in nanoseconds, first gamma and second gamma, and their abundances. So you can see zinc, molybdenum, cadmium, indium, silver, barium, terbium, hafnium, mercury, lead, and so on. So you have a range of radioisotopes that you can use in PSC. So depending upon the sample that you are interested in, you can choose a suitable probe nucleus and dope it, or you can generate. So I will discuss how to produce different, how to dope the probe in the matrix. Yeah. So how to introduce the probe? See, the probe is radioactive. So if you are studying a sample which may be inactive, so how to introduce a radioactive probe and it goes in the lattice position. So one is that you irradiate. Suppose you have a sample, which like for example hafnium oxide you are studying. You irradiate hafnium oxide to give hafnium 181, and then you can study hafnium compounds directly. If you are using zirconium compound, you can dope hafnium and irradiate because zirconium has got very low cross section for neutrons. Or you can diffuse. So you can heat, you can put a drop of a liquid containing the probe atom, inactive atom, and then diffuse in this one, or you can even put a drop of radioactive liquid and diffuse it. And then now, of course, the radioactive ion beam has become very, very useful technique. In fact, it is going to expand the scope of TDPSC. I've discussed a little more details. So you don't have to, in fact, have the two gamma rays in cascade. Even one gamma ray will do, because the probe, the beam will become a start signal. In fact, Isolde CERN has started a program on TDPSC using the radioactive ion beams also. So both radioactive ion beam and nuclear reactions are being used for ion implantation. You can of course do the chemistry. You can even precipitate a compound by sol gel route. You can prepare, or you can in growth. You can grow. Suppose you are growing crystal, you can put the radioactive probe atom. And the concentrations of the probe atoms may be very, very low. If it is a carrier free, then even 10 power 10 atoms are sufficient. Now, so as I was mentioning about Isolde CERN, another technique called time differential perturbed angular distribution instead of angular correlation, TDPA-D is based on in situ production of probe atoms by nuclear reaction, where the beam, like you are using proton beam to produce radioisotope, proton acts as a start signal, and the gamma ray as a stop signal. So this will widen the scope of the TDPSC. Like I have given an example here. You want to study the TDPSC of lanthanum 135, you produce this by boron 11 tellurium 128 4N, and this excited state of at this energy has got 31 nanosecond. So lanthanum compounds you can study, you can actually prepare this and you can implant this in lanthanum compound and study the TDPSC using this. So TDPA-D in fact will cover a large number of elements in the periodic table, and that is how you can widen the scope of this technique. So what information we get from the TDPSC? As I mentioned, you get the electric field gradient, which we define in terms of the VZZ, the Z component of electric field gradient, and the asymmetry of electric field gradient. And it essentially tells you about the local structure. So around the probe atom, in the immediate vicinity.
Tomar, you have another 5 minutes.
Yeah. So in the immediate vicinity, how we can get information about the local structure? If you have a magnetic material, you can study magnetic field around the probe atom. And there are some relaxation phenomena like diffusion. You can even study the diffusion coefficient. So the microstructure of these materials in the immediate vicinity, you can study by TDPSC technique. So I will give you a little more details in the next one. Yeah. So the applications of the PSC essentially include the phase transitions you can study, the diffusion in solids one can study, radiation effects on solids we can study, and metal ion complexes also. So just give you some of the examples of this. So I have taken from literature some of the examples of phase transition probing on an atomic scale. This is published in Physical Review 2020. TDPSC studies on alpha to beta phase transition in multiferroic bismuth ferrite. So this multiferroics have, they say, a combination of ferromagnetic and ferroelectric properties. So this has got the Curie temperature of 825 degree and Niels temperature 370 degree. So this group have implanted cadmium 111 into this BFO and studied the TDPSC at different temperatures. So above and below the Curie temperature, and you can see here there is a change in the TDPSC pattern when you go below the Curie temperature, and then it is, of course, X-ray can reveal the changes. So rhombohedral undergoes fast transition to orthorhombic BFO at 825, which is confirmed by XRD. But it will tell you the electric field gradient around the probe atom. So the quadrupole interaction frequency, which we write in terms of megahertz per second, you can convert to megahertz by dividing by 2 pi. So from 6-fold to 2-fold coordination was detected by TDPS. So local changes around the probe nuclei can be studied using this one. Similarly, there is another study in AIP advances, effect of external magnetic field on hyperfine parameters in gadolinium oxide nanoparticles. So they have used one-on-one indium as a probe, and they found the TDPSC data analysis showed that there are two sites. So the indium sits in two sites. One is axially symmetric and one is axially asymmetric. The eta parameter 0.1111. So you can see here 25% are occupying the symmetric site and 70% on the asymmetric. So what they found that the magnetic hyperfine field is almost zero when the probe is occupying symmetric side, but it is very high, 4 Tesla, when it is occupying the asymmetric side. So this kind of information one can get about the hyperfine fields using the TDPSC data. Similarly, there is a very interesting article appeared in Physical Review Letters way back in 1996 about the what we call as the 2D spin frustrated CuFeF2. So what they have is that this CuFeF2 is a 2D triangular antiferromagnet where the magnetic layers are separated from each other by 2 oxide layers, oxygen layers, and 1 copper layer. So, and they are not one over the other. So they get frustrated because they are not able to align themselves. So the powder neutron diffraction showed the 2 magnetic transitions at 16K and 11K. And so they have done the TDPSC below and above this transition temperatures using 111 indium as a probe. So what they found that the electric field gradient interaction is altered by the magnetic interaction of the crystal, and they could detect the hyperfine magnetic field as well as the electric field gradient. This is one of the very interesting study in our laboratory with VCC, Parnika Das, the high pressure induced phase transformation in the Hafnia. So this Hafnia was put under diamond anvil cell, and at different pressure like 45 GPa atmospheric pressure, significant changes were observed in the TDPSC pattern, which was analyzed to find out the quadrupole interaction frequency and the asymmetry of the electric field gradient. So one can study the effect of pressure, temperature, magnetic field, and so on. Another application was the diffusion of hydrogen in hafnium hydride. So by the diffusion, electric field gradient is changing continuously with time over a time period of few nanoseconds. So the attenuation factor, which was static oscillatory factor, gets altered by the exponential decay because of the relaxation of the electric field gradient. So this relaxation time or the decay constant is used to find out the diffusion coefficient of hydrogen in hafnium hydride. And so they found out that the activation energy of diffusion is 0.43 electron volt for hydrogen diffusion in hydrides. And you can see here as a function of temperature how the TDPSC pattern is changing. The static TDPSC pattern is becoming more and more exponential. Then you can also study radiation effects in solids. Like for example, we use the glasses for vitrification of the high level waste, and the amorphous material will give you a broad hump in the it will not give you the static interaction or of a crystalline field. But if there is a microcrystallinity because of devitrification, then it is possible that around the probe atom you may see the crystal structure. So that we tried, and up to 50 megagray it was found that there is no generation of microcrystallinity. So, but this is a negative result also is good in this sense because your glass matrix is stable to radiation up to this much dose. So this is another way of testing the stability of the glass matrix. And lastly, I could not resist the temptation of showing these results of metal ion complexation with Dr. S.K. Das way back in 1990. So very interesting aspect is that hafnium, when it complexed by EDTA, the hafnium EDTA has got different electric field gradient compared to hafnium aqua complex. And this is in the solution, not in the solid state. So we determine the integral PSE. So you can see here the anisotropy is changing as we go on adding EDTA. And after 1:1 complex is formed with EDTA, it becomes flat. So this data could be analyzed to find out the stability constant for hafnium EDTA complex. And later on, when the precipitate was made, we could determine the static interaction part. We could find out the quadrupole interaction frequency, asymmetry of electric gradient, and the distribution. So this is the this is how one can in the chemistry also we can study PSE in solution chemistry. So these are the references which I have taken for this. This is the book, very famous book by Kai Sigban. In fact, Sigban was the person who actually initiated this ESCA, electron spectroscopy for chemical analysis, and this is the Nobel Prize for this in 1981. Then the Tillman Butch has given very good review of this one, and then recently in I Sold a Son, Juliana Schell has written a paper on how this TDPAD I was mentioning. So a lot of probe nuclei one can study using TDPAD. So I would like to acknowledge Dr. Das, S.K. Das, with whom we started this PSC, Ashwani Kumar, my PhD student, Professor Parnika Das. In fact, Professor Prashant Sen from Bose Institute was, in fact, he helped in the initial part of setting up how to couple the crystal with the PMT. And Professor Vikas, electronics group of BR radiochemistry is the backbone of all our instrumentation and our collaborators from BRC. So thank you for your attention.
Thank you, Professor Tomar, for a nice presentation of TDPSC and application with several systems. The lecture is now open for questions from audience. Anybody from the online? So I have one question, Professor
Yes.
Tomar.
Yeah.
You have shown this complexation that your first major publication TDPSC in 1990.
Yes.
Where hafnium and EDTA complex you are showing. Now you are forming complex with hafnium, but that hafnium is transforming to tantalum.
Yes.
So then how it complex it changes, no? So then how you go about it?
This the after effect of beta decay of hafnium to tantalum has been studied. People have studied in solid state whether the beta decay is going to influence the TDPS. And what they found that when hafnium decays by beta minus to tantalum, tantalum is pentavalent. And so it retains the electronic configuration of whatever was in the hafnium.
Those two gamma rays you are showing.
Yeah, they are of tantalum.
They are from tantalum, no?
They are from the excited state of tantalum only.
That's right. So then, but then information you are getting about tantalum or hafnium?
Though it is the gamma ray belong to tantalum excited state, essentially the compound is hafnium. And during the transition from hafnium to tantalum, people have done the experiment study that environment remains same. The beta decay does not alter the chemical environment around tantalum.
So this time scale is so small. I think it's nanosecond you are talking about. So you don't see that. Okay, thank you.
Thank you.
Delivering this excellent presentation on TDPSC. Now the last lecture in this session is Professor Sunil Sabarwal, who is the former head of Radiation Technology Development Division BARC, and his lecture title is Application of Nuclear Beyond Power, the Untold Story. Professor Sabarwal.
Just take the PDF. Thank you, Mr. Chairman. Good afternoon, everybody. At the onset, let me thank the organizers, especially Dr. Bhardwaj, Priya, for their kind invitation to be a part of this meeting. It's always a pleasure to come back to this particular forum because our career all started from this very place. My presentation is going to be on application of nuclear beyond power, the untold story. I'm not sure how much it is going to be of use to this particular meeting. If the name of the meeting was Nuclear Stories for Industry, Medical, and other this thing, it would have been very relevant. But I'm sure all of you will find something in the lecture to see at least the kind of hard work that you do in your laboratories. Finally, how does it reach the commercial value and how broadly it is utilized. So I will start the lecture with two caveats. Number one, it is, as you see in the lecture, it is untold story. And stories we all know look very broadly. They don't look at the microscopic thing. They try to tend to give you information on a very broad scale. That's exactly what my lecture is going to do. And second thing, you will see names of some countries. So this is only to make a point. It is not to say that a particular country has done well or not done well. So it's not the question. The question is to make my story complete. I will use data from some of the countries which I could lay my hand on. And thirdly, and the most important, I am all for nuclear power. I'm a very proponent of nuclear power. So any comparisons that you see with nuclear power is again to complete my story. And there is no comparison to say, okay, nuclear power or versus other applications. So with these three caveats, let me begin my presentation. We are all very clear that atomic energy basically consists of three things: nuclear power from nuclear power stations, radiation technologies, and on top of that is national security concerns for some other countries. We will not go into that today. Let's see only the nuclear power plants and the radiation technologies. And aim of always a nuclear technology or nuclear application is to provide abundant energy, healthy life, and a very clean environment. In a smaller audience, whenever I show this particular slide, I used to ask a question. I have shown them very equally balanced, nuclear power and radiation technologies. But in actual practice, one of them, it is very heavily weighted on one scale. And most of the time, when I ask the audience, which side do you think it is very heavily weighted, I get a wrong answer. The answer I will show in the next slide is, you can also guess. This is a study which was published in 2002, it's almost 20 years ago. Economic scale of technologies in the United States. Even at that scale, when USA has more than 100 nuclear power stations, 20% of their electricity comes from nuclear power. But the contribution to economic GDP, 25% comes from nuclear power and 75% come from the applications. Look at this number, again from the United States, published in 2003. So the data was collected in 1991 and 1995. Radiation technologies contributed to $331 billion, creating 4 million jobs. compared to nuclear power, which had a sales of $90 billion and about 0.4 million job creation, which evident about 400 people working in 100 nuclear reactors will come to this figure. So you can see for yourself that there's a huge amount of nuclear applications which are there, especially in the developed countries. Now you will say that don't show us only one example. This is another example from Japan, much before Fukushima, when they had 33% of their electricity coming from nuclear power. The contribution to their GDP from nuclear power was 46%, and 54% came from radiation application. And it is 3.2% of the GDP of 494 trillion Japanese yen that came from these applications. So again, you can see that nuclear applications play a very important part, not only nuclear power. There is another example of another country which I will come towards end of my lecture, again to just show my story or conclude the lecture. Why is it so? Why these numbers look so large? What is industry today? Actually, if you look around yourself, everything is the industry today. Anything that can generate, commercial value, economic value on a large scale is industry. Whether it is, mechanics, it is ore processing, it is environment, it is whatever you take today is an industry. For example, even if you go to a hospital today and get a medical test done, they are running an industry. It is health industry. It is tour and travel industry. So around yourself, everything that is done in an organized way constitutes an industry. And in most of these industries, you will find nuclear plays some important part. And why is it so? What makes radiation and radioisotopes, which are basically used in these nuclear applications, so special? Three things. Number one, ultra high sensitivity and ease of detection. All of you know that very well, because you do such nice measurement at such low levels that you know that they are very sensitive techniques. And this forms the basis of medical diagnosis or radio tracers in industry. They are extremely highly penetrating, for example, gamma radiation or X-ray radiation. And their absorption depends upon the nature and shape of material. So this forms the basis of non-destructive testing in industry, which again is a huge industry. And finally, when you expose this material to radiation, you produce chemical or free radicals, which are extremely reactive species, and they bring about chemical or biological changes. So this forms the basis of medical treatment or radiation technology applications. So based on these three simple things related to nuclear, you have enormous amount of industrial applications. Let me go one by one. And not only I wish to emphasize the economic aspect of it, I'll also say the societal aspect of the thing that is attached with applications. Look at the first thing, zero hunger. Even in today's world, when we have the highest food production ever mankind had, 850 million people, that is 1 in 7 people in the world, still go hungry at the end of the day. And one in 5 of them is a child. Even more so with changing environment, with the climate change and other things that you hear about today. You see there are more challenges related to food which are coming day by day. Increasing population, which is expected to reach 9 billion in 2050. Achieving higher crop yield and productivity, adapting to climatic change, protecting your animals and crops, minimizing food losses. So all of them are the challenges which the food industry is facing today. And what is the role that nuclear plays in this? First one, developing more productive and resilient crop varieties, which we call as mutation breeding. Many of you must have heard about it. Controlling harmful insect. Once you have produced the agriculture, you have to protect it also during the growing phase. And finally, once you have the crop, after harvesting, how do you save it? So these are the three important things. There are two others which I will not talk today, but these three which are marked red, I am going to elaborate a bit. Looking at more better crops, more resilient crops. There are more than 3,000 mutant varieties which have been developed using radiation or using nuclear techniques. The example that I give here is about Vietnam. And again, as I said earlier, the example is just to show because I could get data regarding this particular application. That Vietnam produces about 43 million tons of rice and exports 3 million tons out of it with a revenue of 3 billion. And with the mutant variety that they have developed using radiation technologies, it is cultivated over an area of about 3.5 million hectares. So now you can see how much economic value, even if you assume that you get about 10 to 15% higher yields, how much more money comes in the hand of the farmer and how much total it contributes to a nation's economy. Getting ready for the climate change. This is an example which is from the Bangladesh. Now, because of the climate change, the sea levels are rising, there is more salinity that is occurring in the soil. So you need to develop varieties which can withstand this saline atmosphere. So in this case, the Bangladesh has developed this, which has allowed them to get about 40 to 50% land, which was otherwise waste, could be utilized for agriculture purposes. The economic value associated with this, before I come to that, this is the Indian scenario. In India also, from our nuclear agriculture division, we have about 49 varieties of different varying crops which have been developed and which are being utilized across the country. Now, how do we assess the benefit of such an application? See, one is that you can have area planted for the variety. That will tell you how much economic benefit it brings. Then percentage area of the crop in the region. Increased yield of the crop can be converted into economic value. Or enhanced quality of the crop. Sometimes you get much better crop by mutation breeding as compared to the normal crops that you had. Or reduced use of pesticides and fungicides. All these goes into making it economic value. And again, towards the end of my lecture, I will show you some more examples of this. As I said earlier, not only do you have to produce more food, you have to save it during the production stage. And one of them is to save them from the insects. So the sterile insect technique, which is birth control for the flies, is a very, very important thing which has been done by radiation technologies, that you take the male flies, irradiate them, make them sterile, and then release. And this, again, is not on a small scale or a laboratory scale. This is an exercise which is being done today on an extremely large scale. And it brings enormous economic benefits. For example, this is an example from Mexico, where they have medfly, and to eradicate that they irradiate and release this, which costs about $8 million every year to them. But the benefit is that because of this, they are able to export about $1 billion worth of fruits to United States. Another example is from Chile, where again, because of the SIT, they are able to produce export about 500 million of their fruits to United States every year. Once you have produced and saved your crops, you have to see that the post-harvest also you have to save them so that it reaches the end consumer. And you will be surprised if I tell you that about 30% of the produce that we have goes waste during the post-harvest stage. And one technique which is utilized for saving this is food irradiation. Food irradiation is one process by which you can save onion, potatoes, ginger, garlic, cereal pulses, bacteria reduction in chicken, meat, or fish, or spices, and can also be used for quarantine purposes if you wish to export them to other countries. And in certain countries, for example, Australia or United States, anything that is to be exported, especially fruits, have to be quarantined. They have to be treated by radiation. Only then you will be able to send them across. For example, from India, in cases the mangoes, which are always irradiated and then only are able to export. Food irradiation throughout the world is approaching now almost 1 million ton. And 1 million ton, if you look at it, is very minimal as compared to the total food production that you have. So in future, it is expected that food irradiation alone will be such a large money earner for radiation technologies or nuclear technologies over a period of time. So the shared experience is that more than 100 countries use radiation-based plant breeding techniques to improve food. 95 countries use almost isotopic and nuclear techniques to identify and manage their land and water resources. 65 countries used treatment of food for phytosanitary purposes. 30 countries use SIT, and you will be again surprised if I tell you that almost 3.5 billion sterile fruit flies are produced and released every week throughout the world. That means half the world population of flies is given out every week to control or save the fruits. Now, moving on from food to health. In the case of health, again, there are, especially after the pandemic, we have seen one of the most important things that we do or we have to have is sterilized medical products. Excuse me. So nuclear techniques play a very, very important part in this because of radiation sterilization of medical products. And second thing is, which is more important, is for diagnosis purposes as well as for the treatment of cancer patients. Now, again, if you look at radiation sterilized product, more than 30 million meter cube of single-use medical products across the world are treated every year. That means almost 40 to 45% of single-use medical products that you see or you come across have been treated by radiation. When you go for a blood test, the first thing that they put is a needle in or a syringe to collect the sample. It has to be sterilized. And as I said, almost 40 to 50% of the things are sterilized by radiation. More than 450 million curie of cobalt-60 across the world is put in more than 300 plus gamma radiation facilities for these purposes. It's a huge, huge number. And the treatment industry alone of radiation sterilization is US $2.5 billion. Now, coming to India, we have about 25 gamma radiation plants which are operating in the country. And 14 of them I could see are in the private sector. Some are in the government sector or in the cooperative sectors, but almost about 25 plants are there in the country. I couldn't get the total number of the material that is being treated or the economic value, but it must be huge, even in our own country also. Now, moving on to the nuclear medicine part, more than 10,000 hospitals across the world use radioisotopes for medical purposes. And 90% of these are for the diagnostic purposes. And using one radioisotope alone, technetium-99, I have written here 30 million procedures, but the number now today is close to 40 million procedures are done worldwide using one radioisotope. And half of them, again, are basically in United States. So when you now see the number that I had shown in the earlier slides, you see if you have to carry out 40 million procedures across the world, how many laboratories you will be needing, how much manpower will be needed, and if the cost of one of this is about $1,000, how much revenue it generates or how much it contributes to the economics of the industry. So as I said earlier, just one radioisotope, which is about 10,000 curie per week, is the utilization, making it about 50,000 curie of technetium-90 alone contributes to such a huge market, about $5 billion from 50,000 curie of technetium-99. In India, the scenario is that we have 293 nuclear medicine centers, 233 gamma cameras, 222 PET CTs, 3 PET MRIs, and 19 medical cyclotrons. Maybe you will hear more about it in the lecture from the RMC doctor related to this subject. Per year in our own country, we get about 1.3 lakh patients with cancer. And across the country, we only have about 580 radiotherapy centers. So even if you need them in any advanced country, if you will go, the number should be about 10 times of this to treat the patients. But even coming to the lowest standards that the UN has put, we still need something about 1,200 machines in the country. That means we still only have about half the number of machines that are needed to treat the patients on an easy basis. So these are some of the numbers that were there in the IAEA corridors from which I had made this transparency. There are more than 800,000 nuclear industry workers, more than 2 million medical radiation workers across the world. And these numbers don't appear to us. We don't ever look at them, but this is the kind of numbers which are used for the applications of nuclear sciences. Now coming to the third part of my lecture, which is related to material modifications, radiation cross-linking, which my colleague Dr. Bhardwaj and his team are engaged in doing here. When you expose material to high energy radiation, you produce free radicals. And these free radicals are able to combine and generate and give you cross-link materials. These cross-link materials are wonderful things because by sheer force of physical energy, you are cross-linking materials, you are not adding any kind of chemical additives. So you have extremely pure materials. So whether if it has to come in contact with food, no chemicals are present. If you have to make it a wire or cable out of it, it's a much better insulator because small kind of chemicals deteriorate your wire and cables. So these are the two things on basis of which you have huge amount of applications. The cables that are used in most of automobiles, railways, aerospace, power industry, photovoltaic cells, electronic application, even for the solar generations are mostly cross-linked cables by high energy radiation. Again, as I said, this is about 200,000 plus electron beam machines are used across the world for modifications of these material. And it is an industry of more than $100 billion across the world. One of the very important application is to make heat shrink materials. In this, what is done is that you take the material, irradiate it and cross-link. Then when you heat it above its melting temperature and blow, you will be able to expand it. But the thing is, when you reheat this material, it remembers the original shape from where it was expanded and shrinks back to that. So this is what is called as memory effect in the polymeric material. This is an absolutely fantastic thing that you come across when you go to the supermarkets today and you see your food being covered in by heating it in the microwave. It is these kind of shrink materials. If you see the materials which are transported, most of them is by this kind of heat shrink material, which you put it across and just heat it, it will shrink and capture the material. You want to join the pipelines, this is used for joining the pipelines. You want to join the telecommunication cables, these are utilized for that. So huge amount of applications again are because of these kind of materials. So just again once more to prove my point. Look at this. This is a car. A car typically weighs about 1,000 kg, about a ton. And you will be surprised again if I tell you that almost 10% of that is today a plastic material. Whether it is your dashboard or it is your bumpers or it is your seats or it is your coverages, all of them are polymeric material. So about 100 kg of, and without tires, about 100 kg of polymeric material go into making a car today. And with more and more fuel efficient cars, you need materials which are thinner and thinner and which are more, occupy less space. So in these cars, you will see the wire and cables that you use are cross-linked by radiation. The foam that you see on the seats is produced by radiation cross-linked material. Tires, 92% of the tires that are produced in the industry, in the cars, are at some stage utilize electron beam radiation for cross-linking. And if you see, there are close to 100 million cars which are produced in the world. And each car has 5 tires. And besides that, we have tires which are replaced regularly in our cars. How much electron beam radiation is utilized in this industry? So this will give you an idea why is it that nuclear applications have a lot more commercial value as compared to power alone. That's the only point I'm trying to make it here. Not only about this, another very important part that nuclear technique plays is preserving past for the future. Again, in many of the, especially if we have seen museums, if you wish to save the artifacts, nuclear techniques play a very important part. And first, to see inside what is there, how the structure has been formed, you use X-rays and other techniques to see, and then also to, if it gets infested by fungus or other thing, you can treat by radiation. So this is a very important part. This you can see restoring of cultural heritage, which I call as nuclear art. The most important events that have occurred in the history. One of them is treatment of Ramsey mummies, which are there in the Egyptian museum. They were infested. They are huge, very, very old mummies, and they had fungus and other treatment on them. So they were treated by radiation by taking them to France and then brought back. This is one of the most historical event that has occurred in the art industry. And second thing which has happened recently was about 10 years ago, baby chroma. This is a 40,000-year-old mammoth which was discovered in Siberia, and it was contaminated with, again, some very deadly bacteria. And the only way it could be, before treatment by other people, it would be handled was that you had to treat it with radiation so that you kill the fungus and the other bacteria, and then only you can handle it. So these are the two of the epoch-making things in art and culture industry, and where radiation has played a very important part. Besides that, huge number of library books, legal papers are regularly treated by radiation technologies for preservation.
Professor Savarol, you have 2 more minutes.
2 more minutes? Okay, then I come straight away to, sorry, Pant, I had something to show related to your subject areas, but because of the time limitation, I'll come to the last country which I wanted to bring to your attention. That this is an example of status of radiation technology in China today, which is our neighbor country, almost of our size. And there are more than 400 institutions which are working in R&D in radiation science and technology there. And it has an annual output of $43.2 billion coming from radiation technologies. And as you can see, in the year of 1999, that's about 2000, they had a revenue of about $2.8 billion. And today it stands at about $43.2 billion. They have about more than 500 electron beam accelerators, 400 medium energy accelerators, 40 high energy accelerators, 50 low energy accelerators. And I showed you the examples of wire and cable cross-linking or heat shrinkable material that you see across. Most of those material today comes from China. And because of these accelerators that they have put in last not even 15, only in 10 years, they were putting 40 to 50 accelerators per year. And probably in India today, we have about 12 to 15 accelerators which are working. Compare that to this number of 500 electron beam accelerators that they have put. And this is related to gamma radiation technologies. They have about 160 gamma radiation plants which are working and treatment of medical products. Now, again, coming to the last one, which I wanted to make about agriculture. I'm not sure whether in our country we have been able to generate this kind of number, but they are not difficult. We probably could produce these kind of numbers. Look at here. They have about 800 mutation varieties of 45 kind of plants, and 20% of China's crop area today uses radiation-treated mutation breeding. And this is about 20 million acres of land, which contributes about 3.5 to 4 billion kilograms of China's grain produced are by radiation-treated seeds. And this is an industry which to them a benefit of about $2.6 billion. So the moral of the story that I was trying to tell is that there are huge amount of economic benefits. We generally keep saying that societal benefits. Societal benefits is fine, but society also adopts a technology when it brings in economic benefits. So we should look at it and see that how can we bring this to our country and to our society. I thank you for your kind attention. Thank you.
Thank you, Professor Agarwal, Professor Sabarwal, for this very informative and interesting presentation. I'm sure you had many more things to share with the audience. Because of the time limitation, I have to cut it short.
Yeah, sure.
So this presentation is now open for any comments, questions from the audience.
Thank you, Dr. Sabral, for a fantastic lecture. Because I wanted to know how to put a cost to the effect. Like, suppose I have a radiation process product, how to put the actual cost to that. Like for US, they say you take 2.5 times of that. In Japan, it is 4.3 times. So what decides this factor?
I will tell you a very simple example which you should use as a thumb rule. First thing I told you is overall. It's not that you will go into very specifics. I remember in the year about 2005, Isomed had about 500,000 curie. That's about 500,000 curie cobalt-60, which was there in Isomed. And that year, the revenue generated from Isomed was 5 crores, right? And the cost that Isomed charges for the product was about 3 to 4% of the cost of the thing that was going to be marketed, right? So you know that 500,000 curie or 500,000 curie generates the revenue of about 5 crores, and the material being treated is 25 times more, 125 crores. So like that, you see how is the cost. So that's how you will be able to generate these numbers.
Dr. Pant.
That SIT, no?
Yes.
Sterile site technique. How they may pick up male selectively?
This is at a breeding stage. In saline water, the buoyancy is different for male and female. So from there you will be able to see.
Thank you, sir, for your excellent lecture. I just want to know, radiation processing is a very important area of application of radiation technology. And I have been observing in our country for last 30 years, the growth rate of this technology is very slow as compared to China, Europe, I think United States. So now you have the exposure of the entire world because of your association with IEA. So I think you will be the best person to tell us that, what is the reason for this, where we are lacking actually. So India is a huge market. In China, there are 400 electron beam machines being used for the different applications. But in our country, we have only 13 and 14, although we have a very good scope for the radiation processing application. So this often bothers me why their growth rate is very slow, although we have the good expertise, we have the good infrastructure, we have very high quality technical manpower. So this can you tell me the reasons for this?
See, this is the stage, if you look at it, right? Up to 70s and 80s, China and us were not very different. Both of us were at the same stage of, development. But after that, which is not seen here, is that they went for industrialization of the technology. Even today also, if you see nuclear power, China and India are not very different. We produce about 3 to 4% of our power requirement from nuclear. They also have about 4 to 5% coming from nuclear, right? But they took a decision that, okay, this is an industry which ought to be established and propagated. And they went ballistic in 10 years' time. They established the accelerator. They mastered the technology. We also know how to make accelerator. Our teams also have made accelerator at Kharghar. But we have never taken the next step forward and make it industrialized. And when we say today, make in India, they did make in China that time. So that was a difference. That's why they went leap ahead, and we are still struggling. Most of our people from here, I remember when I was here and working with many of these industry people, they were going to China and irradiating their materials and bringing it back. But I'm happy to see at least that we have now 15 accelerators in the industry today, as compared to 1 or 2 about 10 years back. So
there is a question from Dr. Andreas Wagner from Germany.
Yeah, hello. Thank you very much for your comprehensive overview. I have one question regarding the medical equipment sterilization. You quoted in that paper by Tagawa et al. That the gamma ray irradiation with cobalt-60 had about 50% in the US and Japan 20 years ago. Now, how did that change? Do you have any information whether the electron beam now wins against the gamma ray irradiation? Because at least here in Germany, things have changed because the handling of these extremely strong cobalt sources are more and more an issue, for example, against terrorist threats. So these things are now changing towards electron beam. But this is a common feature?
Yeah, you are absolutely right. There is a thrust today to go towards the machine sources rather than the radioactive sources because of the security and other risks that are associated with radioactive sources. But even today also, there is a huge demand for cobalt-60 related to gamma radiation. There are about 40 electron beam accelerator machines which have been now put up for radiation sterilization, and only one X-ray machine which is in Switzerland which is operating for radiation sterilization purposes. But gamma radiation still stays the main stay of radiation sterilization.
Okay, thank you.
Welcome.
Okay, if there are no more questions, I thank Professor Sabarwal for his excellent presentation.
Thank you. Thank you very much.
Now this session is now closed. Now I thank all the speakers, Professor Professor Eberg, Professor Viedino, Professor B.S. Tomar, and Professor Sabarwal for their excellent presentations. And also I thank all the participants and also the organizers.
Thank you very much, sir. Now I'd like to request all our guests to kindly join us for the lunch, which is arranged downstairs. We will be reassembling here at 2 p.m. for the second session of Day 1 NPMMI 2022.
ठीक ही दिख रहा है ना कैमरा में, क्या इशू क्या है, मुझे समझ में नहीं आया। प्रॉब्लम क्या है? समझा नहीं। क्या हुआ? ओह ठीक है ठीक है। लेफ्ट राइट उल्टा हो गया. ठीक है अभी.
हाँ ठीक है.
मिरर हो गया.
अच्छा वो रिवर्स.
मिरर हुआ था ये और लाइट ये उस तरफ ये इस तरफ दिख रहा था ना
हाँ.
फोटो. नजदीक हो मिरर.
The handle on this thing.
आई डिडंट रियलाइज. नहीं जस्ट वो दूसरा शेयर करके आते हैं. JPEG creative.
So he's online. Shall we ask him? Okay. Metallic term. He's present. अच्छा. नहीं, मैं कर रहा हूँ. या इधर रख रहे हैं. अच्छा, पूरा ऐसा देखेंगे.
Someone can hear me? Priya, is Priya there?
Hello?
Hi Priya, this is
Yeah,
Dr.
hello,
Bal.
Dr. Bal. How are you?
Can you hear me and see me?
Yes, yes, we can. Can you see us?
I can see only the auditorium. Somebody is walking with the mask.
Priya.
Okay.
That is Priya. Priya in front of camera.
Yeah.
I'm sorry I missed your call, even though I
I
mailed
was
you my
trying
number
to,
and
unless you give me the power to share this screen, I can't share because the guests are
I
not allowed to share
understand.
this.
Actually, we had taken a short break for lunch, so yeah.
And that is most important thing. Lunch has to be there. Otherwise, you can't hear anything in the empty stomach.
Yeah. So we still have 2-3 minutes. So we'll start the session after 2-3 minutes only because there are online participants as well.
Okay, sure.
So
I'm
just
ready.
within
Whenever
2-3
you tell
minutes we'll
me,
start.
I am ready. Whenever you tell me, go ahead, I will start.
Okay,
My
okay.
time
Thank
will
you.
start from the time you say okay.
एक आधार में रख दिया बरोबर क्या कर रहे थे फुल स्क्रीन में वो बोलेगा तो आएगा बोलेगा तो एक्टिव स्क्रीन वो तो मुश्किल है भाई फुल स्क्रीन कर हाँ क्या वाला
A very good afternoon to all of you. I welcome you all to the second session of Day 1 NPMMI 2022. I'd like to request Dr. S. Kannan, Associate Director, Radiochemistry and Isotope Group, BRC, to kindly chair this session. Please, sir.
Good afternoon to all. Welcome you all for this second session of the team meeting on nuclear probe, materials, medicines, and industry. In this session, we have three invited talks. My first one is by Professor C.S. Paul from All India Institute of Medical Sciences, New Delhi. And second talk is by Professor Sandeep Basu from Radiation Medicine Center, Mumbai, India. Third is Professor Radak Jaleski from Marie Curie, University, Poland. So this is about 1 hour, and each speaker is given about 30 minutes, 1.5 hour. I request all the speakers to complete the talk in 25 minutes and allow 5 minutes for any question answer. So the first talk is by Professor P.S. Paul. The topic of the talk is novel theranostic approaches in nuclear sciences, a current challenges. Professor Paul, please.
Yeah, thank you, Professor Kanon and dear friends. I'm extremely thankful to Dr. Pujari and Dr. Priya and Dr. Mahapatra and to the Nuclear Science Center to allow me to participate in this August gathering. My talk will be in novel theranostic approaches in nuclear medicine and the current challenges. And okay, so what is this? Now this called buzzword. In every science there is a buzzword, and now the current buzzword is theranostics. The treatment strategy that combine diagnostic testing with a targeted therapy are called theranostic and the epitome of personalized medicine. And this word was coined by Dr. Warner in 2004 and published in Scientists. But we are practicing theranostics since long, and we will be going by the SWOT statement, the strength, weakness, opportunity, and threat perception, how this novel theranostic approach is going to fructify. We see we have been using radioactive iodine, which is the first theranostic agent. You can see the disease, then you can treat, and after the treatment you can see the response. And this is what the 1942 and radioactive iodine for the treatment of differentiated thyroid cancer is still the gold standard for any form of cancer treatment in the world. And here you can see there is a lung metastasis and bone metastasis, and that's given in the diagnostic scan, and we give the treatment, and the patient completely recovered. After first cycle, you can see the bone lesion, and in the left panel, you have got bone lesion and you have got lung lesion, all disappeared with the 3 treatment. And this is the gold standard treatment since 1942. But what happens if there is no iodine concentration? What is its weakness? The sodium iodide importer has to be expressed on the thyroid cancer cells to take the iodine inside. If it is not expressed, the iodine cannot enter into the cell. Like look at this 29-year-old female presented with brain mets. It turned out to be the papillary thyroid carcinoma. Thyroidectomy was done promptly, but there is no iodine concentration. The FDG PET scan shows from head to toe all metastasis, but there is no iodine concentration. What to do next? So there is, see, the body has to take the iodine, or the cancer cell has to take the iodine by expressing the sodium iodide importer. So that is one of the weakness. So the difficult roads lead to beautiful destination. What are the opportunity then? So this is the theranostic. The concept is based on see, treat, and confirm the response. Here in this cartoon, I am not going to give in detail because whole lecture will be based on that. You do a diagnostic tracer study, and you demonstrated in the lower panel, you can see the demonstrated extensive disease from head to toe, and then you would give the treatment, and after treatment, you can see the complete disappearance of the disease. So this is what called theranostic. In oncology, if your chemotherapy is given, the oncologist doesn't know whether the chemotherapy will work or not. But after say giving 4 or 5 or 6 cycles, then you do the CT scan and do the RECIST criteria assessment, the tumor has disappeared or not. By the time patient has suffered 6 cycles of chemotherapy and associated toxicity. So 30 to 40% of the patient in oncology, they die of chemotherapy toxicity than the disease itself. So, but in nuclear therapy, we have to see first, then treat and see the response. So we have been practicing theranostics based on sodium iodide importer, I-123, I-124, and I-131 is the therapy agent, and I-123 is the diagnostic agent, and this is FDA approved way back. Then we have got neuroblastoma, and we are using with MIBG in medullary thyroid carcinoma, use MIBG. So the neuroendocrine tumor was in the late 80s and 90s. We have a host of somatostatin-based theranostic agents. Then we have prostate cancer is 2015 onwards. And we have got in lymphoma, we have got the CXCR4 expression. And the newest kid on the block is the FAP inhibitor, that is a fibroblast activation protein, and bone pain palliation. All these have been in the theranostic practice in nuclear medicine. I will go one by one. So what are the challenges in theranostics? The physical half-life of the radionuclide has to match to the biological half-life. Then only you can get, because 1 by T effective is equal to 1 by physical half-life of the radiopharmaceutical divided by the 1 by biological half-life of the pharmaceutical. So then only you can get the optimum amount of effective dose delivered to the tumor. The molecule, people started with the immunotherapy with the large molecules, but that did not succeed. The next was the small molecules and peptides, and we have most common one is now the enzyme inhibitors, and they need enzyme inhibitors because they are small molecule. You need bifunctional chelate. Because the metals cannot bind to the small molecules, you need a bifunctional chelate. Then the metal and the pharmacophore has to be separated. You need a spacer because there will be non-bonded interaction. There will be van der Waals interaction. To avoid that, you need spacers. So these small molecules, they are first movement in the bloodstream. They accumulate in the tumor very fast. Excretion from the body is through the renal path. There is no redistribution activity from the tumor. So you get all these are the requirement for doing a theranostic practice. So earlier we had a DTPA, and EDTA. These are all conventional, they're non-cyclic or linear bifunctional chelate. But we need bigger atoms now. We need yttrium, we need lutetium, we need gallium, actinium. You can see the ionic diameter is in hundreds. So you need a cage which will be very strong. Once the metal goes inside the cage, it should not leach out. So we started with the DOTA, then we have got NOTA, we have got DOTA-GA, that is a glutaric acid added. Then we have got HBED-CC, which is for used for PSMA. So these are the bifunctional chelate, and then we need a spacer to keep the pharmacophore away from the binding sites. So we have been in BRC using the samarium 153 ADTMP for quite some time. You can see that bisphosphonates labeled with, and you have got a chelating agent attached, that is the DOTA, and you can replace the gallium with lutetium, and you can use this, and this has been well established. This is the lutetium 177 group in IAEA way back in 2004. This was, you can see Dr. Meera that time very young, and she was participating in that same. There was a combined meeting of the physicians and the radiochemists, a joint meeting. And that meeting, the lutetium was, because of, Dr. Pillai had personal interest in lutetium. So he created this group, and all these people were asked to take the lutetium to the next level. And in that, everybody was asked to do a phase 0 and phase 1 trial, but nobody opted for that. I was the first person in that group. I opted for doing a phase 0 and phase 1 trial, and the result is already published in Current Radiopharmaceutical in 2016. And then the phase 2 trial study is also published in the European Journal of Nuclear Medicine. And in that study, we demonstrated even if you give lower dose and higher dose, you randomize the patient, 22 patients in the lower 35 millicurie and another 22 patients in the 70 millicurie. We demonstrated the pain palliation. If you are using it for pain palliation, this is identical. But if you are using for increasing the overall survival, higher dose is better, which is now been reconfirmed by the radium-223 studies, allicin castride. So then we use a better agent, because zoledronic acid Zometa is approved for the FDA approved drug for use in bone pain palliation. And if you can use label it with a DOTA zoledronate, so we tried to label this along with the Frank Ross group from Mainz, University of Mainz in Frankfurt, and we had studied 40 patients, and this paper got published in European Journal of Medical Research. This is the basis of this trial, and we did the dosimetric study. And in this dosimetric study, you can see the skeletal dose is milligray, that is 2 to 4 to 200 milligray per megabecquerel you can deliver, and median was about 104 Cwatts. So it is a very safe drug. You can treat them, and we are now planning a phase 3 randomized control trial to that, and we hope this will be approved. So then we come to the another trial is called the PRRT group of IAEA. You can see all the big names, Dr. Baum, Lisa Boddy, and Tom Derisio, Dr. Ravi Kashyap was there, but unfortunately Ravi is no more. So we have all these groups, Marian Pavel in the group. We had called a PRRT group of IAEA. So in PRRT, you need patient selection, choice of peptide and radionuclides, key protection using lysine and arginine, or tumor and organ dosimetry has to be done, monitoring of the toxicity to be done, clinical research and future direction. This was the objective of this group. So we, in that time in 2004, we had octreotide, DTP, indium DTP octreotide, because that time the cyclic bifunctional chelate was not available. So indium was used, DTP was labeled to indium and in one arm and octreotide in another arm. But unfortunately, indium has triple one has got a length of only 10 micrometers. So if the tumor is big, you will not able to deliver the enough dose. Then the group tried to use the DOTA, yttrium-90 DOTA, but yttrium-90 has got a maximal is 12 millimeter, which is very big. So there was renal toxicity and kidney failure started up. So the last and most important one is lutetium-177, which has got a half-life of 6.71 days, and the nuclear cross-sectional area is around 2100 bonds. So you can produce in any nuclear reactor, and you can produce in Curie quantitative activity, and it's tipped as the metallic iodine, which will be the most popularly used radiotherapeutic agent for the future. It has got 2 millimeter, so it is very good for the cells. So by 2004, we had 4 groups in the world. They were using this PRRT. One, the Rotterdam group from Netherlands, and New Orleans group from Tom Doricio, and Lisa Bodi from Milan, and Basel group were the 4. They were using indium, then yttrium, lutetium. That's the last one to be used. And then this octreotide is a somatostatin analog. It has the original native somatostatin has got 28. It gets chopped to 14. But what we need basically is the last 4 hairpin loop system, where phenylalanine, tryptophan, lysine, and threonine has to be in the loop, and you have to have a these are SS bond, that is the salt bridge, to keep the 2 systems together. So you have to maintain this domain structure. So you can, without that, you cannot have the biological function of octreotide to keep the octreotide intact. So you can change any of the replacement by the L amino acid replaced by D amino acid. So the biological half-life from 1 minute increased to 6 hours. So how it helped this DOTA-NOC and DOTA-TOC, DOTA-TATE, all these helped us in not only in the diagnosis, in the telling the patient what patient should be benefited by what. In this patient has got a mid-gut carcinoid. You can see there is a tumor sitting there in the arrow. It's beautifully taken by the gallium DOTA-NOC. Nothing else, not in the liver, not anywhere except the tumor. Now this patient is very nice patient for schedule for surgery. So you don't have to give PRRT in this patient. You just give the send this patient to a gastrointestinal surgeon. He will take it out. The tumor is, the patient is cured. But in this patient, see, look at this patient on the left-hand side. There are extensive metastases from the neopancreatic neuroendocrine tumor, and there is extensive liver metastasis. So if you give PRRT every 3 monthly interval, you can see there is a partial response. At the end of 12 months, you can see there is a 80 to 90% of the tumor has been disappeared, but there is no complete disappearance. So this is called partial response. I had a PhD student in March 2008 to 2012. We recruited some 88 patients, and out of that, the inclusion criteria, exclusion criteria, 61 patients included. We did the dosimetric analysis of the kidney, liver, spleen, pituitary gland, and the primary tumor, and then subsequently the detailed toxicity profile we published in Cancer Biotherapy and Pharmaceuticals. And the IAEA had brought out a guidance paper, this called Practical Guidance on Peptide Receptor Radionuclide Therapy, and this is published, and you can see there are authors who have contributed to that. Then, you know, in oncology, monotherapy rarely works. You have to give multiple therapies. So we added capecitabine, which is a 5-fluorouracil, with the DOTA-TATE, and we demonstrated that if you give combined chemotherapy with radionuclide therapy, your benefit is much more than only giving one. So then, if the patient has now given lutetium DOTA-TATE and patient failed, what is the next? The next is you give, instead of beta, you give alpha, which has got radiation, the radiation weighting factor for beta is 1, whereas the alpha is 20. So the effective half-life will be something like 7 to 8. So you are giving 8 times more effective dose. And you can see in the first paper we published in European Journal of Nuclear Medicine way back in April 2020. And then the preliminary experience, and subsequently we have a detailed paper which has come out with very well. And then last year, this 6-8 months back in the June meeting of SNM, our work is awarded as the Henry Wagner Jr. Best Paper of the Year 2021. It is in the SNM meeting, and we are in the first in the world to demonstrate that actinium DOTA-TATE even can be used in patients who have failed lutetium therapy. So that all the roads are not closed. Look at this 36-year-old male diagnosed with a grade 3 pancreatic neuroendocrine tumor. Earlier it is called neuroendocrine carcinoma, but now we know that is the grade 3 has been separated into grade 3 NET and grade 3 neck. And this grade 3 neuroendocrine tumors can be treated with PRRT or many other options. In the left-hand side, you can see there is a Dotanox scan hardly showing any uptake, and then FDG showing very little uptake. But look at this new agent that is FAPI showing very. I'm coming to that. So there are golden opportunities opening up. If one therapy fails, you have another option you have got. So coming to the prostate cancer, we have got prostate specific membrane antigen, which is a type 2 peptidase enzyme, which is present in the cell surface, in the membrane, which has got extracellular and in transmembrane and intracellular, small intracellular part. It has got 707 amino acid extracellular, 24 amino acid transmembrane, and 19 amino acid intracellular. This enzyme antagonists can be developed. They are small molecules. They are called PSMA. 617 is a small molecule which can be labeled with gallium and lutetium, gallium, lutetium. And you can see this patient which has got partial response. This one point I wanted to emphasize. This is the lutetium used from our BRC reactor, and this has got low specific activity. In this patient, we could achieve a partial remission. But anyway, patient is much better than not having. See, this is the lutetium we got from ITG, which is high specific activity, something like if your BRC lutetium is around 18 to 20 or maybe 25 maximum. But in ITG, lutetium is around 100 specific activity. Look at this patient who has got FDG PET scan showing extensive mets, in PSMA scan showing head to toe metastasis. This is the after therapy first cycle, second cycle of ITG lutetium, and you can see now complete disappearance after 2 cycles. So this is because of the high specific activity of lutetium. So we have, if the lutetium doesn't work, we have got actinium also, actinium PSS 617. Our experience we have published in Theranostics, and the results are very exciting. So coming to the last domain in the process is the fibroblast activation protein inhibitors. These are the novel theranostic agent. Fibroblast activation protein is it's only very recent, the nascent one. This is just published in Journal of Nuclear Medicine in 2019. And this is the University of Antwerp Medical Center developed this, the pharmacophore. And this pharmacophore you can attach to the this quinoline ring to this is piperazine ring. You can attach, and then at the end you can put a DOTA or NOTA. Then you can make this. So the FAPI2 and FAPI4 are the pharmacophore should not be disturbed, but then bifunctional chelates. And this agent is not like prostatectomy only, it will work in prostate cancer, but here it can work in many, because this fibroblast activation protein is the stimulator for the fibroblasts, which are normal fibroblasts, but they get converted into cancer-associated fibroblasts. Because in a cancer mass, suppose say there is a 10 gram of tissue, 90% of them are the supporting cells by the cancer-associated fibroblast. The remaining 10% is cancer. So earlier, the people were trying to kill the cancer cells, but what the modern approach is now, to not only kill the cancer cells, you can kill the cancer cells by manipulating the milieu of the cancer. So you are now approaching the cancer supporting cells. So if you kill the supporting cells, the cancer will automatically die. So this is the new concept. So there are different drugs now being developed, monomers and dimers, and we are in the process of developing with the Dr. Frank Ross group from University of Mainz. And we have done the animal studies and then human studies at our place. And we have shown them that the biodistribution, pharmacokinetic dosimetry of gallium, we compared against the FDG, and we got the exactly similar reports what the JNM has published. And this is only 1.5 years later. So we are at the cutting edge of this is in May 2020, we published this in the breast cancer, and that is the image of the month it has got published. So you can treat many cancers, including breast cancer, thyroid cancer. And then we can label with, instead of gallium, we can label lutetium and we can use it for therapy. But one thing we found that in this, our work, we found the biological half-life of the monomer is very low. So we need to increase. If you want to deliver higher dose, within 24 hours, everything is gone. What we need is to keep the tracer a longer time in the tumor so we can deliver larger dose. So how to do that? So we have now developed a new molecule that is called DOTA-GAP-FAPI. Instead of DOTA-FAPI, we have got one functional group is now freely available, and then you can make a dimeric. So this is the squaric acid. Instead of piperazine, we have a squaric acid here. So these two squaric acid and the UMCA, this makes the DOTA-GAP-FAPI dimer. And this DOTA-GAP-FAPI dimer is now the development at our center. We have, you can see the tumor uptake increases intensely. And then we have the first human results in biodistribution pharmacokinetic dosimetry of lutetium DOTA-SF-FAPI and lutetium DOTA-SF-FAPI therapy is been published in pharmaceuticals. And we demonstrated that better results on monomer has been scope of this. And now you can see the monomer, which was only 24 hours, now increased to 6-7 days. You can at the end of 168 hours, that is 7th day, you can see there is intense uptake in the tumor tissue. And even in the breast cancer, you can see there is extensive mets, and you can see the lutetium DOTA-SF-FAPI. So it has opportunity to treat. And this, our initial experience on radioiodine refractory thyroid cancer, which was developed some 8 years back. There was no further development. We tried to use, because I have my interest in thyroid cancer. I've been working for last 32 years on thyroid cancer field. And we have this initial experience in 15 patients, and we got it published in thyroid. And you can see these beautiful results. Those who are not having radioactive iodine, even brain metastasis is getting cleared off, and lung metastasis is getting cleared off. And we have demonstrated out of 15 patients, 7 patients showed a molecular response. So which is extremely, extremely good result. And the future prospect is to dose escalation study, and then we have to improve the molecule further to achieve greater tumor sink effect. And then coming to the last part of my talk in 2 minutes is the do not correct a fool or he will hate you. Correct a wise man and he will appreciate you. So what are the threats? Threats is that radiochemistry, every university has got chemistry department, but radiochemistry is very rarely seen in this country. So radiochemistry has observed a multifold development in abroad, but requires further research in chemical and biological equivalence, improve the target to non-target ratio, refinement of tracer molecule. But then coming to the use of licensing product, the cost of licensing, oncologic engagement, and response to global demand. Huge, huge scope for the radiochemist. We have lutetium coming from BRC, is N-gamma reaction using lutetium-177, so it cannot be carrier free. So you have a low specific activities. Sometimes you get 15, 20, maybe maximum 25. I have seen for last 14 years. Then the ITG is producing this N-gamma yttrium-176, which is the carrier free, and you get around 100 specific activity. So the shortage of therapeutic radionuclide, even good old iodine is not regularly available nowadays. I don't know what is the problem. Lutetium low specific activity is frequently reactors are down and irregular supply. And what about think about actinium-225? Extremely difficult and highly expensive, and procured from international market is becoming drying off. So what BRC should do now, have a task force to create the alpha therapy in this country. That is my request. And fortunately, the European Society of Nuclear Medicine adjudged in 2019 our best paper. And then in 2021, we got Henry Wagner's Award Best Paper for 2021. And now the cover page of the Thyroid, which is the American Thyroid Association official journal, has put our image on the cover page of Thyroid. So thank you very much and for patient hearing. I am there to answer any question.
Thank you, Professor Paul.
I just finished exactly 25 minutes.
The talk is open for the discussion. Sir, I have some, not doubt. See, since you told this is theranostic, right?
Yeah.
So actually, I feel that first diagnosis, afterwards only should be therapy.
Yeah.
So under that condition, the name itself is something, of course, it may be frequently used by nuclear medicine.
No, no, it is a hybrid. It is a hybrid.
Okay.
First, you do demonstrate and then you treat. So you just change the, you keep the, you will just change the payload. Your missile will be biological warfare or it will be nuclear warfare, or but the delivery system same.
So
So you are using a diagnostic agent, say gallium or a fluorine or technetium to a molecule. You see this trace distribution of the tumors, and then you change the radionuclide by a theranostic radionuclide. You can deliver the beta or alpha therapy, and or J electron. You can produce the therapeutic effect.
Okay, sir. So when you accept actinium-225, it is
Yeah.
alpha emitter.
Yeah.
It is used for only therapeutic purpose, not for the diagnosis.
Yeah, but उसका counterpart is gallium-68. But its counterpart is gallium. It is not the actinium. It is actinium, which is payload is your PSMA, your DOTA-NOC or DOTA-TATE or FAPI. On the back of the FAPI, FAPI only decide where the molecule will go. But the tail is attached to a radionuclide tracer, so it will do the damage.
Okay. Thank you. Do you know more? Any? Yeah.
Thank you very much, Professor Bal, for a very nice overview on theranostics. This is Pujari.
Yeah, thank you.
I just wanted to, not a question.
Yeah, you can see how much we are not a radiochemistry department. We are a clinical department, and fortunately we are collaborating with a group in France, in Germany, and we have been in the forefront of the cutting research. You can see in 70 years, the India never got a Henry Wagner Award. First time in 70 years, India got the recognition as the best research of the year in SNM, Society of Nuclear Medicine, USA.
So I must congratulate you for that. I just wanted to comment on current level of the radioisotopes quality and quantity.
Yeah.
So things are changing, and you know that government has announced setting up of a new reactor only for isotope production.
Yeah.
So that is the project is progressing very well, and it will be one of the largest in the world in terms of the volume of radioactivity that will be produced. So in the short term or medium term, we are also looking, my colleagues in radiopharmaceuticals division, they are examining, and developing some process for producing lutetium-177 through the carrier-free, through EPM, and you'll be happy to know that we are engaged in BRC on developing these radioisotopes, enriched radioisotopes themselves, because that itself is that could be a choke point if the supply is restricted to us.
Yeah, last 2 months we have not got on microcurie of lutetium.
Yeah. So
yeah, see, the second thing I would like to, Dr. Pujari, was to encourage you. The actinium-225 can be also produced by the radium-226 path.
Yes.
Why don't you try that? We have got tons of radium in our country. Radium-226.
We have a shortage of radium-226. We have hardly less than milligram radium. That is not even the global supply right now is from the legacy waste of uranium-233. If you have a huge stock, then that decays to 229 thorium, and that 229 thorium gives you 225 actinium. So all the international supply is through legacy waste. Unfortunately, we don't have that much, but we in DRC, I'm assuring you that we are engaged in sourcing whatever actinium that we can do, at least 5 to 10 patients a year. So that work also we are engaged.
I treat 30% in one batch. You are talking about 5 to 10 in whole year. We are treating 30% in and still my waiting list is 6 months.
But you are buying it, not purchasing it.
Yeah, that's what. But we will buy from BRC also. BRC is not going to give us free.
No, we are not. We'll give you free.
Your iodine cost is 2 times than the private iodine supply.
So you tell
your
them
information.
For
your information, the iodine supply from the South Korea is coming from even from the Iran is half the price what BRC is selling.
So on 23rd, I hope you are coming to Mumbai, or you'll be joining online.
Yeah, I didn't get any invitation. I hope I will be because without invitation, I can't go as the head of the department. I cannot go without.
You'll be getting it.
Yeah.
Yeah. So it is.
Yeah, there is a huge scope. I think there is a huge.
We'll discuss the supply issues that day.
Yeah, sure.
So,
okay. Thank you.
And we are trying our best to improve the services, and BRIT also will be there, and we can address this.
Sure, sure. Thank you.
Thank you, Professor.
Thank you. Thank you.
Thank you. And our next speaker is Professor Sandeep Basu from Radiation Medicine Center, Mumbai. The title of the talk is Impact of Positron Emission Tomography on the Practices of Medicine over last 2 decades. Dr. Basu, please.
You have to say your basis so that all out so they can see. Okay. Sure. First slide. So a very good afternoon to all of you. And I would like to take the opportunity to thank the organizers of NPMMI theme meeting, Dr. Pujari, Dr. Priya, to invite me to participate in this academic activity. So, there are two major developments over the past 2 decades in the field of nuclear medicine. The first one, of course, if I analyze 2000 to 2020, the stress of 2000 to 2010 was everything was PET-CT. The 2003-4, we got the first PET machine in the country, and then over till 2010, all about PET. And if I see how 2010 to 20, these 10 years, primarily it was therapeutic radiopharmaceuticals, and where I feel BRC has done a great job with respect to the providing the lutetium to the entire country. So in this treatise, we are going to see how PET-CT caused a revolution in the medicine over the last 2 to 3 decades. So the practice of medicine is highly indebted to the positron imaging research, where this forum is involved. And this has increasingly made a mark heavily in the oncological, cardiac, neurological, and also in a big area in infectious inflammatory disorders, along with other applications. Now in the PET-CT, this is just to see the standard PET-CT imaging protocol. We have 3 particular 3 points in PET-CT imaging in a standard PET-CT machine. So this is a typical PET-CT machine that we have in RMC, is a time of flight PET-CT scanner. You have the CT gantry and the PET gantry, so a combined gantry, and the patient undergoes both these scans one by one. So what are the components of it? First is topogram, or what is called a scout image. So the patient undergoes a scout image where you can define the coaxial imaging range, and then the spiral CT where you calculate the attenuation correction, and this is also used for anatomical correlation. Then the patient goes to the PET gantry where emission scan is attached, and from the CT image what you calculate is mu image, which is also the attenuation correction factors, which is applied to these emission images, and finally this fused PET-CT image is produced. So you have a topogram or scout image, and number 2 is spiral CT image, and number 3 is PET emission image. These 3 combined a standard PET-CT scan in a standardized protocol. Now this PET-CT, how really it has, we had CT, we had excellent MRI. So the question is how it has really augmented medical imaging. First, it has produced superior sensitivity and resolution. Number 2, a greater flexibility of incorporating positron levels into biomolecules. So we had this conventional gamma camera, but where PET-CT really scored is you could have the flexibility of incorporation. So you could use glucose, you could use amino acid, you could use receptor tracer like PSMA, DOTA. So a whole lot of molecules, biomolecules could be involved. And then the third point, SPECT was good, gamma camera imaging was good, but PET-CT allowed superior quantification. So we could quantify how much is the tracer uptake into the tumor. So that really helped in your treatment response evaluation. So just to see what are the major targets that have been used over the last 2 decades in PET-CT imaging. Among them, the red colored ones are the one which in our clinical practice today, not only in India, but all over the world, these are the maximally used PET-CT. So first is, of course, the molecule of the century in diagnostic imaging, which is FDG, glucose uptake and enzymatic phosphorylation. Then comes amino acid uptake, which is in the form of fluoroethyl tyrosine. So brain consumes glucose a lot. So for that, FDG is not good, particularly the low-grade tumors where fluoroethyl tyrosine or these amino acid tracers are useful. And then from the previous talk, you saw that theranostic. So you could target somatostatin receptors. You could target PSMA in prostate cancer. You could target estrogen receptors with fluoroethyl estradiol, which is estrogen receptor. So these were used for protein targeting with PET-CT. And also very importantly, we were doing bone scans with MDP, but fluoride PET-CT came, of course, with PET superior resolution. So fluoride PET-CT. So in a standard nuclear medicine clinical work profile, these are the ones that the red colored ones are the ones which are maximally used, though a whole lot like FLT, RNA components, phosphatidyl choline, so many are there. Now just a brief recap, what really FDG. FDG is often termed the molecule of the century. So for diagnostic imaging is concerned, it is taken up in a high amount in the tumor because of 3 factors. First, GLUT overexpression, that is glucose transport. So one of the earliest marker of malignant transformation is GLUT overexpression. There are 4-5 GLUT receptors. Among them in malignancy, GLUT 1 and 3 are important. Number 2 is hexokinase, the second path of glycolytic in the cell, hexokinase overexpression. So these 2 components takes FDG in high amount. And then in tumors, glucose 6-phosphatase, which actually washes out the tumor FDG6 or glucose 6-phosphate to FDG back, is in very less compound. So these 3 factors leads to what is called as metabolic trapping of the radioactive glucose, which is FDG6-phosphate, into the cell. And that gives rise to the so-called hotspot in PET-CT imaging. Subsequent enzymatic processes, they are very stereospecific. They don't allow FDG6-phosphate to get metabolized the subsequent steps. So what happens in tumor cell, FDG6-phosphate gets metabolically trapped. Now, virtually at every steps of cancer, so we started with 1 or 2, if we think of 2003-4 when we started the PET scans, and today virtually in every part of decision making, PET-CT in cancer management has made a mark. So detection and diagnosis, initial staging and restaging, monitoring treatment response, detection of recurrence. So virtually every step now PET-CT is being considered in cancer management. So if I analyze, there is a thing called this personalized management, and which has maximally effect in oncology, particularly because of its lot of side effects of chemotherapy. So you want to see very clearly whether your therapy is going to work much early in its course. So if I see the initial, say 3-4 years of PET-CT imaging, all that we read is accurate disease staging. So all PET-CT was doing is PET-CT was staging the disease much better compared to CT or MRI. So accurate disease staging, early initiation of appropriate therapy. That was one. And second, after the therapy has been given, the oncologist wants to know, I have treated whether there is viable disease or not. So this first one and the last one. So first 3 or 4 years, if I think of RMC's PET, we were only addressing from TMH oncologists these 2 questions. But virtually after that, what came as the personalized management. So the other aspects came up, defining tumor biology and heterogeneity of tumor characteristics, surrogate of targeted therapy to be found out by receptor-based PET tracer, and then you see early treatment response. So by that way, you can tailor and customize any treatment, particularly the toxic chemotherapies by the help of the PET-CT imaging. So this is a garden variety standard case. I just took last week's case, one lung cancer who came, who of course has multiple disease seen in CT.
But if you see the PET has identified something sitting in the adrenal gland. So obviously the disease becomes stage 4. So this lung CA immediately becomes stage 4. Not only that, there are some splenic metastasis which is unsuspected. So these were the things which were our initial observation, that PET started finding out disease much more than the CT. Subsequently, if you see, this is a contrast CT. This is a big lung mass. If you see the CT mass, if I see this CT and this is inoperable by the thoracic surgeon, and then the radiotherapy has to be given, CT cannot tell me whether this entire tumor is viable or, so what happens really, because of the pressure of the tumor, the lung gets collapsed. And that in CT shows almost equivalent. As you see, if I see this CT, I want to read, I cannot tell how much is the tumor. What FDG does is, FDG will be taken up only in the viable tumor. What is its importance? This is a big mass, chunk of mass, which has to be given radiotherapy, and radiotherapy is toxic in lung. So I really don't want to give too much of radiotherapy to the entire lung. PET tells me that this is the area that is viable tumor. This is only collapsed lung. So the radiotherapy ports could be given to the viable tumor. So after your initial disease staging, I will just go 1 or 2 examples where we are really using PET-CT in a big way in disease management. Then comes, this is a locally advanced breast cancer. So LABC we call. And one of the most important treatment of LABC is giving neoadjuvant chemotherapy because it is not operable. So this is pre-treatment. This is after 4 cycles of neoadjuvant chemotherapy. So you see there is an excellent response and only minimal disease is there. So this is very important because today for every chemotherapy, there is a first line chemotherapy, there is a second line, there is a third line. So you would like to know whether your chemotherapy is working or not. This big mass very often will not totally go away in CT. This has particularly good relevance where it has really made changes lymphomas. See, when we were students, we were doing the diagnostic, some of those gallium imaging, and they were coming after 6 cycles of chemotherapy or CT. And then we will tell this chemotherapy has worked or not. And by that time, the patient has already undergone 6 cycles of toxic chemotherapy, and some of them will not respond. So what really has changed? Today, the oncologist will do a PET-CT at 2nd or 3rd cycle. It was initially 3rd cycle, but now it is even 2nd cycle, the oncologist. So this is a Hodgkin's lymphoma. Patient has undergone the 4th AVVD chemotherapy, and after that you see very good response. So that means the therapy is working. The patient will receive another 3 cycles. So you see here, there are 2 patients. One has shown very good response in Hodgkin's lymphoma. The other patient has not shown any response. So again, importance is at 3rd cycle, the oncologist knows this patient, his traditional chemotherapy, that is AVVD, has not worked. He has to go for the 2nd line. So PET-CT has helped your treatment response by doing this early treatment response much earlier. So this is also a part of personalized management. So you know that this patient need not go for 6 cycles of chemotherapy, and here we need to consider for the 2nd line of chemotherapy. Third, very importantly, you know, this another 10-15 years, last 10-15 years, there is a lot of targeted molecule, targeted therapy. And in this target, what is known as tyrosine kinase inhibitors. This has come in oncology and chemotherapists and the medical oncologist domain in a big way. And you will see a large number of tyrosine kinase inhibitors that are there. And this is one of the area which if I have to think, I worked 2004 to 2008 in a big way along with TMH oncologist in the GI group. That this GIST is called gastrointestinal stromal tumor. This used to be one of those dreaded malignancy where after diagnosis, death was sure and certain in a large mass, almost by say, I will tell 1.5 years in this thing. After this molecule came, imatinib mesylate, there was a sea change into the prognosis. It probably started something around the same time we got the PET scanner, maybe around 2000, 2002, and many of our patients that time were getting it on trial basis and getting a PET scan, Indian patients at RMC. So that's how, you know, this thing, and also many of them were getting follow-up at TMH. So if you see what really happens, this patient of gastrointestinal stromal tumor, see the CT, and this is pre-treatment, and this really gave the PET scans a big everywhere it was like PET. It came because of the results in GIST. And if you see, and world over, everyone started working on it. So this, if you see in the CT, it is almost same pre and post treatment. But if you see the tumor wise, this is pre-treatment and within 1 month. So the importance is the tumor is there, that's almost similar size, but the metabolically inactive. So the importance is that what the treatment is, what the tumor is doing is more important, and not only the size shrinkage. And most of these patients who underwent this imatinib mesylate, around 70 to 80% response rate. So those who we started seeing this kind of a result, and it was also translated that many of these patients who used to otherwise not survive because of imatinib mesylate, they started surviving, and many of the patients now, this has become a choice treatment, imatinib mesylate. But what important from PET scan is PET molecular imaging showed first with these targeted therapies where there is no size shrinkage like chemotherapy, but your metabolic activity goes down, which is not evident in the CT scan. And then comes quantification. You see partial response PET CT superior quantification. This is a case of parotid lymphoma, and you see pre-treatment, post-treatment, the mass is there, and there could be sometimes partial response. PET CT SUV max is very well calculable, and now it is, of course, compared to the first generation scanners, it is readily available to the PET CT readers. So you can do all kind of so now there has been development of persist criteria where you can see SUV max at different. So more than 30% is called partial response. Less than 30% is minimal response. So you can do that with your PET CT quantification. Now the next one is also a very important thing, which is called the finding out the tumor biology. See, this has yet not totally been translated into the clinical practice, but just to show you, see this, there are two tumors here in the breast, and you see this is ERPR positive and HER2 negative, and this is triple negative breast cancer. Now see, again, a kind of a personalized management, same breast cancer, in one, there is a good prognosis, and where you see the FDG uptake is very less. Whereas the other triple negative breast cancer is known that it is biologically aggressive, and you see the FDG uptake is very high. So what is its implication? The biologically aggressive cancer, same size, but it is also consuming glucose very high. This has, I will tell, we can think of that this in the coming 5 to 10 years, this will be used in oncology. Presently, it is not being used. We are observing it that a biologically indolent, which hormone receptor positive breast cancer has shown less uptake, whereas hormone receptor negative, which is biologically aggressive, shows up FDG uptake very high. This has, again, oncologists are not totally taking this for their treatment purpose, but I presume that this will have a very important role in the coming 5-10 years, that we observe that glucose consumption as a marker of prognosis. So this is just a study that we did, triple negative breast cancer versus hormonal receptor positive, which was published in Cancer, and where we found that the triple negative breast cancer always shows high uptake. The uptake of SUV is compared to the hormone receptor positive breast cancers. Now we saw the oncology, and there is a plethora of other applications in cardiology, in neuropsychiatry, and another big area is infection inflammatory disorders. I will just go with some of the examples. In cardiac, one of the most important is viable disease. So ischemic versus viable. So you see in the myocardial perfusion scan, there is a gap. The patient has undergone kind of a myocardial infarction or so, and the cardiologist, before doing a bypass or angioplasty, would like to know that tissue is dead or viable. FDG is the gold standard. So this is now a standard practice. Before FDG, this was not there. So before revascularization procedure, a viable myocardium gives a much larger confidence to go ahead and do angioplasty or bypass. The new thing that is coming up in cardiology is seen in this cartoon. If you see in this angiography, what we are seeing is these larger vessels, which is called epicardial arteries. But entire muscle of heart, there are these smaller vessels. And the small vessels diameter is around 300 to 400 micron. So today when we do angiography, we see these vessels. But all these vessels, smaller vessels, cannot be seen. but your atherosclerosis or the thrombosis starts here first. So this is called microvascular disease. So that is very important to understand, that angiography at present or even MR cannot tell whether there is a microvascular disease or not, and PET perfusion imaging is coming in a big way, and you can do what is known as myocardial flow reserve. So my myocardial SPECT with technetium maybe cannot give me the quantification blood value, but if I use N13 ammonia, I can do this myocardial flow reserve. So resting myocardial blood flow and then stress myocardial blood flow. In stress, it has to be between 2 to 2.5. It is below that, then you know that there is a kind of a flow reserve deficiency. So the patient may have microvascular disease where it is correctable through medicine, and not, you don't need to go for. So again, the role of PET quantification in myocardial perfusion imaging, where you can use this as a for using medical management. Atherosclerosis research is a big area, but just to show that molecular inflammation is one of those early markers. These are excellent pictures, as you see. So this aorta shows high uptake in its wall in FDG. So that FDG uptake is a marker for early atherosclerosis. This is not again translated into clinical research. These are being reported in the journal. We are also seeing this, and we need to see where it goes in the coming days. Now, infection inflammation. See, something that in oncological management always came as a non-specific. This is one thing that came as a weakness of PET, became its strength. So that one thing, because we were reporting and we were telling the TMH oncologists there is a lymph node sitting in the mediastinum, they will go and operate and they will tell, Dr. Basu, you told it came out to be tuberculosis, which happens in India a lot. But what really now has happened is this has been now translated for being used into the FDG, into the infection inflammation. Just to show you, we had done a lot of research between 2008 to 11, and this is one of those tuberculosis cases done with a medical college in Mumbai with Nair Hospital. We did almost 150 patients of tuberculosis. Just to show you, this is the time when we did not have a PET CT, and we did it with only PET alone, the first scanner of RMC. And you see, this is on 4th May and 22nd June, patients baseline tuberculosis with high uptake, including the abdominal lymph nodes, 4th May scan, and then 22nd June following 4-drug regimen of tuberculosis. So that is where we started observing, and a lot of groups as well, like ours, has started thinking that particularly where you don't have sputum available, skeletal tuberculosis, where PET could be useful for diagnosis as well as for treatment response monitoring. Very important. This is an HIV patient from a medical college, pre-treatment, and after the treatment, early treatment and following. Mycobacterium avium intercellular infection in bilateral lungs by HIV patient, of an HIV patient. This is very recently done. This patient was sent from a medical college. If you see, the patient has already got 6 months of anti-tubercular treatment, and he does not improve. He has got weight loss. Of course, multi-drug resistant tuberculosis is a problem. And then the FDG PET has been done. His baseline we don't have. He was sent by the infectious department of the medical college to see how much disease it is. You see the lung is with active tubercular involvement. This is actually one of those early patients from BRC hospital itself. If you see that this patient came with the first line agent, this was the first two was in the first RMCs, those PET scanners, and you see with treatment in the first line, the hepatosplenic tuberculosis. What is its importance? Tuberculosis is usually done with sputum itself, you can do. But when you have hepatosplenic tuberculosis, you cannot do sputum as your examination. So following the treatment, there is increase in the lesions, and then it goes for second line AKT. So first line AKT, it is resistant. Second line anti-COX treatment, and after the treatment, you see there is a very good response. So again, the importance that in multi-drug resistant tuberculosis, this PET scans role is very important. This is another patient from BRC hospital itself, and you see this patient was undergoing a treatment, came to TMH with a suspicion of lymphoma. And you see the biopsy when it was done, this is another granulomatous disorder, which is known as sarcoidosis. And sarcoidosis is good because the treatment is steroid. When I saw this, it is way back 2007-8 scan. When we saw this scan, we first thought it is surely lymphoma. But these are, again, some of those false positives in FDG PET, and this inguinal node biopsy was done. He happened to be working in central complex itself, and we did the scan, and that day we were thinking, and the biopsy report came to be sarcoidosis. And after corticosteroid was started from hospital, then see after 6 weeks everything is gone. So again, PET was now in sarcoidosis. PET scan is being regularly used around 6 weeks to 8 weeks following start of corticosteroid therapy. Another very important and interesting area, we had done only very preliminary work in 2008 to 10, but now I see a lot of journal data is coming from rheumatology. This is with KEM we did, is in rheumatoid arthritis. You see joint inflammation in rheumatoid arthritis, and you have to, the usual disease modifying agent in rheumatoid arthritis is methotrexate. And this is, we were doing initially, again, we did only probably 30, 40 patients, and pre-treatment and following treatment, there is a response. So this has been being highlighted. The importance is, again, it is a whole body scan, and you can actually do quantification, how much reduction it is. So again, with multiple. So you see, like oncology, infection, inflammation has a huge. So not only infection, so many non-infectious inflammatory disorders like sarcoidosis, rheumatoid arthritis, where FDG PET can play a very important role. Diabetic food, another very important area. See, diabetic food, those who are uncontrolled, 20% of them present with foot ulcer. And one of the major diagnostic conflicts is Charcot's arthropathy and osteomyelitis. And this is during my stay in US that I had worked a lot. There was an NIH funding trial which was going on in 2006 and 7. We published it. And this is what happens in Charcot's neuroarthropathy. And in ulcer, there is uptake. If you see this vis-a-vis this is phenomenal, because we just clubbed it, the MRI and the PET scan. And if you see what good pictures you can get, so the importance is the osteomyelitis in the talar bone. You don't need to put needle to make a diagnosis of osteomyelitis. PET and MRI fusion can give rise to a diagnosis of osteomyelitis. So you see this Charcot's neuroarthropathy, which is it is a neuro, and the both managements are different. Here is only rest, where osteomyelitis will require aggressive antibiotic, intravenous antibiotic management. So you see the osteomyelitis shows up very highly. So PET really helps. In otherwise, clinically, these two entities are very difficult by the clinicians to use it to differentiate both these entities. Joint processes incidence has gone up rapidly over the last 1 to 2 decades, and there is very often complication. Patient come back with joint pain, and the two major diagnostic thing is aseptic loosening versus infection, where PET can play a role. If you see an uptake in this joint shaft ratio, so joint and prosthesis interface here, this is suggestive of infection. Again, this is being in the preliminary phase, but it looks like this also will play a role so far as diagnostic of infection. Again, you don't have to do an open biopsy, and PET CT could give a clue whether there is an infection or aseptic loosening. Infection, you have to remove the prosthesis. Aseptic loosening, you have to just give conservative management. Again, PET by the way of non-invasive investigation can play a major role. We heard from previous, previous lecture of Dr. Bal about this. So again, PET has played a major role in theranostics, 2 receptor-based PET. One is dotatate and PSMA. And again, I would like to tell that this lutetium, I know that there has been some concern, but we have excellent response. We have, I personally feel BRC has done a great job. I always tell whenever I go, because without that, nothing would have been possible. We have completed nearly 6,000 therapies with lutetium dotatate, 12 years experience. PSMA, we have now 5 to 6 years experience. The entire lutetium that made these BRC's endeavor really made our nuclear medicine to the forefront of cutting edge theranostics. And most of the centers have a very big experience. And also now what is coming as monoclonal antibody, rituximab and trastuzumab, that is what we are all working towards the preliminary phase. But just to tell you what really this receptor PET is, if you see, this is a prostate cancer bone scan, and this is PSMA PET within 5 days. But just see the difference. The bone scan is the typical thing in prostate cancer. You see hardly 1 or 2 lesions. But if you see the PSMA PET, it is flooded. So the receptor PET really was, it put a lip. So today in prostate cancer, we don't do bone scan. Bone scan is out. PSMA PET is the major thing for diagnostic. And then I'm not showing this, but as you see, every center has got, we have also got an experience with PSMA PET, pre-treatment, lutetium PSMA treatment, and post 3 cycles, excellent response. And similar, what we do is somatostatin receptor-based PET for this neuroendocrine tumor. And what we really do is we do dual tracer PET. We see the FDG PET and somatostatin receptor PET. PET has really helped in this, in our premise, in TMH and RMC premise today. You see, when we started in 2010, we did not have this step. Today in our algorithm of neuroendocrine tumor, PET is such important. Today, no nuclear medicine physician, all the surgeons, medical oncologists would like to see the PET picture, both DOTA and FDG. And by that way, we are personalizing who will go for PRRT, who will go for chemotherapy, who will go for combined chemo PRRT. Those who are both DOTA and FDG positive, they go for a combined chemo PRRT in our setting. Just to show you an example, this is a patient who is treated with PRRT alone, pre-treatment, and post-treatment, the primary has shrunk down and excellent response. And as you saw in the previous lecture as well. But again, the importance, it is not for the diagnosis, but treatment decision making. PET is also playing a role for the treatment response monitoring. So with this, I would conclude my lecture. Thank you again for your patient hearing.
Thank you, Dr. Basu. Now the session is open for discussion. Any questions?
Acharya.
Yeah, Dr. Basu, very nice talk, very informative. Just I have a query. When you talk about fluorine 18 PET scan, is it diagnosis or it is diagnosis and therapy?
Okay, so fluorine 18, you know, this hydroxyapatite has 3 components: calcium, hydroxyl, and phosphonates. So with fluorine 18, what is being targeted is that hydroxyl ion of hydroxyapatite. So that OH minus. So fluorine 18, fluoride, I of course did not show because there are so many things to show in PET scan, but fluoride PET is for diagnostic imaging. And then if we see high uptake and skeletal mets, we treat them with samarium or lutetium EDTMP. That is possible.
So my next short question is the nuclear medicine diagnosis and therapy sufficient, or we have to go for diagnosis and chemo? That is the better.
No, so it depends upon the malignancy. At present, if you see, the theranostics have particularly made a dent really in neuroendocrine tumor and prostate cancer. Radioiodine is one, MIBG. So these 4 or 5 are where nuclear medicine is coming almost at the core. Neuroendocrine tumor, yes. If you see 2010 when we started, still, all the patients that we were getting where medical oncologists don't want to touch. Today, PRRT is the first after 10 years. That I can tell. But prostate chemotherapy is also there, and nuclear medicine is one of the treatment option. It is not the front line, but it is certainly now being chosen increasingly more frequently.
Yeah, thank you.
Yeah.
Thank you, Dr. Thank you. No more question? Dr. Pujari.
Like the copper chloride based about theranostic kind of. So are we engaged in research?
Yeah. So, sir, what we are using copper chloride, we are primarily seeing gallium PSMA versus copper chloride in prostate cancer. And probably we have done around now 25-30 patients on prostate cancer alone. If you ask me, I have done a head-to-head, looks to be PSMA still has the upper hand at present, because PSMA PET is really good. If I have to see, certainly if I have to see FDG versus copper chloride is better. But copper chloride is image-wise, I see the gallium PSMA appears better than copper chloride
That
alone.
is one part. What about the therapy, theranostic, copper 64 as a theranostic?
Theranostics, one of the thing, I think the beta abundance of copper is one of the issue. That's why I see world over copper for a therapy purpose has yet not been too much, or we don't have experience in therapy, of course. We are only at present doing diagnostic PET. So we have to just little bit see, sir, what will happen is this copper tete-a-tete has come, like copper tete, like DOTA. So something like if copper can be labeled with some of the somatostatin receptor, that could be, or copper with PSMA, that could be giving rise to better targeting, in my belief, rather than copper chloride alone. Thank you.
Okay, thank you, Dr. Vasu. The next speaker is Professor Radek Zaleski from Poland.
Good afternoon. Can you hear me?
Yeah.
Okay.
Yes, sir.
Yes.
I will try to share my screen. Just give me a moment. Show here. Okay, so I assume that you see my screen.
Probably it's not in full view mode.
Not in full view. I
We're able
cannot
to see, but
As usual.
yeah, it's fine, sir.
It's fine.
It's okay. Right. I would like to see a larger WebEx here. Okay, I think I'm ready. Thank you for giving me an opportunity to show my presentation here. I'd like to show some studies of materials which are designated for controlled drug release. The work is in cooperation with our Institute of Chemistry, and I will show three different kinds of materials. Let me start with drugs, different systems for drug delivery. I think I do not have to convince you that drugs are important, unfortunately, probably. But this is important that we know many drugs for different diseases, but the current studies are focused not on finding new drugs, but on finding better ways to deliver them to where they are needed in a proper time. So there are a lot of materials which can be used as drug carriers. I have shown here a few examples. What I'm going to focus on is 1D material, which is shown here, but not this kind, but silica material, mesoporous material. This is also the same, and some polymeric materials. So I will show you the difference between immediate release dosage, which happens when the drug is given without any carrier. It is given in a pill and you take it. So there is a quite fast increase and then decrease when the drug is removed from the body. There is a concentration of the drug which is the best for the treatment. This is between the minimum effective level. Below this concentration, the drug has no effect, but the upper upper limit of this concentration is minimum toxic level. Above this level of concentration, the drug can be harmful. It is it is toxic simply. So you have to take a drug, maybe even exceed this minimum toxic level for a moment, and it is working. It is curing in this time, and then it is removed from the body, and then you have to take once again and twice again this drug to keep the drug concentration in these limits. So the better way is to use a drug carrier, which allows to keep a maybe not such a constant level, but possibly constant level between these lines between minimum effective level and maximum toxic level. So you have to take next dose, well, 4 times. It takes 4 times longer before you have to take next dose. So this is what are advantages of such approach. The drug of the concentration of drug in the blood is more or less constant, so you do not exceed this minimum toxic level. You do not have to administer the drug so often. So this is much more the comfort of the patient is much larger, much better. You do not have, for example, waking during the night to take next dosage of the drug. In this way, the treatment can be shortened, and the cost of the therapy is also maybe also lowered. But this is also a disadvantage because the manufacturing cost of such a drug delivery system is higher than simply manufacturing of pills with a drug. And there is a danger of overdose because if you take another dosage of the drug before until this first one is removed from your body, it is difficult to remove it, and it can be overdosed. And this is also there is also a delay in if the dose has to be reduced, so it cannot be done so fast. But these disadvantages are probably much less important than advantages. So most of the drugs which we use now these days are use such controlled release formulations. And the first mechanism of drug removal from the drug delivery system is simply by diffusion of the drug in a solution, in water simply, in a solution which is in our stomach, for example. Because I'm focused on the drugs which are taken through the mouth to your stomach. The first drug carrier is so-called SBA 15. This is porous silica matrix, which is prepared with tetraorthosilicate, and the template, which is polymeric pluronic P122. So this is the template. The silica builds on this template, and we have such honeycomb-like structure. So there are pores with the size of few nanometers in the form of such long tubes, which you can see here. It looks, our drug carrier looks like this in such magnification. So there are some needles, some silica needles, which such porous tubes, so pores in the form of tubes. Then we add the drug to this silica matrix. The drug is simple. This is well-known diclofenac sodium painkiller. We are focused on the matrix, on the system of drug delivery, not on a specific drug. So I will always show the results for this diclofenac sodium. And then this is administered from a solution, and then we try it and press with the pressure of 16 megapascals to make such tablets. This is a tablet, typical tablet which can be swollen, taken, and this is the powder between before pressing the tablet, and this is the tablet after such using a press. In microscope, and magnification, it looks like this. There are needles when the drug carrier is in the form of powder, and after tableting, it looks like this. Then we do not see needles anymore. The needles are very small. They have a few micrometers, and this is more or less uniform structure. At larger magnitude, we can see the same silica needles, and there is no sign of them after tableting. But what about the pores? Are the pores destroyed? Because there is a clear change in the structure of this drug carrier. So we used nitrogen adsorption first to find this. We have this matrix in the form of powder. This is the red curve. This is nitrogen adsorption and desorption isotherms. After tableting without a drug, this is the blue one. And with the drug, the matrix in the form of powder, this is violet or purple, and green after tableting. So you can see that its porosity decreases. You can see the specific surface here. So after tableting, the decrease in the surface is not so large, and also in decrease in total volume here. When we administer the drug is added to the matrix, you can see that most of the pores are filled with this drug. So we have a significant reduction in the specific surface, and half of the volume is occupied by the drug. And when it is tableted with drug, so we can see further decrease in the surface and the volume. The pore size distributions look like this. This is the distribution of pore sizes before tableting and after tableting, red and blue. So you can see that the size of the pores is mean size is decreased, but still we have a lot of pores after pressing this material with 16 megapascals. And when the drug is added, this looks more or less like with
after tableting of empty matrix, and when this is tableted, there is a further decrease in the volume, but the size is almost the same for these three matrices. For these three systems, because it's not only matrix but also matrix with the drag. So we used positron annihilation lifetime spectroscopy next for three samples this time: the carrier, tableted carrier, and carrier with the drag also tableted. You can see the lifetimes here. The lifetimes are quite long. They are about 100 nanoseconds. There are also some components with shorter lifetimes. You can see the difference here. The lifetimes with a few nanoseconds. I will discuss them in a moment. To find the sizes of the pores, we use a model. Probably some of you know this extended Taldrup model, so I will not describe it in details. It uses well-known Taldrup model, but extended by the excited levels, and it uses quantum mechanical probabilities of finding positronium on these levels, and the occupation which comes from the thermal distribution of positronium occupying these levels. And then there is a simple calculation of the volume, which uses this formula to find lifetimes and volumes from, pore sizes, and their volumes from lifetimes distribution. So from this lifetime distribution, we have such a distribution of pore sizes, so-called PSD, pore size distribution. And we see that the sizes of the main pores, there is an effect of positronium migration, but I will not focus on this. The sizes of these pores are not changed neither by tableting nor filling carrier with the drag. So we have similar sizes of the pores. There are some pores are filled with the drag. This is the component which is characteristic for silica walls, which is in the carrier and tableted carrier. But when we add the drag, it is the most of positronium annihilates in the drag, not in the walls. This probability of trapping positronium in a drag is higher. There are two characteristic peaks. This is peak characteristic for a drag, so it is in the form of quite large clusters, which are large enough to host positronium, not finely dispersed. And this is probably on the interface between a drag and silica. So this is a little bit different than silica itself. Then we use UV-VIs, this spectrophotometer, to find the rate of the release of diclofenac sodium. We are focused on this peak with wavelength of 276 nanometers, and the height of this peak gives us information how much drag is removed when it is submerged in the phosphate buffer solution R1. This is typical for such measurement of the rate of the release of the drag. This is, well, it simulates fluids in our body with such parameters during the test. And we find that the drag itself is removed without
and carrier it's removed, well, it is dissolved within a few tens of minutes before 1 hour, shorter than during 1 hour, and then it is there is from the matrix it takes a little bit longer, but when the drug is tableted, it takes much longer time. We are expecting linear increase to the most well. We would like to have a linear increase, but only 30% of the drug is removed during after tableting. So a lot of it is trapped inside a matrix. It is a little bit faster, a little bit not. It's the speed is similarly the same, but much more the drug is removed when tablet is fragmented. Why it happens? We used EDS to find elemental distribution on the in the tablet. This is the cross section of the tablet. We cut the tablet along its diameter, and this is upper surface of the tablet, lower surface of the tablet, and this is the middle of the tablet. So we have studied two elements, chlorine and sodium, which are present only in a drug. So we find that only in the distribution along the tablet is more or less uniform. There is a peak because the tablet is there is some non-uniformity of the matrix here. What happens after 24 hours of drug removal? The chlorine is removed from whole tablet, but mostly from its surface. We can see that it's removed in the ionic form because sodium stays in this layer on the close to the surface. So when you look at it's far from here, this part is only removed and sodium remains. This is diclofenac sodium. There is also phosphate from the buffer, which is also absorbed in the matrix. So when the tablet is crushed, this surface area of this surface of the fragments of the tablet are much larger, so a lot of much more drug can be removed from the tablet. The positronium porosimetry shows this process. We've got lifetimes here and pole size distribution, PSD on the right. We use this extended group model to transform this after 6-hour blue, before drug removal, 6-hour green, 12 hours violet, and orange after 24 hours. So we see that we have drug still after 24 hours in cluster large enough to host positronium, but the size of the pores is slightly increased with time of drug removal. So probably the drug is the surface of these clusters, which are in the mesopores, is removed, the clusters become smaller and smaller, and the pore space increases, so the size also increases. What are the conclusions? The drug is located in mesopores, not on the surface of the carrier, which would be much worse. The clusters are large enough to host the positronium, what I said already. Tableting does not destroy mesopores, but some of them are closed. The positron porosimetry see them, but not the nitrogen absorption. This is how we know that mesopores are closed. Tableting slows the release, but the amount of the released drug is also decreased. The solution penetrates entire volume of the tablet, what we have seen from EDS, but the drug is most effectively removed from the outer layer of the tablet. And the tablet fragmentation increases the surface area of the outer layer and accelerates drug removal. I'm sorry, how much more time I have? Because I do not know when I started.
Thank you, Professor.
Do I have more time or not?
We can give another 2 more minutes. Time is already over, but I can give you another 2-3 minutes.
Because I have, well, two more drug carriers. I can say about one or two of them, but how much more time? A few minutes, right? Do I hear you correctly?
5 more minutes.
Few minutes. Okay, so I show one more carrier, drug delivery system. The other drug delivery way of drug removal from the carrier is through the swelling. This is characteristic for polymers. We used for the first study, I will not show the last one, the simple polymer matrix XAD7, which is commercially available. And first we have filled it with 3%, 3 mass percent of diclofenac sodium, and the other part was filled with 50% of diclofenac sodium. So there are EDS results. When there is a small amount of the drug, we can see such distribution. The drug is located mostly on the close to the surface. This is also the cross section of the tablet. And this is the middle of the tablet. There is the smallest amount of the drug, and this distribution changes linearly. When we have 50% of the drug, the distribution is much more uniform, but some drug stays on the surface of the tablet. We have results from the nitrogen porosimetry. This is the result for original material for the matrix, and when we add the drug, we can see that the pores are much larger. Also in the case of the positron porosimetry. This means that adding the drug in a solution causes that the polymer is swollen. It increases its volume. So the drug can be also placed within the between polymer chains. We can see from the positron porosimetry, this is the distribution, quite complicated of small free volumes. This is also characteristic for polymer. There are probably continuous distribution of free volume sizes. They are not pores, they are smaller than pores, according to the definition. And this is not changed significantly with 3% of diclofenac sodium. This is blue. There are different widths of the peaks, but it's well, the method of analysis is not sensitive enough to take the widths into account. But when we have 50% of diclofenac sodium, then we have such distribution, which is characteristic for diclofenac, which we have seen for SBA 15 as a carrier, and some of micropores are filled. So we have some clusters of diclofenac sodium, and some of micropores or larger free volumes are filled with a drug. The volume of mesopores is significantly decreased, not the size, which is the same for 3% and 50% of diclofenac sodium. So this is total volume which increases when small amount of diclofenac is added. So this is another proof that we have that the material is swollen. And also the surface and mean pore diameter increases, so the structure of the polymer is changed. But when we have much larger amount of diclofenac sodium, these parameters decrease, except the diameter, which increases further. So the pores are mostly, at least mesopores, are mostly filled with a drug, with the drug. Only largest mesopores remained open. What is the release rate? This is what you have already seen. Diclofenac sodium is removed fast. When we have 50% of diclofenac sodium, the release is a little bit slower, but not slow enough. We have we have so-called burst release at the beginning. So this is the drug which remains on the surface of this polymer spheres is removed first, and then we have slower removal from the inside. When we have a small amount of the drug, the release is much much better, but amount of the drug released is smaller. But well, we have make a larger pill and to take advantage from this slow release. And the conclusions are written here. The concentration at 3%, at the concentration of 3%, this distribution decreases linearly from the surface to the center. Drug is finally dispersed. We do not see such component in positronium porosimetry, which is characteristic for clusters of the drug, and the release is relatively small. At 50%, the distribution is uniform along the radius, but we have drag on the surface in large cluster. Probably there is a layer on the surface of these microspheres of the polymer. Yes, this is microspheres, not a tablet. I said this before. And all drug is released, but burst release dominates. At both concentration results, drug introduction results in swelling of the microsphere. So I do not have time for the last part, and I will stop here. If I had time, I could say about composites, but I will end here. Thank you very much.
Thank you, Professor. Now the paper is open for the discussion. Any questions? It's a question from Dr. Pagowal.
Hello. Just I had a question for a hydrogel of spherical geometry. Over a period of time, the diffusion length will increase, isn't it? With time, as it swells, the diffusion length will increase. So how one assures that the rate of release remains the same?
The rate of release remains the same. I do not hear exactly what you say. For which carrier?
For hydrogel of spherical geometry.
Okay, for this.
Go ahead, back. One slide back.
Previous one.
Previous.
Previous.
Previous one, yeah.
Yeah. Go ahead.
Yeah.
No. Go ahead.
Here?
Ahead. Go ahead. No. Yeah. Previous. Yeah.
Well, I'm sorry, but your voice is there are breaks. It's the sound. I do not see.
Yeah, because see, as the hydrogel swells, now the drug has to move from core to surface. It has to go a long distance. So how do you assure that for a period of time, the rate of release remains the same? Just by swelling.
I'm not sure in which case. In the case of SBA 15?
Spherical geometry.
In spherical geometry. So the spherical geometry is here.
Yeah, here. Once.
Okay. And how
Okay. If there is no question, we thank the speaker for his excellent lecture. Thank you, Professor.
On
I'm
behalf of
sorry.
the organizing committee,
Professor, thank you, Professor, for your lecture. Now the session is over. Thank you.
on behalf of the organizing committee, I'd like to convey sincere thanks to Dr. S. Kannan, Associate Director, Radiochemistry and Isotope Group. Now I request all the guests to join for the tea, which is arranged downstairs, and we'll be reassemble here around 4-5 p.m. IST. Thank you very much. Welcome you all to the third and last session of Day 1 NPMMI 2022. I take this opportunity to introduce the chairperson of this session, Dr. S.M. Yusuf, who is presently serving as the Director of Physics Group PRC. He is also a fellow of the Indian Academy of Sciences and National Academy of Sciences, India. He has also served as the Director, Institute of Physics, Bhubaneswar. His area of expertise is magnetism and neutron scattering. With this brief introduction, I request Dr. S.M. Yusuf to kindly chair this session. Sir, please take this. Yes.
A very good afternoon. So this is the session 3 of the first day of this team meeting, and we have 3 talks, 3 invited talks. Each one is of 30 minutes duration. So 25 minutes for presentation and 5 minutes we'll give for discussion. So I'll give some indication after 22 minutes or so that another 3 minutes would be there to wind up, so that we get after that 5 minutes for discussion. And first speaker will be Professor A. Wagner from Institute of Radiation Physics, HZDR, Germany, and he will be talking about positrons in material sciences, intense beams for defect studies and applications. Dr. Wagner, please.
Thank you very much. Can you hear me?
Yeah, very much.
Okay, thank you very much. So welcome everybody, and I thank both of the organizers for the possibility to present our work here. Even when the times are at the moment really difficult here in all over Europe, you see on top, this is the Brandenburg Gate, which is illuminated in the colors of the Ukraine flag. And with having a war just a few hundred kilometers from here, and also Russia attacking actually the largest nuclear power plant in Europe with tanks and missiles is really not giving us a very, very nice time here. But beside that, I hope you will enjoy what I'm going to present today. So as has been said, it's about positrons in material science, and I will give you some applications about our facility. The facility we are operating is located in Dresden-Rossendorf, and it's run by an accelerator, which serves as a high-intensity positron source, which feeds several beam lines and also other types of radiation, but I'm going to talk only about positrons today. And with these secondary positron beams, we are doing mainly material science related investigations for a broad range of applicants and users from all over the world. I will show you some examples of these applications, and also maybe if time allows, I will give you an outlook about the next facility we are planning at the moment, and which hopefully will become online by the end of this decade. So the ELBE Center, ELBE is an acronym standing for Electron Linear Accelerator with High Brilliance and Low Emittance. This is a center for high power radiation sources, which contains mainly a superconducting electron machine. And this electron machine drives via either undulators, secondary infrared beams. We produce coherent terahertz radiation also for material physics. Positrons, as will be the main part of this talk, but also neutrons for nuclear physics related research, for example, in nuclear transmutation, and secondary by scattering high intensity lasers, also secondary X-ray sources. Electrons can be used directly as a beam, but given the intensity of the accelerator, this is usually not performed because it's just too much of flux. And we also have a secondary gamma ray source, which I will not cover today. The size of the facility of the installation is about the size of the Taj Mahal Palace in Mumbai. So I always try to pick some, let's say, known example from the audience. So it's about 110 meters long. It's almost exactly that size. The accelerator actually is being used to drive an electron beam, as I said, typically with energies around 30 MeV and average currents at about 1 milliamps. So it's about up to 30 to 40 kilowatts of electron beam power, which we convert into Bremsstrahlung by using a high Z material as a converter. And then any secondary produced positrons via pair production are being moderated in a thin foil and then re-accelerated and transported magnetically towards the sample in the end. There has to be some, let's say, beam tweaking in between in order to maintain a high timing accuracy. The timing accuracy of the electron beam is less than 10 picoseconds of bunch width. So this gives an excellent source of high time resolution investigations with high fluxes. And what we operate is a positron user facility. So we are not totally aiming at our own, let's say, in-house research, but mainly to offer this institution or offer this beamlines as user facilities for people all over the world, who can apply on a certain scheme for beam time. And once the beam time is being granted by an international advisory committee, people come or during the last 2 years remotely send their samples and get that analyzed in our facility. So the main workhouse is the monoenergetic positron source, which goes back to original ideas and also had been set up by the university in Halle by Reinhard Krause-Rieberg's group. And with him, we are operating at the moment the facility. As I said, we have around 1 milliamp. Here's a bit less because the repetition rate is less than the normal one for the accelerator. A bit less driving beam, but it still offers an enormous activity or usable event rate at the detector. So once the beam, you have seen that before. Actually, the facility looks like this. You can see it also in my back behind me. And typically we get up to 250 kilocounts per second event rate. So that means for a typical positron annihilation lifetime spectrum, it takes about 80 seconds. And we do every processing of the data from or the signals of the detector via fully digital setup and online processing of the information. And with this, we can really get to such high, let's say, spectrum production yields. And with this also dynamic effects, for example, migration of hydrogen. I will show some examples later. And annealing and formation of defects over time can be studied with up to now unknown timing resolutions and also speeds. We have also for secondary or for complementary research doing Doppler broadening spectroscopy. Remember, please, Reinhard Krause-Rehberg's talk in the morning where he had shown both positron lifetime and Doppler broadening spectroscopy. Here we operate the thing with an intense sodium-22 source, which is not connected to the accelerator, which has the advantage that we can use it all over all the time, whereas the positron source is in competition with the other radiation sources at the facility. So this is how it looks like in figures so that you get an idea how colorful this is also in reality. For the accelerator-based source, the nice thing is that we can match actually our repetition rate of the beam because it's a superconducting machine. So it runs the radio frequency of the accelerators on all the time. And we can inject electrons into the machine as we want. And depending on the estimated lifetimes or the envisioned lifetime, you see here on the right-hand side of the figure in blue, this is a highly porous low K material. I'll come to this, what that is in later. with lifetimes which are beyond typically 10 to 50 nanoseconds, can be covered without having the problem of pulse overlap of previous beam pulses. Yeah, so this is important technology-wise or from the methodology, important for measuring long lifetimes and porous materials or metals and everything which has short lifetimes as well. The facility has been extended over the last years to include also a secondary setup on top. You see here the first thing is the standard setup here on the lower section, and the upper part is now having a facility where ion beam implantation, or actually ion implantation, not ion beam implantation, gas loading, and things can be done to the sample where we can do in situ studies of defect evolution in the materials. The converter, which converts the electron beam into high energy X-rays, is shown here. This is a water-cooled, high-pressure tungsten foil-based converter where the electrons beams are as much as we can being converted into high energy X-rays, which in turn produce positrons. You see the stack of the converter here up there. At the moment, for those who had been with us and did some experiments here, we are at the moment constructing a new sample chamber at the setup in order to get much larger diameters, in order to reduce backgrounds from backscattered positrons, which typically annihilate somewhere in the surrounding of the target. We want to get to higher positron energies. At the moment, we operate between 0.5 kilo electron volts up to 16 kilovolts of beam or secondary accelerated positrons in order to do depth scanning. We want to get a little further down into the material. But most important, there will be a load lock with 12 sample repositories so that we don't have to break the vacuum. At the moment, you have to do that anymore when changing one sample to the others. And you can imagine when you have one measurement, which takes 80 seconds, the most of the beam time is actually spent by exchanging samples. And this is one thing we want to change. Cooling and heating will go from 50 to 900 Kelvin. And there's also some ample access for illumination, irradiation, and things like this. So that once you have an idea how your sample should be treated during operation, you can contact us and yeah, we get into contact. Now let's come to some positron science cases. Priya asked me when she invited me, or you invited me to the talk, to give an overview about applications, what you can do, and where we may also have some industrial users. I'm coming to this at the very end. So as I said before, for the long lifetimes, typically applications range from porous glasses, membranes, for example, for gas separation, metallic organic frameworks. These are things which have a high porosity material, just as we have seen the application by Radek Zaleski, who has talked before about porous media for drug recovery, release, or before. Low-K dielectrics, so these are for CMOS devices. The idea is to also produce porous media in between the conductors of a chip in order to reduce the overall K, or for physicists, the epsilon, the dielectric constant of the material, in order to go to higher speeds in switching and also to lower power consumption. Lower power consumption is also something for magnetoionics. This is one of the, let's say, most successful stories we had in the last 2-3 years. So I'm going to present this a little later, what that is. Lean back for this. We also, through ion irradiation, had experiments where, for example, here, iron rhodium lattices had been deformed by ion irradiation and where phase changes and transitions between paramagnetic ferromagnetic states happened. Now with the, let's say, outcome of the at least in Germany, the change in the energy production and consumption, hydrogen becomes a more and more important material. And there are studies about the hydrogen-induced vacancies, for example, in nickel had been done. So this was with a group from Japan, where we studied over time the evolution, now with having the high repetition rate of the beam, and high sample, let's say, rate, we could study dynamic effects in the annealing and diffusion of hydrogen inside nickel for example, storage or even sensor applications. Sensors also in, for example, optoelectronics, in non-equilibrium, for example, tin, germanium alloys. This is an important aspect for future optoelectronics devices, because here the stoichiometry, or the whole thing is governed very much by vacancies which are forming in the material and which change the optical properties, for example, of sensors based on germanium tin. Niobium hydrides play a role in superconductivity. You see here a superconducting accelerator piece here, which is being used in many accelerators right now. For example, the European XFEL in Hamburg, but also our own machine, which is a niobium-based superconductor at 4 Kelvin temperature, and where the formation of hydrides at the surface, which we found out very much influences the quality factor of these resonances. And by knowing how these migration happens, and how it's being influencing the quality and the performance, you can actually try to mitigate that and get to higher efficiencies. And this plays either you can increase your energy of the accelerator or also the average current. And last not least, this was an experiment we just did this week, microsolid oxide fuel cells. So again, something which is related to energy production, energy consumption. Yeah, now let's take a tweak, or let's go a bit more in detail into what I call the magneto-ionics, or what we call it. So these are basically the idea that you want to have a device which can either store or process information without the need to use a current flowing, because a current always means there's a power dissipation. So the best thing, or a better thing, would be to have just an applied voltage which changes a state. In this case here, this is either magnetoionics in cobalt oxide, changing the states of the film from ferromagnetic to paramagnetic without having to apply a current, but just the voltage. Yeah, you see here when we have some voltage applied here across this electrolyte. Now, in this case, it's a liquid electrolyte here. We change the oxidation state of the cobalt oxide here, and with this one we can transfer. You see here. The black one is the paramagnetic, and the other ones are the ferromagnetic states. And with this one, with this technique, you can envision that in the future you can have a low power long-term either information storage or things like a neuro simulator, for example, mimicking the functioning of the brain. And all these are influenced very much by open volume atomic defects and grain boundaries. So that means there is a defect-induced magnetism inside this material, which is, let's say, resolved by positron annihilation lifetime spectroscopy and also Doppler broadening spectroscopy. Yeah, this was the second initiative, or a second game opened in exchanging the oxygen to nitrogen, and we also have been done experiments on nitrogen magnetoionics with cobalt nitrides, which offers a faster and more stable magnetic switching, and where we found out that there's no grain boundary related transport, and so this has helped to untangle what the material properties in such a device would be. And there was quite a fruitful number of publications in high-ranked journals about this. So I'm skipping, let's say, the details of this, how this being worked out. And basically, this was one of the user-driven experiments which had taken us quite some experiments over time, and where we think positrons made a significant impact. Now, in order to make use of this, some technical issues are, for example, consider here in the upper part, you see these porous structures, which offer very long positron annihilation lifetimes. You see that the facility we have offers a tremendous signal to background crispness of the signal. And what we're interested, of course, is the deconvolution. You have heard this from Reinhard's talk, deconvolution into different components, lifetime components here, which can associate it or attribute to different kind of porosity inside the structure. But this means we have to compete also, or we have to deal with a relatively high signal processing speed. And when you imagine that in a signal digital processing, you can generate with an with a state-of-the-art ADC. So we employ 14-bit ADCs with 2 gigasamples per second rate, which is necessary in order to get a high timing resolution. We end up with a data rate of about 1.1 gigabytes per second, or about 100 terabytes per day, which is as much as the full Atlas detector at CERN delivers. Of course, they also have data reduction, so it's not a really fair comparison. But it's obviously that one cannot store this kind of information directly from the experiment. So there has to be some online reduction and online analysis of the data. And this is what the work by Eric Hirschmann, who is a PhD or was a PhD student in my department. And with this one, with a highly parallelized data procession, we ended up in reducing very much the data rate. And now we can cope with even up to megahertz data processing rate in these kind of experiments. We're also applying this in medical physics, but this is another different issue. Now, one other physics topics is gallium oxide. Again, important for sensors applications, for example, where in collaboration with Bowling Green University in Ohio, Berkeley, Los Alamos, we have studied also the annihilation lifetime distributions in beta gallium oxide, and learned, for example, depth distribution, and also with different intensities of hydrogen decoration of gallium vacancies, how the electron mobility, for example, inside this material changes. So this is again something which is of importance for semiconductor industry, sensing, and future devices. Also, of course, at high temperatures, as we have heard by Akira's talk in the morning. Yeah, so the future will hopefully bring us a new extended facility. So we call that DALI, which is the short for Dresden Advanced Light Initiative. Again, a multi-beam facility, which basically drives not only a VOV coherent X-rays, or sorry, VOV coherent source, but also infrared and terahertz sources. And by doing this, we employ also, again, a high intensity electron beam, which can serve mainly, take it as a beam dump, as again a source for high intensity secondary positron beams. And there was, we are working at the moment, this will be a facility in the ballpark of around 200 million investment, working on the conceptual design report for this facility. And hopefully this will become reality in the future. One future thing we are hoping for is to use not only normal positrons, non-spin polarized, but to extract by starting with spin polarized electrons, then again polarization transfer onto the X-rays, and then through pair production again to the positrons. That sounds complicated, but a group in Jefferson Lab has shown that it works. Extract also a spin polarized secondary positron beam with varying intensity. And there, of course, one additional degree of freedom will open up. So many magnetic effects which are present also and will be present in future, for example, magnonic devices, spintronic devices, will become accessible, because now you have the additional degree of freedom of looking for the interaction of positrons with either the vacancies or some magnetic states at the surface of semiconductors, or in film semiconductors, and understand how this can be employed for future devices, for example, in magnonics, where the information transport is no longer through the electrons, but through spin waves in a device. And this is an upcoming and emerging field. And also in our institution at the Helmholtz Center in Dresden-Rossendorf, there's a large activity in this kind of research for spintronics. Yeah, and with this, I'd like to come to an end. I give credit to not only my colleagues from Dresden-Rossendorf, but also from Martin-Luther-Universität in Halle. As I said, Reinhard Krause-Rehberg drove this effort from the very beginning. And we have, and this is only a very small list of collaborators who have been working with us in the last few years to do nice experiments and also produce a lot of nice papers by applying positron annihilation in the scientific fields. One of the things, because Priya has asked me also to talk about, let's say, technology transfer. We don't have too much of, let's say, high-level industry users. Sometimes they are a little reluctant to come to large-scale facilities because it also means a lot of work. And for a state institution or a federal institution like we are, we cannot actually make money by serving companies. And this is why we have funded a subsidiary, which is called HCDR Information, which actually does that for us. So any kind of applications where there is a non-publishable, because the companies want to keep their knowledge secret, we can offer this also on a paid level. And it's at the moment, it's not that much, but it's in a growing field. And we hope that in the future, the technology transfer and methodology for small, medium-sized companies up to larger companies will become available. So with this, I want to end and thank you very much for your attention.
Thank you very much for a very clear presentation and bringing out the importance of these positrons. And now it is open for question, comments, discussion. Yeah, before I take other questions, probably I can start. I have one question. See, you talked about cobalt 304 and it is magnetoionics. Now, is it due to the surface effect or it is the entire? What is the thickness of the film you are talking about? And when you talk about the ionics, is it that only surface is getting affected? And the magnetization data also, which you showed, it is M versus H. But I wanted to know magnetization as a function of temperature, whether only the Curie temperature is getting decreased from, I believe this is a room temperature. It may happen that only TC is decreasing. So at room temperature, it appears to be paramagnet, but may not be so. Could you kindly clarify?
So we did not do temperature dependent. So of course, these are all room temperature measurements, which we did here. And so the migration, so the application, of course, was, let's say, in situ of the material. And so I'm not aware of how the, let's say, higher temperature behavior of such a thing will be. I mean, the good thing is that since we don't have a current which is applied here, and there's a low power consumption in this future device. I mean, we don't have a device yet, but in the future it will mean that we will still stay at a moderate temperature. So it's not like in a normal CMOS semiconductor that due to the current you get heating up of the material and you have to, for example, what I showed before, this gallium tin alloys. Of course, the problem is that above, let's say, 200 degrees or so, the tin migrates and forms local clusters. So the alloy is, let's say, disassembling. And so we hope that, or we think that in this case here, due to low power, it does not play a role. But you're right. I mean, this is one thing one has to solve before that thing becomes a device. Yeah.
Yeah, thank you. Another quick question from me. The positron polarization, how do you achieve? And what is the polarization maximum you have achieved?
Okay, so first thing, there was a second part of your question where you asked whether this is a surface effect or not. Yeah, of course we studied. I did not show that. For example, with electron energy loss spectroscopy, we looked in the depths of the material. So this is not a surface effect, but this is inside the material here. And we also know that the magnetism is not a surface effect, but it comes from the, let's say, about 200, 300 nanometer depth of the material. So this is now here, this was a variable energy positron annihilation Doppler broadening spectroscopy. As I said, this was a beam-based thing. And here you can see how the depth dependence is. Yeah. So, and now for the polarization degree of freedom, as I said, the to produce a secondary positron beam here had been shown by an experiment which took place about more than 10 years ago at Jefferson Lab, where they have used a 6 MeV electron beam. And as I said, they produce polarized electrons, hit a target, which converts into polarized positrons. So this is the spin transfer. And then you select the spin degree of freedom. And there's like a figure of merit. You see this here in red. Unfortunately, this is at the maximum. It's covered here. So the polarization degree of freedom is about 80% of that secondary beam. And they have also shown that when you decelerate and moderate the beam, which you of course should not do in a magnetic material, then you can keep that polarization degree of freedom of the secondary positrons. So it's relatively high and is comparable to for example, sodium-22 based sources or gallium-based sources, where they, of course, due to the parity violation, they also have a polarization degree.
I'll take another question from.
Hi, Professor Wagner. This is Priya. Thank you for your wonderful talk. So I have a small query regarding the magnetization. So the magnetization depends on the vacancy size or concentration. Do they have some correlation with that? I mean, the size of the vacancy and concentration. How does magnetization behave?
This I think I cannot really answer because I mean it was always that we did not do these experiments in situ. Like for example, changing the magnetic field while doing the positron studies. Yeah, so this is I'm not sure how one can. Well, at least we cannot do it because there's always a magnetic field present in these experiments.
Okay.
The question about for example, if you correlate, for example, in VPAS here, you see when you have a different voltage being applied, you see here the change for the low momentum fraction. So in that sense, also if you want the defect concentration issue, yeah, how this affects the states. And you see here, if you carefully look here, we start with an S-grown film. That's one, the black one, yeah. Then we do the voltage application, so changing the state from para to ferromagnetic, and then we go back and recover this. So this not entirely goes back for the first cycle to the original level here, but it comes close, yeah. And this is actually one of the things, how many thousands of cycles this thing can undergo and how stable that is. You know, but it's like the first steps.
Is there any other question?
Thank you.
Comment? Yeah, this is the last question.
And yes, this is Pradeep here. You
Hello.
know, the first slide, hello. The first slide you had shown the laser with, you know, the photon source you had mentioned.
Yeah.
Is it inverse Compton scattering business is there? Laser you're giving to the electron beam?
Yeah, so there was a few years ago we did that. So we scattered the electron beam from the laser beam. Yeah, this was when we started to install. Maybe I don't have really the facility layout. Let me check because it's just a second. Almost there. So this is the layout of the facility, and you see that we have not only the accelerator part, but we also have, let's say, like a high intensity laser here. And we scattered off the 500 terawatt laser beam of a facility called Draco off the electron beam here. And with this one, we generated backscattered X-rays. But at the moment, it's actually, because the repetition rate of such a laser is relatively low, actually the more X-ray intensity you get when you scatter off this high intensity laser light from electrons, which are again also accelerated by the very same laser by means of it's called a ponderomotive acceleration of the electrons, because there the local densities of electrons is orders of magnitude higher than what you can do with an accelerator. Yeah, so we are transiting at the moment from, let's say, the secondary X-ray sources from the large-scale accelerator towards a laser or laser electron laser scattering. Yeah, so this is.
Thank you. Thank you. Thank you, Professor Wagner, for covering this very fascinating field. And there are lots of opportunities I can see. And thank you so much for a very interesting presentation. So with this.
Thank you very much. It was a pleasure.
Thank you. With this, we'll move on to the second talk of this session, and it will be delivered by Dr. S. Avaya from Material Science Group of IGCAR Kalpakkam. Title of the talk is Understanding Defect Behavior in Nuclear Structure Materials, Insights from Positron Annihilation.
Screen only, right? Share content. Share content. Screen. What do you want to share? Content. That screen you open window.
Hello. Can you hear us?
Just a moment, sir.
Yeah.
Yeah. So the share content. Okay.
So is it visible?
No, not yet. You are visible, but not your presentation. You need to share it.
Share the screen. Escape.
Just a moment, sir.
Escape. Share the screen.
Okay.
Meeting in progress.
Here, that Google Meet.
See, at the bottom, there is a square button with.
No. You select that window.
Window.
Then select the PPT and share it. Now, yes.
Now share it.
Now is it visible, sir?
Yeah, please go to full screen view.
Yeah, it is already in full screen, sir.
Okay, that it is not presentation mode.
It is already in presentation mode, sir.
Okay, it may take. Is your slide changing? Could you go to next slide and see whether changing or not?
Yeah, I'm able to change here. You're able to see the changes there?
No, that is what I anticipate.
Go back.
Dr. Abhaya, please share the screen instead of window.
Okay, sir. Okay.
Once stop the screen and go to the share again and share entire screen instead of window.
You have to share entire screen. That is what the mistake.
Stop sharing the screen once and again use the share button and select the screen, not the window. Which comes
screen.
Which comes by default. And go to share. And now,
now
that's
it is
great.
fine.
Continue.
Yeah. Okay.
Now is it okay, sir?
Yeah, pretty much. Yeah, please start.
Okay. So at the outset, I would like to thank the organizing committee for giving me an opportunity to present our work in the Positron group at IGCAR. So the title of the talk goes as Understanding Defect Behavior in Nuclear Structural Materials. And I would like to acknowledge Dr. Amarendra, Rajaraman, Ranjit, Raghunathan, Pramila, Arun Kumar, and Haribabu Sata for their contributions. So the outline of the talk goes as follows. I would like to give a very small introduction about the positron annihilation spectroscopy as such. Then I will move on to the positron related works that we have carried out on the austenitic stainless steel, then the ferritic martensitic steel, then the ODS, then coming to the high entropy alloys, then finally on to the cesium doped iron phosphate glass. So basically what we have here is the electron-positron annihilation. It forms a basis for the positron annihilation spectroscopy, wherein we get information about the open volume defects in materials. So we have this Na22 as a source of positrons, and it gives out positrons via the beta decay process. And the energy of the positrons varies, say, from 0 to about 545 keV. Because of the varied energy distribution of these positrons, they get implanted at various depth regions starting from the surface up to a depth of a few hundreds of microns depending on the density of the material. And then they get thermalized, they lose energy due to inelastic collisions, then they diffuse, then they get trapped at vacancy defects Then finally, they annihilate with the electrons, giving the 511 keV gamma rays, from which we get the information about the open volume defects. So now coming to positron annihilation spectroscopy, it is basically used for defect studies in bulk materials. So we have the positron lifetime and the Doppler broadening. So as I have already told you, this Na22 source, it gives out positrons via the beta decay process. And along with the emission of the positron, you have the emission of 1.274 MeV gamma photon, which marks the birth signal of the positron. And once the positron enters the sample, it annihilates with the electron, giving out 511 keV gamma rays. So this marks the death signal of the positron. So the positron lifetime essentially comprises of getting the time difference between the birth signal and the death signal. And this positron lifetime is inversely proportional to the electron density that is spanned by the positron at the annihilation site. So a typical positron lifetime spectrum looks like this. So you have a Gaussian, then over that you have an exponential that is riding over that. The slope of this will give you the annihilation rate, and the inverse of the annihilation rate will give you the positron lifetime. So as you can see that as you increase the number of vacancies in a cluster, we see that the positron lifetime slowly increases and then it saturates at about 400 picoseconds. And this Doppler broadening spectroscopy, again, it's a very important technique wherein we get the electron positron annihilation, which is that 511 keV. So this is that Doppler broadened spectrum, and the Doppler broadening is arising because of the finite momentum of the electron positron pair. And what we get here is we basically get two parameters, S and W. This S basically characterizes the annihilation of the positrons with the valence electrons. And the S is mathematically expressed as the counts in the peak region to the total counts, whereas the W parameter is characterized by the counts in the wing region to the total counts. So what happens is that in presence of the vacancy type defect, the S parameter will increase. There is narrowing of the Doppler spectrum, and this S parameter will increase. And the W parameter will give you information about the chemical nature at the annihilation site. So if you can see here, the Doppler broadening spectrum, which we have obtained for the well annealed nickel, as well as for the 25% cold work nickel. So what we see here is you have a narrowing of this Doppler spectrum for this 25% cold work nickel because it contains cold work induced effects. Now coming to the variable low energy positron beam setup that we have in our lab, this is the photo that shows the variable low energy positron beam, which was indigenously developed in the year 1997. So actually you have a very strong Na22 source, and from the moderator, the tungsten moderator, we get slow monoenergetic positrons, and these slow monoenergetic positrons are transported and they are guided through the beamline to the target chamber, which contains a high voltage feed through over which we have mounted the sample. Now here you apply a negative potential, say from 0 to 22 kV, and therefore what happens is that you get the Doppler spectrum for each positron beam energy, and from the Doppler spectrum you get the S parameter variation. So a single positron beam measurement will help you get the variation of S parameter as a function of positron beam energy, or in other words, the implantation depth. So here you can see that this is actually the S parameter variation for the annealed nickel and this cold work nickel. So you can see that the saturation S parameter is higher for the cold work nickel because of the cold work induced effects. Now coming to the positron studies in titanium modified austenitic stainless steel. So here actually this D9 is basically the titanium modified austenitic stainless steel, which is envisaged to be used as the fuel clad and the wrapper in PFBR. And it has a typical concentration of chromium of about 15.2 weight% and nickel of about 14.8 weight%. So what they have done here is they have done a variation of the positron lifetime as a function of annealing temperature to get the defect recovery curve for the 20% cold work, which has, so they have done 20% cold working in titanium free model alloy as well as the sample that is containing titanium. So what we see here is for the titanium free alloy, we see that the positron lifetime it is high at first and then it decreases. So this decrease is actually corresponding to the defect annealing because of the defects that are present here. This is actually the vacancies that are associated with the dislocations, and you have defect annealing of that. Then beyond about 800 Kelvin, you see a hump, you see a second defect recovery stage. And this second defect recovery stage is attributed to the formation of nano-sized titanium carbide precipitates. And then again, beyond about 1200 Kelvin, we see that there is a decrease in the positron lifetime, which corresponds to coarsening of these nano-sized titanium carbide precipitates, and the positrons get no longer trapped in these precipitates, and you have defect recovery beyond the temperature. So we see here that the dislocations, they act as nucleating sites for the formation of nano-sized titanium carbide precipitates, and positron annihilation spectroscopy is able to tag the formation of these precipitates at that temperature. And this is another work which tried to correlate the titanium carbide precipitation to the void swelling. So this is again the same curve which I showed you previously. This is actually for two different titanium concentrations in D9. So what we see here is, again, you have a defect annealing stage, and then you have a stage which shows the formation of the titanium carbide, and then you have the coarsening of these precipitates. But one should note that for the sample which contains higher titanium, we see that the positron lifetime is higher, which corresponds to higher number density of the nano-sized titanium carbide precipitates. And what we see here is they have done swelling studies. So swelling studies, they have irradiated about 30 APPM of helium ions, followed by 5 MeV of nickel ions in these two samples of varying concentrations of titanium. And what we see here is the swelling behavior using the step height measurement is shown to have, that is, you can see that the swelling behavior or the swelling percent is less for the sample containing higher titanium, and that is well correlated with the higher number density of the nano-sized titanium carbide precipitate. Now, coming to the effect of titanium on the defect recovery. So this is again a curve which shows this is actually the this 20% cold worked titanium-free model alloy. So herein we see that it is a very typical behavior of the positron lifetime. So you have a higher positron lifetime. Then as you increase the annealing temperature, you see that there is a reduction. Then finally you have defect recovery beyond about 800 Kelvin. So this is for the titanium-free model alloy. So this is another work wherein they have done 3 MeV proton irradiation in D9 alloy of varying concentrations of titanium. So what we see here is the behavior is going to be the same. But the thing is, if you're going to take the titanium-free alloy, we see that the complete defect recovery takes place beyond about 800. Whereas if you're going to increase the concentration of titanium, you see that the defect recovery shifts to lower temperature. So this only means that titanium addition in the solution enhances the vacancy diffusivity. And since you don't have dislocations, you don't have the formation of this second recovery stage. There's another work which again talks about the creep resistance and the titanium carbide precipitation. So here what they have done is they have done the cold working of, this is about this 20% cold working. And this 20% cold working, they have done it for different D9 having different titanium concentrations. So what they have done is you can see that the positron lifetime more or less does not change for the 20% cold work D9 for any variation in the titanium. But what we see here is once you do the creep testing at 973 Kelvin under a constant load of about 175 megapascal, you see that they rupture at different times. And what we see here is the titanium concentrations of about 0.23 and 0.25 have higher rupture times when compared to the other concentrations. And this 973 is actually the temperature where you have the onset of this titanium carbide precipitation. So here again, they are able to correlate a very high creep rupture resistance for the samples having higher concentrations of the titanium, and they are able to correlate with the higher number density of nano-sized titanium carbide precipitates in the sample. Now, coming to the positron studies on Euro 497 and the model Fe9Cr alloys. So this is basically like this is the work which was carried out to see the defect recovery in this Euro 497. So the initial condition is this. Actually, this Euro 4 steel is this is actually the ferritic martensitic steel, which has a carbon concentration of about 0.1 weight%. And what we have done this, they have done this initial condition is actually it has been normalized and it has been tempered at 1033 Kelvin for about 1 hour. And this sample has been isochronally annealed so as to look at the defect recovery stages. So what we see here is we can see that this is again the hardness measurement. The hardness measurement is a macroscopic measurements. So you can see the Vickers hardness variation.
Hello? Hello, we can't hear you. Dr. Avaya?
Spectroscopy is sensitive and selective to these kind of this thing. So what we see here is basically you have the lifetime variation. This is actually the lifetime is quite high and then it decreases. This is actually annealing of the vacancies which are present in the matrix as well as in the matrix precipitate interface. Then what happens is that you have a you have a second shoulder which corresponds to the formation of the MC precipitates, and then you have a coarsening of these precipitates. Then finally you have again an increase in the positron lifetime. This increase is also seen in the S parameter, and this increase is also seen in the Vickers hardness, and this is understood as a formation of the martensite phase which with the high defect density. So this is another work. This is actually the dislocation-driven chromium precipitation in model Fe9Cr alloy. So why I have chosen this work is that actually this model Fe9Cr alloy has a carbon concentration of about 65 ppm only. So what they have done is, again, they have taken the sample, they have done the tempering. So when you do the tempering and you do the isochronal annealing, there's not much of a change in the positron lifetime. But beyond about 1100 Kelvin, we do see an increase in the positron lifetime. But here, if you're doing the normalization, and then if you're doing the arc quenching, what we see here is you have the annealing of vacancies associated with the dislocations. And then beyond a certain range or a range of temperature, we see that you have chromium clusters which are formed, and positron is probing the chromium clusters, and then you have a decrease. Then finally what happens is again you have an increase. So this increase in the positron lifetime is attributed to the structural transformation to the FCC phase, and this chromium clustering we get evidence from the EDS measurement as well as from the SAD measurement from the TEM. So what I would like to tell is that so because you have a variation in the carbon, so the presence of carbon totally changes the microstructural evolution in these alloys. So as against as for formation of the carbides in that Euro 497, we see the formation of chromium clusters as against as carbide precipitation. And there you have the martensitic formation that is taking place. And here you have the structural transformation to FCC. So you are able to see a very clear difference with respect to these two samples. And the positron is able to pick up these microstructural evolution. Now, coming to the recent results on the positron beam studies on the ODS alloys, actually we have this ODS steel processing. As we all know, you have the alloy powder, and along with it, you take the Y2O3, you do the ball milling, and then you have the mechanically alloyed powder, and this you subject it to hot extrusion at very high temperatures and pressures, and finally you get the ODS steel, and this contains oxide dispersion in the steel. So this is the radiation damage studies on zirconium and aluminium containing ODS steel. So what they have done is they have taken zirconium ODS and this aluminium ODS, and they have irradiated with 1.6 MeV Fe ions up to about 100 dPa at both room temperature as well as 340 degrees C. So what we have here is For the unirradiated samples, you see a very clear difference between the aluminium ODS and the zirconium ODS. So you can see that the aluminium ODS, the S parameter variation is always high, which is attributed to high vacancy content. And you can see, if you're going to see the SW correlation plot, we see that the SW plots are totally different. So there is a difference in the nature of the defects getting trapped in these samples. And once you do the irradiation, what we see here is once you do the irradiation at room temperature, so you see this is for this aluminium ODS, we see that there is an increase in S parameter when compared to this unirradiated sample. So this corresponds to the positron getting trapped in that implantation induced defects. But once you do the implantation at high temperatures, say 340 degrees C, you can see that it actually matches with that of the unirradiated sample. So you can see vacancy interstitial recombination at high temperature irradiation. So now if you are going to do the zirconium ODS, so for the zirconium ODS, you see that up to about 100 dPa, there's not much of a change. It almost matches with that of the unirradiated sample. But once you do 150 dPa, you see that there's an increase in the S parameter corresponding to the implantation induced defects. But beyond about, say, once you do the implantation at high temperatures, again, you see that it is exactly matching with that of the unirradiated sample. So you can see that there's a high tolerance to this radiation damage for the zirconium ODS when compared to aluminium ODS. Now, this is another work where we are talking about the irradiation resistance of FeCrCONI. So this, we all know that the high entropy alloy actually contains multiple elements, but yet they form a random solid solution due to the high configurational entropy. So if you are going to have elements in equiatomic proportions, then you are going to increase the configurational entropy. If you are going to increase the number of elements in the system, again, you are going to increase the configurational entropy. Again, if you are going to bring in the temperature effect, you are going to increase the configurational entropy. So the high configurational entropy will drive the system to form a simple solid solution rather than forming intermetallics. So there are a lot of papers which talk about the radiation damage or the radiation resistance in these high entropy alloy. And this is one such work where we have carried out 1.5 MeV nickel ion implantation in FeCrCONI at both room temperature as well as at 773 Kelvin, amounting to a damage level of about 100 dPa. And what we see here is for the room temperature implantation, we see that the S parameter decreases and then it saturates at some lower value. Once you do the implantation at room temperature, we see that the saturation S parameter increases because of the implantation induced effects. Once you do the isochronal annealing, you see that there is a decrease in the S parameter, and beyond a certain annealing temperature, you see that the S parameter almost matches with that of the unirradiated sample. Now, when you take the 773 Kelvin, again, you have an increase in S parameter, saturation S parameter, but that increase is not that distinct as this. That is because of the high temperature irradiation that has taken place. But once you do the isochronal annealing, again, you see that there is a decrease in the saturation S parameter, and it almost matches with that of the well annealed sample. So in both these cases, we form only mono vacancies. And we wanted to see what kind of defects are being evolved as a function of annealing temperature. And what we see here is this is actually the averaged S parameter, which has been averaged at between 12 to 18 kV, and it has been plotted as a function of annealing temperature. And what we see here is you have a decrease in S parameter, which corresponds to the defect annealing of the mono vacancies. But beyond a certain temperature, we see a second stage, and then you see complete defect recovery. So this stage is basically attributed to the presence of stable stacking fault tetrahedrons. And the presence of the stacking fault tetrahedron is obtained from the GAXRD measurement, wherein you calculate probability using this expression, which gets the shift differences of the 200 and the 111 diffraction lines. So you can see that the stacking fault probability is maximum in the temperature range, where you see the second defect recovery curve, and then you have the beyond higher annealing temperatures, you see that you have SFT collapse. Then finally you have the complete defect recovery. So this formation of SFT acts as a competitive mechanism for the void formation in these alloys, which are irradiated at room temperature. But once you go to high temperature irradiation, we see that again there is a defect annealing, the monovacancy annealing, that beyond that you see another defect recovery stage. And this stage is, again, we have done EBSD measurements in these samples, and the EBSD measurements show clear presence of sigma COCR phase. And what we see here is from the GXRD measurement, we have also tried to calculate what is the stress, what is the strain, the micro strain. So we can see that the strain increases in the temperature range where you see the defect, second defect recovery stage. And you can also see there's an increase in the lattice parameter in this stage which is primarily due to the presence of the sigma COCR. So what happens is that you have positron trapping in the nano-sized sigma COCR.
2 more minutes. You have 2 more minutes to
Yes, sir.
complete.
Yes. So no problem. So what we have is you have essentially positron trapping in the sigma COCR, the nano-sized, but beyond a certain higher temperature, what we see is you have coarsening of these precipitates, and positrons no longer get trapped in these precipitates. And these precipitates actually act as sink sites, and they increase the void swelling resistance. And this is how this behavior of the FeCrCONI for the high temperature irradiation. Now coming to the positron studies on cesium doped iron phosphate glass. So this is basically the 40 mole percent Fe2O3 and 60 mole percent P2O5. This is actually the POP linkages wherein you have the phosphorus being substituted by Fe3 plus and Fe2 plus, and they have a glass transition temperature, say, of about 500 degrees C. So what we wanted to see is we wanted to put the cesium-137 because it's a nuclear waste matrix. We wanted to see whether that is we want to incorporate this cesium into the matrix and follow the microstructural evolution of these open volume defects using the positron annihilation spectroscopy. And what we see here is this is the graph which shows a positron lifetime. So the tau1 shows there's not much of a change in tau1, which corresponds to annihilation from the skeletal network, whereas this tau2 it shows a change that is actually corresponding to the annihilation from the open volume defects that is associated with Q1, Q0, and Q2 linkages. Whereas if you're going to see that is the change here, I2 is basically the concentration of open volume defects, and that decreases linearly with the cesium loading. So what happens is that here. So what happens is that as you increase the cesium, the available voids that are here, they are getting filled with cesium, and that is why you see a decrease in I2. But here, what we see here is beyond about 18 mole percent, you see an increase in the positron lifetime, that is a defect component tau2, and that is actually corresponding to the disproportionation of this Q1 network into Q0 and Q2, thereby increasing the open volumeness in the sample. Okay, so this is actually, so now coming to the conclusions. So you have the positron annihilation spectroscopy to be a very powerful tool to study the radiation damage in nuclear structural materials, and the void swelling resistance clearly tagged to the high number of nano-sized TIC precipitates using positron measurements. And you can see that the presence of carbon leads to evolution of different positron trapping sites in RAFM and Fe9CR model alloys. And zirconium ODS shows higher irradiation resistance when compared to aluminum ODS. And FeCrCONI alloy shows high damage resistance. So it opens up a new avenue wherein you can evaluate or try to evaluate this iron-based high entropy alloy for their applications as a nuclear structural material. And positron annihilation technique is a powerful tool to follow the base loading capacity in iron phosphate class. So thank you for your very kind attention.
Thank you, Dr. Abhay, for a very clear presentation. Now it is open for question, comments, discussion. Okay. Before I take any question from the floor, I have one query. See, you are talking about the microstructural evolution, and that you are talking in terms of the lifetime change, right?
Yes, sir.
I wanted to see in terms of the size and size distribution, how it is changing, but you didn't show any view graph. So do you also extract? I could of course see that the lifetime change with annealing temperature, you could easily correlate how
Yeah,
these
yeah, yeah.
things are evolving. But I wanted to see a direct visualization of the microstructure.
Sir, actually, in most of these samples, we were able to get only a single component. That is, the mean positron lifetime is what we were able to get. So from that variation, we were trying to look for changes in this Doppler broadening measurements, taking the ratio curve, as well as doing some hardness measurement, or substantiate them with the TEM measurements. So this is how we are able to arrive at the defect evolution as a function of annealing temperatures.
See, my point is, let us say around 1000 degrees centigrade, you see how the lifetime is suddenly increasing, and you are trying to correlate with the defect evolution. But is it possible to have the real?
No, actually, like I have not presented. There are a lot of TEM pictures. I have not shown you that. Actually, they have arrived at these results using TEM measurements.
No,
And
not TEM, that can do, but from this technique alone.
from this technique alone, actually from like if you're going to look for the chromium clusters, then a ratio, actually I have not shown you the ratio curve. So the ratio curve clearly shows presence of chromium clusters in this Fe9Cr alloy. So we have I have not shown you like the results, but we have done other experiments to clearly point out to the effect that these are the things that are responsible for the microstructural evolution.
Okay, we have a question from the floor, Dr. Achari.
Hello, Dr. Abhaya.
Yes, sir.
My question is general nature. When you talk a material property, it is a bulk material property.
Yes, sir.
Most of the studies done by Positron Annihilation is surface studies. So how you correlate your surface studies or the results to material as a bulk and its property?
No, sir. Actually, the very few slides that I showed you, it's basically the positron lifetime spectroscopy, which is done. So you are able to probe the sample starting from the surface up to a depth of a few hundreds of microns, which we take it as the bulk. So, but whereas if you're going to take the results that we have shown for the high entropy alloy, basically we are looking at the damage resistance. So we have created damage using heavy ions, and they are able to go from say 0 to about a few hundreds of nanometers. So this is how we.
So we can correlate from nanometer to bulk. Are you telling that?
No. Actually, this like I think I have not properly convinced you. This studies that I have shown in the case of austenitic stainless steel, ferritic martensitic steel, as well as this Fe9Cr, all these studies have been carried out using positron lifetime, which is a bulk measurement, which means that you're going to get the average defect information, because you're going to sample the defect starting from surface up to a few hundreds of microns. Whereas if you're going to see in the case of zirconium ODS, aluminum ODS, or this high entropy alloy, we have done implantation, and that implantation effects is about from say 0 to about to 1 micron. So we are able to study them using the positron beam.
Yeah, understood.
Thank you.
Any other question? If not, I have one more quick question. See, for the high entropy alloy, in one hand you are talking about this positron annihilation, and you are, I believe, extracting information about your defects. Now you are comparing that data with the gauging incident X-ray diffraction, where we see the grains or the particles. Now, how to correlate? In one side you see the voids, defects, and another one is the particles. So how you are correlating? Could you kindly clarify?
No, here basically like here we are seeing stacking fault tetrahedron. It is also a different configuration of the vacancy clusters, and that we are trying to correlate with the with the GXRD measurements where we get the stacking fault probability. So the stacking fault probability says that the probability of getting stacking faults is more in that temperature region. So
Okay,
this is how we try to correlate. Actually, we have not done TEM measurements.
My only point is that as per the XRD, it is not probing the stacking faults. It is probing what material is there. So that was my point. Anyway, with this, I have to end this discussion and we have to move on to the next one. So before that, I thank you once again for a nice presentation. Thank you, Dr. Abhay.
Thank you, sir. Thank you.
I move on to the last talk of this session, that is IT10, and it will be delivered by
Escape.
Sudarshan from Radiochemistry Division of Bhabha Atom Research Center.
Just to close it, the share content.
And the title of his talk is 3 Decades.
Already they have disabled. Stop videos.
At Radiochemistry Division of PRC.
Good evening. Let me start with the outside saying that my talk is slightly different in the sense that it covers more of scientific history rather than the science itself. So when I'm talking about scientific history, let me start with a disclaimer that any historical inaccuracies are purely inadvertent. So with that disclaimer, let me start my talk of 3 decades of positron chemistry at BRC, which is the scientific history of the group, and why these 3 decades is an average career span of a researcher in an Indian context. And I consider that the case study of growth of positron laboratory at BRC in these 3 decades could be a case study for building the lab around nuclear probes. And that is further important because the society that is organizing this conference, SPAN, one of his first aims is to popularize the nuclear probes. So I felt that this would be apt for the audience. And the initiation of positron laboratory was around 1985 in the nuclear chemistry group of radiochemistry division, where most of the researchers were involved in charge and mass distribution studies of fission products. So they had the expertise of radiochemical separations as well as gamma spectrometry. So hence, Professor Satyaprakash and Dr. Tarun Datta thought that this is the Patta-Bragg correlation and positron laser spectroscopy. These two techniques are the right ones which can be taken up as the nuclear probes with the expertise that they had in the group. And around that time, Dr. Pujari has also joined the group. And the only infrastructure that time available was copper-64, which could be produced in the reactor, and a 2cc HPG reactor, and lot of motivation, definitely. And the first humble beginnings came in the form of these 2 symposium presentations, one by Tarun Datta et al. And other by Pujari et al. In the radiochemistry and radiation chemistry symposiums at Kanpur and Tirupati, where the interaction of positron with charge transfer complexes was studied, and it was found that the charge transfer complexes show a different momentum distribution, and this, please do remember, in the current context was done with a copper-64 source, which is not carrier free, which means that in the today's context, more than 80% is source correction and 20% you are looking for the signal. But may not be acceptable now, but it was the norm that time. And with this humble beginnings, the initial baby steps were in the form of these 2 papers. One is the positron interaction in the organic solvents, communicated in 1987 January, early January, and published in 88, where again copper source was used for the Doppler broadening annihilation studies, and it was deconvoluted from the detector response. And later it was, nowadays it is felt that you cannot really deconvolute in a unique way, but still it is some sort of parameterization where it was dissolved into narrow component and broad component after deconvoluting the detector response itself. And it was shown that the narrow component was higher wherever the charge transfer takes place between the 2 chemicals that are used, which is mostly iodine and pyridine, etc. And another initial study was the positron annihilation spectroscopy studies in the YBA to CE3 superconductors. Again, Doppler broadening studies as a function of temperature, because by this time a cooling system with cryogenics was also procured, but with copper 64 source again, where with superconducting transition, the narrow component in the momentum distribution curve is shown to change the phase transition. But from baby steps to getting foothold started after procuring about sodium 22 source about 1991. And this is necessary for doing the positron lifetime measurements, whereas with the copper 64, only Doppler broadening was feasible. But even then, they didn't take the risk of using the sodium 22 says at higher temperature as shown here. But to understand the phase transition, still the copper 64, thin copper 64 wire irradiated was used as the source for the Doppler broadening studies, whereas the room temperature lifetime studies were measured with the sodium 22 source. And in this shape memory alloy, the S parameter change, drastic change in slopes at the two temperatures where the disordered to ordered transitions was occurred. And this is the more significant papers that have been come after this, I would say. These are my personal opinions. And further staying with the similar studies, and more number of papers I have picked up papers, one for each type of work rather than taking all the work. So this is in the high temperature superconductors, where by this time of 94, even the low temperature dependent lifetimes were also initiated, and the data analysis steps, etc., were also taken with improvement in the terms of computational skills, where it was shown that the below TC, the positron lifetime decreases. This is the S parameter curve, but even the lifetime data was reported in these superconducting papers. But by around this time, the initiators of the work, Dr. Tarun Datta was no more, and Professor Satyaprakash took VRS, and Pujariji was left alone. And after two more additions in the form of a PhD student in Hemant Sode and a visiting student in Anjali Panda, the diversification of the group started towards the polymer science, and where free volume distributions as a function of temperature and different modifications were the norm of the studies there. And in terms of the infrastructure or the technical skills, from the positron lifetime, it was slowly moved to free volume distributions via Canteen, where the lifetime distributions were being evaluated by this time in the polymers to understand the diffusion of the ions in the polymers as well as the structure itself. And that was also extended to few porous materials, where the pore size distributions, etc., were compared with the other complementary techniques. But this was more of the first decade where the strong foothold in the field was achieved. And going further in the second decade came the real infrastructure boost in the positron laboratory. And it started around 2001, where the coincidence Doppler broadening, till then the facility that we had was the positron lifetime and Doppler broadening, the two systems, was the coincidence Doppler broadening. And this decade, there are many more instruments facilities which have been developed, starting with coincidence Doppler broadening, where two detectors was used in coincidence to get the elemental specificity via the high momentum region of the Doppler broadening spectra. And this is the first paper published using this. That's why I have included this, where the positron annihilation studies and another high temperature superconductor was studied. And it was shown that the boron layer is the one where the positrons are localized via the Doppler broadening spectroscopy. And it was shown that the lifetime reduces below TC, and which gave some sort of conclusion that it is the boron layer that is active in the superconducting transition in the MgB2 layered structure. And further improvements in the boost in the infrastructure came in the form of slow positron beam around 2005-6, where we could vary the energy of the positrons so that the depth-dependent Doppler broadening studies can be carried out, and it is a continuous beam. And this gave the impetus for depth-dependent Doppler broadening studies, and I've just included one work where it was in situ lithium nanoclusters formation and their disappearance mechanism as a function of annealing temperature was studied by implanting lithium in alumina and annealing them at different temperatures and observing the Doppler broadening profiles, which have shown that they grow initially and then diffuse out. And further, infrastructure boost only I'm talking about is the another system, which is the age momentum correlation setup, which allows us to follow the Doppler momentum as a function of age of the positron, which gives the more specific localization sites of the positron, because for each lifetime component also you can individually calculate the momentum distribution rather than Doppler broadening and lifetime being disjoint. We are doing a correlated measurements, which was used in many of the papers where we could identify the sites. In this case, it was interface of magnesium and nickel oxide, which was the sites. And going further with the infrastructure, it is another facility was the photon-induced positron annihilation spectroscopy, where so far all the methods that I have measured, that I have covered were where we use either thin film samples in case of ion implantation studies, or otherwise 1 centimeter by 1 centimeter samples of 1 mm thickness for the conventional studies. But this was done to where you can measure the samples of any geometry, where the thickness of the sample is not limited by the positron, but is limited by the 511 keV that is coming out. So, which means that almost an inch of the sample could be as thick and in any shape. And in situ, photons were measured, produced via the nuclear reaction of proton and fluorine. And I would say the working in the nuclear chemistry group helped in choosing these targets at a combination, which gives you 6 MeV gamma rays, and that could be impinged on samples to produce photons, which gave the liberty in the sample size too. And this was used in understanding the, comparing the defect failed turbine bed and a normal one. We could see that in the failed region, there is a huge change in the S parameter, which is the fractional area in the narrow momentum region, which I was referring to earlier. Whereas in the normal, where it didn't fail, it didn't show any difference. And this was extended to understanding the residual stress in zircon plates, which were rolled to different stress, and very good correlation between the S parameter and the residual stress measured from XRD could be observed. This shows that this technique can be used for very thick samples irrespective of the size. And this is the second decade which comes to the infrastructure boost. And with the infrastructure development, we have really diversified in the areas, which the third decade I consider to be spreading the wings or diversifying the research areas, as well as I should not be, just because I am from the positron group, I shouldn't be saying that that is the only technique that can solve all the problems. So enough complementary techniques were used when you are addressing the problem as such. So our research is centered around positron annihilation spectroscopy. So now I would be covering some of the areas that we ventured in. And studies using slow positron beam is mostly about the radiation damage studies, which is one of the important departmental programs where you can cause accelerated damage in the nuclear materials and understand the defect evolution in them. And in terms of different regions like tail region and the actual damage region and non-radiated region, this is the 3 parameters in most samples that we use. And this was used in qualifying the nickel chromium alloys from 2 different commercial sources in terms of their sustainability for different radiation damage, which was required for the department, and where one was showing a higher radiation damage resistance with respect to other from the 2 different commercial sources. And this was used as a qualifying technique. And in the staying with the nickel chromium implantation itself, in the helium implanted nickel chromium alloys, it was seen that in the tail region, the defects formed are mostly isolated vacancies, whereas in the cascade region, helium is associated with that. So similarly, we have carried out studies on many of the alloys and early stage hardening in the nickel chromium alloys, etc., and continue to carry out the studies on various departmental samples. And this is a study which uses the photon-induced positron annihilation spectroscopy in scanning the PHWR pressure tube. And it was shown that at 2 of the regions, means which this was about 16-inch long pipe, which was scanned using photon-induced positron annihilation spectroscopy. And this region also showed abnormalities via eddy currents and has some issues with the stability of damage of the tube. And it's not that the departmental doing the departmental work doesn't lead to publications, and this was an indication that basically we are a research group and we continue to publish. And staying with the positron beam related work, the molecular packing of organic molecules in the engineered surfaces where thin films were studied, and it was shown that the modification of the surface was necessary for a regular growth of the films when compared to unmodified surface. And all these studies are also leading to a good publications, I would say. And the other area is of porous materials, where this particular example shows that the positron lifetime data and the pore size measured from different techniques, when it is compared, there is a huge scatter in the data, and it was shown that it is because of the vacuum level that is maintained or the oxygen that present that is quenching the positronium. And it was also realized that the quenching rate is a function of pore size itself. So after correcting for all these things, a model was given from our group which relates the positron lifetime measured in air with the pore radius, where you can correct for the oxygen quenching, and this quenching is pore size dependent. Later you will realize that many of the properties of even the liquids change when they are present in the pores, and that is also taken up in the later stage. Staying with the porous materials itself, and whatever I was talking about earlier was the inorganic porous materials, and these metallo-organic frameworks, which are flexible frameworks, though they are also porous materials, but when you are comparing with the other complementary techniques, like nitrogen adsorption isotherms, etc., they have a flexible pores that the nitrogen pressure itself changes the pore size, which means that it becomes more difficult to have the pore size estimation, whereas positron becomes a non-invasive probe, which doesn't really alter the pore structure. And using this positrons, it was shown that this aperture size in the GIF8 is dependent on the crystallite size, and that is the reason why this gate opening phenomena, or where the aperture size increases with pressure, appears at a higher pressure in the smaller particles or the smaller size nanoparticles, simply because the size is smaller in them. But in the other conventional studies where the single crystal has been grown, it is crystallite size was grown to large enough that it is a comparing with the other techniques becomes difficult. And also this pore interconnectivities, etc., and the pore architecture change in the metal oxide films, powder samples, etc., were measured as a function of temperature, and it was shown that when you grow the films, the interconnectivity is there, but it collapses when you anneal at the higher temperature, etc. And all these studies of porous architecture are very important because you can measure even on the powder samples. In the powder samples, the only other techniques that are feasible are gas absorption based, not the single crystal based. And the gas absorption isotherms give a bias because of the flexibility of the pores. And this is about the nano droplets, where I was saying that the nano sized droplets, when the liquids confined in the nanometer domain, show different properties from the bulk. And lot of studies have been carried out, and there is a specific lecture on the nano droplets tomorrow by Dr. Datta from our group. So you can tune into that. But just to give a brief introduction, many parameters were studied on the nano droplets, like surface to liquid interaction and liquid-liquid interaction, how they are going to change the phase transition of the liquids confined. And also when you are taking the mixture of liquids, how does this surface interactions lead to segregation or formation of micro droplets within the nano droplets, smaller domains of varying concentration, etc. And also how does the freezing start from the surface and continues into the bulk. And you can listen to the more details of this work tomorrow, so I am going faster in that. And another area which we ventured in is the polymer nanocomposites, where large number of nanocomposites in different combinations of polymers and nanoparticles were synthesized, and free volume distributions were evaluated to understand the effect of shape of the nanofiller, dispersion of the nanofiller, and its concentration, and the interfacial interaction between the polymer and the nanofiller. And in many cases, it has been seen that wherever the interaction has been very weak or very strong, it leads to a bimodal distribution sort of thing. And in other cases, it simply changes rather than being the bimodal. staying with this and during this, we have also incorporated many parallel techniques from thanks to our collaborators, etc., where the techniques like small angle X-ray scattering, dynamic mechanical analysis, broadband dielectric spectroscopy were used to understand the relaxation dynamics of these polymer chains and also correlate with the free volume distributions that I am talking about. And staying with during these studies itself, one of the interesting things that we have realized is that when in solid polymer electrolytes, it is considered that semi-crystalline polymer like PEO, if you can amorphosize it via incorporation of nanoparticles, it increases the ionic conductivity. That is the perception that is there. And there are people are going on trying to incorporate various fillers so that it would amorphosize. But once during these measurements, we have realized that when it was doped with alumina particles and alumina nanowires, alumina nanowires increase the ionic conductivity to a larger extent, even without much change in the crystallinity or free volume region. So which gave a suggestion that probably the alignment of the free volumes is more important than the free volume concentration itself, because the nanowires are giving a higher conductivity. So to get an aligned way of free volumes are the transport channels. The GIFs that I was discussing, which were prepared as films or powders, etc., were thought to be right candidates to incorporate in PEO. And incorporation of GIF in PEO, though didn't change the free volume significantly, has increased the ionic conductivity by an order of magnitude when compared to the other fillers, and it shows almost close to the commercially available ones. And the initial testing of this solid polymer electrolyte, it is also very encouraging. And this is part of the work of one of the students of Dr. Pujari. And staying with the other areas, this is the defect evolution in Syria, which is used as a catalyst by introducing the oxygen vacancies, where we have shown that if you co-dope one trivalent and pentavalent, you can simply dope trivalent to create the oxygen vacancies in the system, and also you can co-dope with niobium so that 1+4 is replaced, 2+4s are replaced by 1+3 and another +5 charge state, so that the oxygen vacancies are removed. But combining with the positron lifetime and the photoluminescence studies via the europium emission, we could see that by charge compensation, you can remove the oxygen vacancies, but this doesn't really fully account for the size mismatch between cesium, europium, and niobium, and still the distortions in the structure exist, and the initial lifetimes in the positron are not restored by even co-doping with niobium, whereas as far as the photoluminescence in terms of the retaining the octahedral symmetry is concerned, it comes back. Similarly, the other is the photoluminescence in NDU ZR207, which was annealed at different temperatures, etc., to remove the defects. And it was shown that the photoluminescence yields and the lifetimes increase as the positron lifetimes decrease, or the defects in these cases are giving a non-radiative pathways for the materials. And these are the different fields that I was talking about, and currently we are developing the pulsed positron beam light.
You have 2 more minutes.
Okay. And these are the first results where the polyimide RO membrane was studied, which contains a narrow pores in the surface and the deeper ones in the name of polysulfone region. This is the first results. Probably more studies would be carried out on this. To summarize, this is the second decade where we have developed so many FSTs, which I have already talked about. Besides these experimental FSTs, we have also developed the skills of megadoppler calculations and VASP calculations to supplement our experimental studies, and the fields of research with the new people joining as been to thin films, liquids under confinement, polymer composites, defect engineering, porous materials, and defect and radiation damage in alloys, etc. And for the future outlook, we are trying to, this is still in the drawing board, where we are trying for the reactor-based positron beam, which would give you a much higher intensity than what we are working in the laboratory. And all the work is published in close to 200 papers, and you can see how we have grown in the 30 years. And the most number of papers published in a single journal is Physical Chemistry and Chemical Physics, and followed by Journal of Physical Chemistry and Journal of Nuclear Materials, where the departmental samples are studied. And the group also has received enough recognition at the departmental level in terms of various awards to the group members and also other prestigious fellowships like JSPS, Max Planck, Indo-US postdoctoral, and then INSA bilateral, etc. And at the international level too, we could win the bid to organize 2 international conferences, which is the Positron and Positron Chemistry 11 and also Positron Studies of Defects, which we could successfully organize, and also were members of the International Committee on Positron and Positron Chemistry, etc. And to summarize, the Positron lab is on 4 pillars. One, first being the visionary leadership and dedicated and passionate workforce and strong institutional support and collaborators with matching scientific temperament. And these are the 4 pillars on which this lab has grown in the 3 decades. And these are the people who were associated in the past intermittently or briefly: Professor Satyaprakash, Tarun Datta, Goswami, and Amit. And PhD scholars who did PhD in our group and left: Hemant and Pushkar. And Muthu has just submitted the thesis, and Pranav will be submitting in a week or 2. And these are the visiting or part-time students, Prashant and Anjali. And the core group is this, with Dr. Pujari being associated with this work for the last 35 years, and followed by the others: Sudarshan, it's me, and Dandeep, Sandeep, Saurav, Priya, Devarati, and Jaydeep. And thank you.
Thank you, Dr. Sundar sir, for doing an excellent job covering these 3 decades activity in just 25, 26 minutes. And it is very difficult, but you brought out very, very nicely. And in fact, I'm really pleased to see that. I mean, unfortunately, this is my very first, first time I'm witnessing the journey of this Positron activity in BSU, though I'm aware of this activity right from my early days, but somehow didn't get the opportunity. Sorry for that. And it is really satisfying to see that. But I have 1 or 2 technical questions. In superconductors, when this onset of superconductivity leads to the dropping of the lifetime. Now, how to explain this?
In most papers, it is explained of Cooper pairs being reducing the positron lifetime by.
No, if you have to go that, I was also thinking that way. So then is it under field study or without magnetic field study?
It was without magnetic field, only temperature.
So if without magnetic field, if it is under magnetic field, I can understand the vortices are there, and that will cause like a, the defect center. But without that, so.
See, in most papers on superconductivity, it has been mentioned that at below superconductivity, the electron mobility has increased and that has reduced the positron lifetime, except in one superconductor where I found that they have talked about not the lifetime, but they did the Doppler broadening, which is supposed to give complementary. And if I extrapolate that into lifetime, it should have increased, but they have reported only Doppler broadening. That is about 92 paper. But in all other papers I came across, it is the lifetime that is reducing. And they explained in terms of the higher electron mobility at these temperatures, where the chance of positron encountering the electron has increased and the lifetime has reduced. That is the explanation that is given, but not the any first principle calculation of estimating the lifetime.
Because the experimental observations are very, very clear, and I mean, really good to see that. One more question. See, you were talking about the dynamic study, which is carried out by SACS and other methods. The system is evolving with real time. Now, when that happens, what is the signature you get in the Positron Annihilation?
See, in fact, when you're doing the Positron Annihilation, positron lifetimes are so small that effectively you are measuring the dynamic free volumes, not the static free volumes as such. Because
no, I mean, it depends upon what is the dynamic time scale. Let us say when you see in SAC study, so their time scale, and whether that time scale matches with your typical nanosecond time scale, because positron lifetime itself is nanosecond kind of. So some dynamic has, if it is there over that time scale, which is of nanosecond, then only you will be able to see. If it is larger than that, then it is static or other way. So can you throw some light on that?
See, even in the dynamics of the chain dynamics of the polymers, it has been shown that when, if I talk in terms of alpha, beta relaxation, if you go for the low temperature dependent studies, each type of relaxation could be deciphered by doing a temperature dependent positron lifetime. But if you are doing it at room temperature, it depends on what is the glass transition temperature of the polymer that you are dealing with, etc. When you are really focusing on the dynamics of this. In certain polymers at room temperature itself, all are active. In other polymers, only some of them might be active. So whenever you want to decipher different types of relaxation, you need to do a temperature dependent sort of thing. So that always varies from case to case, which may not be uniform.
Any other question from the floor? Any question, comment? Yeah, please.
Sudarshan, this is a nice compilation. You know, there are many known techniques. When you think of a study, we always go to a technique, go to this technique. We have contributed a lot, so I am in same division. When I think of a study, how a researcher or a person from non-field can be attracted for positron, can you just give some idea?
I'm not sure if the answer is too simple for that. But at the same time, let me tell you that, see, techniques are just tools. Unless you choose the problem wisely, means you cannot have a sword and go for grass cutting. Finally, you have to have the right tool for the right purpose. And even for the positron, it is true. You cannot say that positron will be able to, it's not a magic wand which can solve all the problems. But there are enough areas where positron scores over the others. And there are also complementarily other areas where positron is inferior to the other. Unless you complement with the other techniques, it doesn't become really convincing enough. But at the same time, there are enough areas in positron annihilation technique where they score over it. For example, one of the studies that I was presenting, or even the speaker before me was presenting, was the radiation damage, right? Where you, when you are doing accelerated aging, you have to be depositing with the charged particles, which hardly gives a few nanometer damage. And there are not enough techniques which can still preserve the integrity of the sample and still measure the defect study. There are techniques. I am not claiming that this is the only technique that would do it. But this is the only technique which would preserve the integrity of the sample and still give you the damage. So if you are choosing the problem wisely, there is no problem. But if you want to just pick up any sample and measure the lifetime, it gives you a lifetime. It doesn't give any other meaning to the lifetime or any of the other. So definitely as a researcher, it is left to the wisdom of the researcher to choose his problem, not the sample. And the problem, when you choose it, automatically other things would follow.
Okay.
Of course, I add here that sitting here over these three talks, I could learn that the potential of this technique, and it is going from whether it is superconductivity, whether it is microstructure, whether it is magnetic sample, whether it is ion irradiated, material science. So it has, whether it is case kind of structure, whether it is porous material, and but what I have been always talking about, that so far what we could observe, I mean, what was presented here, that always data presented in terms of the positron lifetime variation and so on. But I was thinking from that, can we not extract by modeling the real space information directly or the time scale information directly? So with all this, I see the enormous potential. In fact, I am very much tempted to, to use this technique for even for where there is a magnetic phase transition. If I am looking at the luminescent spectroscopy study, and I can see the luminescent spectroscopy, if I apply on some material, let us say where the electronic transition is taking place, whether it in terms of magnetic ordering or electron proton coupling, so there will be corresponding change. And if I tune that, I will be able to tune it by applying external perturbation like magnetic field or even pressure. So there's enormous potential of this technique. I think even sitting in BRC, I'm sorry that I didn't get opportunity to learn this before. Anyway, so I really appreciate. And of course, the major thanks goes to none other than Dr. P.K. Pujari.
He was the first pillar.
Yeah, so I really appreciate, and this is my eye-opening, I will say. Thank you so much. So I think with this, I'll close this session. I'm really happy to chair this because I could learn a lot. Thank you so much for giving me the opportunity.
Thank you.
On behalf of the organizing committee, I thank Dr. S.M. Yusuf, Director of Physics Group, for chairing this session. Before concluding our today's program, I'd like to convey warm regards and gratitude to all the invited speakers from India and abroad for their fascinating lectures, all the honorable delegates and participants who have attended this meeting both online and offline. And I'd like to invite all of you to join the dinner party, which is arranged at Oasis Deonat today from 7:30 p.m. onwards. And tomorrow we will be meeting at 10 a.m. at the same venue for the second day of our theme meeting. Thank you very much.